you can hear me?
Sure, we can hear you.
Okay, and this is visible. Is the animation visible? I will animate little bit. It's
It
okay.
is visible.
Okay, all right.
It is visible. Yeah.
Let us hope.
Yeah.
I normally never pray, but I will pray that it will not give trouble during the lecture.
We hope so. I mean,
No, sir, it will go well.
yeah.
Okay.
ठीक
Okay.
है.
All right.
Sure. Good morning, and you're fine, sir, today?
But can you see me? I can't see
We can
myself.
see you. We
Yeah,
can see you
but
in another window.
I would like to see myself also in a small window. It is not visible.
You want to see yourself in a small window.
Yeah, it is always there. No, the speaker should know that he is online.
अच्छा देखते हैं सर को दिखाओ ना, वो शायद देखना चाहता है खुद को
नहीं छोटा एक विंडो आता है ना, अने
वो छोटा विंडो हम लोग देख पा रहे हैं.
देना ना अपने हाथ.
नहीं आएगा.
ये फुल स्क्रीन है ना सर.
Okay, all right. I'm given to understand. My support tells me that since I am now on the full screen in the slide mode, I can't see anything else. Although I'm seeing you.
You can see me, na?
Yeah. I mean, I see your back, not you. I mean, I see
okay, yeah.
You are waving, but on the opposite. Now I can see you face.
Yeah, I request this mic people, they can focus on the crowd so that he can see the crowd.
Okay, all right.
Mike, this you focus to the crowd so that sir can see the crowd.
Is not important. What I want is what I have to say is visible or not. That's more important.
Crowd दिखाओ.
ये बंद कर सकता है ये नहीं?
You can see the crowd now, sir?
Yeah.
Yes, I do see background. Yes.
Sure. Good. Front there is chairs.
Okay,
so that backside people, please come here.
I will leave everything intact and join you after about 10 minutes, 8 minutes, 7 minutes. Is that okay?
Yeah, we are ready. So whenever you want to join, tell us. We'll join.
Well, I was given time of 11 o'clock. I can
sure.
talk even
now, but
it's better to keep the time.
no
Although I'm personally notorious for always exceeding my time. At least
we know, sir.
I should keep time.
ठीक है. 11 o'clock we start. In my watch it is 5.
I will join at a few minutes to 11.
Sure. Thank you so much.
Yeah, but I will leave the connection on so that we don't have to struggle again.
Please. Yeah. It's 5 minutes in our watch, another 5 minutes.
Okay, within 5 minutes, I will join. Yes.
Sure, thank you. This side is showing opening up. Because sir is going to see the crowd, we have arranged it in that way. So I request all the participants from the absolute back to come in the front, these chairs. One day you people also will be teacher, and a teacher feels great if the students are very close by. Okay, understand this simple philosophy of a teacher, psychology of a teacher. Make him feel good. Okay, all of you come and fill up the front. ये प्रोफेसर्स लोग को भी बैठा देते हैं ना, प्लीज कम ना, he will feel better ना. All speakers please come forward. Please come. Indrajit, come. Why he is alone? Speak, sit na. Everybody can come. Patro, जाओ बैठो. इंद्रजीत के साथ बसे जाओ. Good. Yeah. Very good. Yes. See, make sure that these empty chairs are not visible. Okay. The moment this camera is going around, it is only focusing on empty chairs. I don't know. The camera is tuned to that way, I think. Okay. And backside, so many empty chairs. So Professor Mehta will be able to see you. Okay. Yeah. He doesn't like so much. So just you don't know Professor Mohita.
Leave it.
वो पहला क्या बोला 11 बजे
ठीक है सर, आप ठीक है सर, ये
एक मिनट नहीं इससे बोलो
किसी को यहाँ
My voice will reach. Don't worry. My voice is so much can reach. That's it. सब बन जाएगा ठीक है. Sir, are you ready?
Okay, I am ready now.
Okay, fine. Good morning, young students, participants, dear faculty colleagues. It's a great honor for me to be present in a dash where you have Professor Mehta on the screen and going to deliver a lecture. I will not be audacious enough to introduce him. That will be the worst thing in my life that I would do. So you all know Professor Govardhan Mehta. And he is awarded not only by this country, but by all countries. And we have a very detailed CV or brief description of his research in our book, and you can always go through it. Young students also know him, so therefore I would also tell the young students, if you don't know him, you listen to his lecture, you will know him. And These days, Professor Mehta talks about one thing I'm curious to know, that is called systems chemistry. Today in his lecture, he will be talking about pivot chemistry, a pivotal science for sustainability of people and the planet. With these words, I now invite Professor Mehta to give the plenary talk in this particular symposium. Professor Mehta.
Okay, thank you very much. I hope you can all hear me and see my slide.
Yes, sir.
Okay. So first of all, very good morning. Our traditional namaskar to everybody, and of course, season's greetings. I must say that it's a great pleasure to participate in this workshop. Particularly, it is being held at IIT Bhubaneswar. I have had many connections with IIT Bhubaneswar, so it's a special pleasure and privilege to be part of this workshop. My lecture today, as you will notice from the title, is going to be very different than the kind of lectures that many of you might be used to hearing in a chemistry workshop or seminar. And also perhaps you will hear in this seminar as well. What I'm going to really do is to take you for a grand safari of the chemistry world. And during my presentation, particularly because you will hardly see any chemical reactions and reagents and transformations with which you are generally familiar, because I wish to show you and tell you that today you might feel that my lecture is a bit out of place for your symposium. But if you were attending a symposium of this kind in the 22nd century, and I'm sure that there are many of you who are very young. Hopefully you will live to see this 22nd century. You may find that what I have to say will be relevant at that time. So it's a very futuristic view of our science. Now, what I'm going to really do is, my gosh, I thought I had checked, but it looks like animation is not working. Is animation working? I mean, is my slide moving?
No, not yet, sir.
Not? मूव नहीं कर रहा है. मूव नहीं कर रहा है.
You can try moving to the next.
Okay.
Slide. Yeah, yeah.
It
is
now?
moving. Yes, yes.
Okay. So what I'm going to present to you is an expansive view of chemistry. And my focus will be on chemistry matters that matter. It's not going to be reagent-based, transformation-based, reaction-based. It's something more profound, something more deeper, and something which is very futuristic. I would also really be presenting a 360-degree lens on chemistry horizon. And my focus will be of a new proposition that I am going to make, is that chemistry needs repurposing. You are all perhaps become familiar to the term repurposing during the COVID pandemic and the need for discovery of new drugs and so on. But please remember, chemistry also needs repurposing, rather urgent repurposing. And I would try to validate this statement in the next 30 or 40 years, why we need repurposing. It is very routine that one must share first the outline of my presentation. I have 4 bullets that I'm going to be talking about, but frankly, in today's lecture, I will only focus on 2 aspects. Chemistry as a molecular science for sustainability, and then share with you new chemistry opportunities, which in my view are going to dominate the march and movement of chemistry in this century. So let's begin first by looking at one of my very favorite quotes, many of you might have heard before, which says chemistry ought not to be for chemists alone, This is a quote from a Spanish philosopher who was not a chemistry student, but he recognized the importance of chemistry. And I want that all practicing chemists, whether you are a student, early learner, you are faculty, or a promoter of chemistry, must keep in mind that chemistry is a science for everybody. And in fact, you will see at the bottom of this slide, we wrote an editorial in Science about 6 or 7 years ago, whose title was very simple: Chemistry Embraced by All. So everybody should embrace chemistry. And this should be also a kind of task that every student and learner of chemistry should propagate. Why it is necessary that everyone should know chemistry, where every citizen should learn chemistry? This is because chemistry is about life, chemistry is about our universe, and actually chemistry is about everything. And you will see this in the backdrop of an imaginary chem connectome that I'm showing you here, which is nothing but the neural network in the human brain. What does it show? It shows that it has endless, infinite connectivity. And one of the main attributes of chemistry is therefore indicated by this. And that is, chemistry offers unlimited avenues for interdisciplinarity. No other branch of science can parallel the interdisciplinarity canvas of chemistry. The second point that I'm going to emphasize during my lecture, and it will become obvious, although I'm not going to talk specifically about it, is that we know chemistry is molecular science, but we have never recognized that this molecular science has planetary implications. I'm going to point out to you some of these planetary implications. What it means is that this molecular science has planetary implications. And if you combine interdisciplinarity and molecular science with planetary implications, it leads to a very straightforward conclusion that chemistry is nothing but sustainability science, where both its interdisciplinarity and its molecular attributes play out fully. I would even venture to say, and this is my own proposition, you may laugh at it or you may enjoy it. I like to look at chemistry basically as a rainbow science. It has many colors, not colors in terms of dye stuffs that you are familiar with. It has many colors and many dimensions. And therefore, chemistry can also be considered as rainbow science. Having said that, let us now begin with the main theme of my lecture. And I will take you back by 3 centuries to 17th century. And many of you might wonder, we are in 21st century. You have already talked about possibilities for 22nd century. Why are you starting with 17th century? This is to provide you the backdrop in which I am going to position chemistry. Why 17th century? Because the science as we understand today was actually started or born in 17th century. You see here Francis Bacon. And you also perhaps know that science is many times referred to as Baconian science. The second reason why 17th century I have chosen is, you see here the photograph of Robert Boyle. You are all very familiar with him. You know, he is attributed to have coined the name chemistry. Many of young learners might be wondering, where did the name chemistry came from? It's actually Robert Boyle who supposedly gave and coined the term chemistry. So that's why I chose 17th century as the starting point. And I have to share with you a conversation between these two humans. And what was the conversation like? Their conversation ran something like this. Our air is clean. Our water is pure. We all get plenty of exercise. Everything we eat is organic and free range. But something is just not right. And they identified many things, but I am going to show you some 2 facets of their conversation. First, they said nobody lives past 30, and a lot in life is missing. So life was in some ways incomplete, although life was very organic to live with. And this then brings me to a question which I must raise, that 3 centuries later, when we are sitting together in the 21st century, what has changed in recent centuries, in the last few centuries? How and why? The fact is that chemical sciences has been pivotal in advancing human development, whether it be health, wealth, quality of life, and even our survival. In fact, you will shortly see that the very fact that we are all sitting here and we have survived is largely because of the chemical sciences. I just want to share with you some numbers very quickly. What has really changed in last 3 centuries? You know, global GDP, which was 1 trillion in 1800, now is 100 trillion. The life expectancy that I referred to a little while ago was 30 years in 18th century. Today, it is 73 years and rising. And lo and behold, the world population in the 17th century or end of 17th century was 1 billion. And you must have read a couple of weeks back that the world population has reached now crossed 8 billion. Question I ask is, how are we surviving? And I'm sure you have read while studying nitrogen fixation that the planetary ability of nitrogen fixation can only feed 2 billion people. But today we are living in times where about 8 billion people are surviving with reasonable degree of food sufficiency, whereas nature can only support 2 billion people on our planet. How has it happened? And I'll say that much of this credit must be given to chemistry, not chemistry alone, but in concert with other disciplines, reflecting the true interdisciplinary nature of chemistry. So I'll just show you what chemistry in concert with other branches has done very quickly. You will see the first picture is of food security. You see fertilizers enabled that. You will see that most people in our planet, 8 billion, have some kind of shelter. I just show you a symbolic cement plant. So chemistry in concert with other branches have enabled shelter. You will see mobility. Everybody is on the move now these days. And chemistry had promoted mobility, particularly through fossil fuels. So you see here a picture of refinery. And of course, we need energy. The very fact that today we are communicating is not only because of the internet, but the basic requirement for any gadget or for any connectivity, the fact that you are sitting in a life, the requirement of energy. And you show here a coal plant. This is not very desirable in today's context, but the fact is that conversion of coal to energy was enabled where both chemistry and physics and other branches of engineering were involved. So thing to remember to set the stage for our discussion was chemistry has enabled access to a breathtaking array of new materials and objects such as plastics, alloys, polymers, dyes, pharmaceuticals, name everything. Because I said everything on our planet owes its origin in some form or the other to chemistry. So chemistry is changing life and changing lifestyles. And for all this, let me once again emphasize interdisciplinarity was essential. If today anybody is practicing chemistry without significant involvement of interdisciplinary arenas, that chemistry is incomplete. So this is an important message I wish to leave with you. Now, all this advance, is very welcome and we all recognize it. I've shared with you. But this advance has also unfolded some side effects. Like all good effective medicine, you always have side effects. What are the side effects? I'm not going to dwell in detail about these side effects, but I'll briefly mention the side effects which are at the planetary level and at the global level. Some of these side effects, for example, is global environment is under severe stress. I don't have to go into this. Pollution is increasing, biodiversity we are losing at an accelerated pace which has never been witnessed before, leading to accelerated extinction of species, climate change, adverse events, and we have, of course, as I said, food and water stress. In another arena, economic and political, but a planetary dimension, is globalization, which has been taking place for last 25 years, and now we are at the threshold of deglobalization. We see conflict, violence, multiple crises, inequalities, population challenges, and so on. So you can clearly see that many side effects have come through the developments in science in general, and of course, chemistry has also contributed. This has also come at a personal level. Every human being and the human body and mind have been affected by these developments. Some of them are familiar with you, new and re-emerging disease. There is a lot of talk about AMR these days. We have recently witnessed epidemics and pandemics, and that continue to grow with increasing number. The world population, although has increased to 8 billion, but aging and geriatric population is a big challenge. Aging brings some problems, and that is because predominantly we have geriatric population. And a major side effect of all this advance and development has been that there are severe behavior and mental health issues. And I don't have to elaborate, but I must mention that all this advance and development has come with a price. So what has been the cost for all this development? And I would begin by simply stating a well-known fact to you. All material used on our planet is chemically processed. All material used in our planet is chemically processed. Question to ask is it sustainable? And I'll just give you two examples of this. What you see on your right is that carbon dioxide concentration on our planet in the atmosphere. Carbon dioxide concentration in the atmosphere is at an all-time high of 415 part per million. What is so holy about 415 part per million? As you know, that it has been projected that when the 450 ppm threshold of carbon dioxide in the atmosphere is crossed, we are very much on way to having 1.5 temperature rise by the end of the century. And of course, you all know this is not the time to discuss those, that it will have catastrophic consequences. You also know that recently the climate scientists have predicted that 1.5 degree temperature rise may happen much sooner than end of the century. In fact, during the lifetime of many of you. Why is it important? 415 ppm carbon dioxide concentration increase in the environment, because for last, you will see in this graphic, last 800,000 years, the concentration of carbon dioxide you can see has remained within a narrow band, as this graphic shows. But last 150 years, and you can see, for example, this is steep rise in last 150 times, 150 years of carbon dioxide concentration, leading to global warming. The other challenge you will see in the two graphics on the left-hand side, and I will have something more to talk about it, is the rapid depletion of lithium. You know, it is now very well known that by end of this century, there will be no lithium available for mining. No lithium will be available for mining anywhere in the world. And you please understand the importance of this statement by the fact that I don't think in the audience there is any pocket which does not contain a lithium ion battery. Every pocket has a lithium ion battery. Very soon, 8 billion people will have lithium ion battery in their pocket. Where will we find this lithium? This is also true, by the way, and you will see this in my top graphic, that by end of next century, there will be no rare earths available for extraction. And you know, today, both in a geopolitical sense and also in the utility sense, that rare earths are important for electronics, including communications, including miniaturization, and so on and so forth. So you can see this is the kind of challenge that we feel. You know, 3 years back, we all celebrated 150th year of the discovery of the periodic table. I just want to show you a familiar periodic table, which has now become very commonplace. And in this colorful periodic table, you will see that there are red elements which will disappear in next 100 years. You can see that about 12 elements will disappear, and there are many others which are under threat. I think this is a familiar periodic table, so I will not dwell upon this. But what is the message that you get from this? And every chemist who understands this should reflect on what I am going to say. First, chemical elements are not replaceable. You all know where did the chemical elements came from. You say a metal catalyzed reaction. You talk about catalysts for the production of ammonia and so on. Where did these elements came from? These elements came from a single event which happened 13 billion years ago, the so-called Big Bang. We cannot produce elements. They are not replaceable, except we do make some elements through nuclear reactions, but they are in tiny microscopic quantities, and many of them have very short half-life as well. So please remember, when you use any elemental resource, chemists understand and therefore must be very thoughtful and circumspect. Okay, so the message is every chemist should be an steward for elemental resources. So element stewardship does not belong to common citizens, does not belong to politicians alone or policymakers. Element stewardship is, in my view, a sacrosanct duty of every chemist. And this will ensure that our planet has what I like to call as material sustainability. So, in fact, we should all strive for element circularity because they're irreplaceable. So they should remain with us and they should remain in a utilizable form. And of course, that's a big challenge for chemists. That's why I am highlighting this. Okay, now I'll switch gears, as you can see at the top left of my slide. There have been two recent wake-up calls for humanity. And of course, chemists are also human, I suppose. And therefore, it is also a wake-up call for all scientists and human beings. What are these two wake-up calls? Israeli scientists showed in a paper to which you can see the reference, and those who are interested can read. By the way, everything that I'm going to talk about is referenced, and therefore there are relevant references. Those of you who want to get more clarity, are excited, or want to think about it, go to the original reference. But what they found through a modeling study, this is not experimental study, this is from a modeling study which is quite well validated. They said global human-made mass or anthropogenic mass exceeds all living biomass on the planet. And I just now said that all mass or all material on our planet is produced chemically, but regrettably by many times by inefficient and unsustainable chemical processing. But just imagine that we produce more mass on this planet than nature produces through human activity. That is what anthropogenic activity or anthropogenic mass means. And just imagine who we are on the planet. We as humans, 8 billion of us, only account for 0.01% of the global biomass. But this tiny minority on the planet, 0.01% of humans, produce as much mass on the planet as nature produces. So it's a thinking point. Think of a different dimension. The second finding which was reported was a very recent finding reports that safe operating space of the planetary boundary of novel entities has already been exceeded. So what I am going to tell you is first try to understand what this planetary boundary is. I will take half a minute to explain to you that. But the important thing is, in a way, there is no place available on the planet for new chemical entities. Doesn't mean that we chemists will be out of job or there is no possibility of developing new chemical entities or new materials. But the fact is that we should recognize that there is no space So don't get nervous. There is still room for those who love compound making. I've been doing all my life. Many others do it. We can do it, but we cannot do it in the business as usual mode. That is the message. We have to be circumspect when you make a compound. You have to ask some questions. Why are you making, and so on and so forth. Chemistry World, the RFC news magazine, ran an editorial earlier this year after this paper appeared. And you can see why it is so important. They said majority of top chemicals in market deemed unsustainable. That's what this study says. That we cannot have all the chemical entities which are available to us for long in a sustainable manner. So first, let me tell you then at what is this planetary boundary. I'm just exposing you. There is no time to explain all these things because, as I told you, I'm taking you for a grand safari of the chemistry world, which also includes everything in our world. So the important thing is that scientists have identified, mostly climate scientists and environmental scientists, that there are 9 boundaries which define the space available to humanity on the planet. And in 4 of them, we are already at what is called as tipping points. That means we have reached our end. And therefore, there is no more space to operate on those boundary lines. Okay. And obviously, therefore, I'm asking a question, are we staring at a man-made crisis? If we have problem with the chemical entities, yes, it is very much man-made crisis. And that's why importance of chemistry for the sustainability of people, for the sustainability of planet. And that's why you see why I have given that title to my presentation. Okay. We have, if you want to know more about it, we wrote an essay, a perspective article in Chemical Science. We were invited to write this about, and it appeared, I think, last month or in November or October. The title tells you all, and that's the message I want to convey to you. The title is Chemistry Must Respond to the Crisis of Transgression of Planetary Boundaries. Doesn't mean we stop doing chemistry, but we must respond. And if you read this article, you will know that we have defined a pathway in which you can still operate in the safe operating space, which is available to the chemist. And I've used here some words. It is just to sensitize you, to enhance your vocabulary. What is needed from chemistry? What is needed from chemistry is more resilience. What is needed from chemistry is more mitigation. You have all heard, I'm sure, that the economy and production has to be decarbonized. Chemistry has to work on decarbonization and, of course, eventually for sustainability. If you want to know more about resilience, earlier this year, we wrote an article which has appeared. You can see the reference here. The title only is shown here, A Shared Future. Chemistry's engagement is essential for resilience of people and planet. To give you some more familiar example, what I'll say for your understanding, and I'm sure everybody would understand this, that resilience is to sustainability what immunity has been for COVID. You know, during COVID, everybody was talking about immunity. Take vitamin C, take zinc, eat this herb, eat that nutritive preparation, because it will give you immunity. This is for individual. How nature gets immunity. Immunity for nature, resilience provides and stabilizes the planetary systems. And chemistry has something great to contribute towards resilience. You know, I want, as practitioners of chemistry, I want you to feel proud that you have an opportunity to practice chemistry, because chemistry changed the world and chemistry will change the world in future much more profoundly than it has done in the past. And that's why I told you, you sit in a workshop in 22nd century, you will see you will only be talking about some of the topics that I am mentioning to you. So I'm only a century in advance amplifying your vocabulary for participating in the workshop in 2022. Okay. Now, let me talk again, shift gears, and let me talk something about sustainability. I'm not going to give you a lecture on sustainability, which I do sometimes, but the fact is that there were early warnings about sustainability, but you might have seen that only in last 20 years, the word sustainability has become more popular and we are waking up to this idea of sustainability. So very quickly, I will not go into the history except to say that actually it was a lover of chemistry, but not a chemist, but an archaeologist who gave the world, who alerted the world against the possibility of unsustainable world. His name was Buckminster Fuller. You also know that Fullerene name came from Fuller. He was an architect. But like all chemists, not all chemists, some chemists, very imaginative person. So as an architect, he wrote a book conceived of the C60 structure and alerted the world. And look at the title. This is what future people who peep into the future do. He wrote a book, Operating Manual for a Spaceship Earth. Earth is like a spaceship. You cannot leave it unnavigated. You need to navigate it. And he prescribed that. And there are many other people. I will not bother you. It's too long. In our country, the father of our nation, Mahatma Gandhi, in around 1930s, alerted us. He did not use the word sustainability, but alerted about the possibility that we might be running out of resources. He's put it very simply, typical Gandhian style. The world has enough for everyone's need, but not enough for everyone's greed. Okay, it is basically also a funda of sustainability. And of course, you all know that in 2015, United Nations overwhelmingly proposed what are called United Nations Sustainable Development Goals, 2015 to 30. There are 17 goals. Six of these goals have direct relationship with chemical sciences. And you will see we have written a lot about this, and you will see some references here. But these, remember, that achievement of sustainability development goals by 2030 will require strong input from chemical sciences. And I will simply show you some baby steps which have been taken. For example, European Union has started a program called Horizon Europe Research Program, which aims at converting 100 major cities in Europe which will have carbon neutrality. Why carbon neutrality? I told you carbon dioxide concentration is directly related to global warming. Okay, 1.5 degrees. How can you reduce it? By reducing the carbon dioxide emissions on the planet. Very recently, this year itself, United Nations also has proposed a legally binding agreement to address the issue of plastic pollution. You don't realize what havoc plastic is playing. We all go with carry our bags and so on, but plastic is playing havoc. And it's a very ambitious, very appropriate mission that United Nations has launched to end plastic pollution. That is fine. How will it happen? Can anything ever happen in this direction without deep involvement of chemistry? We may call them as polymer chemists, but it's basically chemistry. And why only polymer chemists? Every chemist can work in this area. Okay. I must say a word about our country is responding very positively, proactively, I would say, to these opportunities. For example, India is fully committed on the way to meeting sustainability development goals by 2030. Many of you might have read it, but perhaps may not have sunk in everybody's mind that last year in November, India made a really, you may call it audacious announcement. What it said was India will become net zero by 2070. India will become net 20 by 2070. And Prime Minister has repeated this on many occasions. You understand what net zero means? Net zero means these greenhouse gas emissions that we produce will be balanced by those which are absorbed. So we'll become carbon neutral. Basically, that's what it means by 2070. A very ambitious goal. And this has been reiterated last month at the COP27 meeting. Again, India represented very well there, and they announced that we will become carbon neutral by 2070. Why I am talking about you all this in a chemistry workshop? I am talking this because it is once in a century opportunity for chemistry and chemists in India. And you are all young guys. Such an opportunity will never come again. How to work towards making sure that India becomes carbon neutral. I hope you know that carbon is an element. All elements belong, of course, to humanity, but chemists always have interest in all the elements. How do we become carbon neutral? Okay. So very quickly to say, there are new opportunities, challenges, and promises to keep. And to use a familiar saying, chemistry can. So very quickly, again, I'm running out of time, so I will not have that much time, but I'm raising the question, how must chemistry change, readapt, and reinvent? It will not have automatically. It will not happen in business as usual mode. Chemistry must change, readapt, and reinvent. I have my wish list of some audacious suggestions, but I'm not going to read them out. For example, I like to think that almost all chemical transformation reactions should not be reagent based. So can you think of non-reagent based chemical transformations and also production? For example, can you say chemistry becomes solventless? You don't need solvent for doing chemistry. It is possible. It has to be this way in the next 50 years or 40 years. Can chemistry be made wasteless and implemented with full circularity? You do a chemical reaction, no workup that you are used to pour it into water, extract with solvent and so on. That's not the way in future it is going to be. And therefore, new thinking has to be brought in. You can see we have written about it in a paper a few years ago. Okay, so what is the way forward? One of the ways forward is that we should transit from green chemistry to circular chemistry. You know, green chemistry became very popular and it was very well practiced, I would say. Many people got their grants because the word green chemistry figured in the title of their research project. Many papers got accepted because green chemistry figured in the title of the paper and so on. But it served a purpose. But the principle of green chemistry itself has some flaws, because what was happening in the past is what you see here. Take, make, use, dispose, pollute. Take, make, use, dispose, pollute. This is not going to be the way forward. What is going to be the way forward is circular chemistry. And the bedrock of circular chemistry is make, use, reuse, remake, recycle, make, use, reuse, remake, recycle. Make it cyclic process. Nothing to throw away, as I told you in this process. And of course, you can see here that this has make, remake connectivity I have shown by arrow. Use, reuse is a connectivity. I don't have to elaborate. You can see why it should be sustainable, because there is no exit point in this. Everything is interconnected. This is how chemistry will be practiced, but it will not happen automatically. We will need strategic and conceptual shift. For example, many of us are used to, again, using the term atom economy. There is very little room left for atom economy now. Now you should use atom circulation, so that this atom is available in perpetuity, in new roles, in new dimensions. And that's what the approach should be. But one will also have to undergo a major conceptual shift. You know, when people design molecules, you talk a word very familiar, at least to practitioners of organic chemistry, is retrosynthesis. Retrosynthesis is no longer important. What is important is that the design principle of making a chemical should have restorative and regenerative principles. Restorative and regenerative principles. And of course, I also put should be mindful of resource efficiency, utility, value addition, etc. Okay. All of you know there are 12 principles of green chemistry. There are also 12 principles of circular chemistry. I'm not going to read them out. There is no time. But in the first highlighted bullet that I have, you will see maximize atom circulation, not maximize atom economy. Maximize atom circulation. Of course, when you do this, atom economy is built into this. And the last point about this quest for sustainability I want to make is, and as a chemist, I will urge you, never use the word waste. Waste simply does not exist. Chemical matter only changes form. So waste is a misplaced resource. It's not waste. Waste is a misplaced resource at a wrong place at a wrong time. That's the mental thought you should now imbibe. Forget about waste. And I like to, there's many ways we can put cradle to cradle, smart chemical design, not cradle to death or cradle to whatever it is. So, and jettison, throw away myth. You know, people talk even in our usual conversation. You know, you buy potato chips, you eat them and say, throw away the packet. Please ask yourself, ask all your colleagues, where is this place away? Can anybody tell me? I'll give a individual prize of 10,000 rupees if somebody can tell me where is this place called away. Take it from me. I'm making a public statement. Okay. So time to reflect. I have raised many issues. Take half a minute to reflect upon what I have said. So chemistry's main pivotal role in path to sustainability in terms of topics is energy and environment, sustainable agriculture, advanced materials, and human health. I have given some topics here, but I will not have any time to discuss this, but keep these bullets in your mind. What should be the approaches for this sustainability? And that's again, I will repeat what I might have indicated. Chemistry has to work towards resilience, adaptation, and security and securing planetary boundaries. That should be the approach. And then you use the chemistry tools to deliver on these approaches. Okay, I'll give you 2 or 3 chemistry examples, how chemistry can help, and share with you contextual chemistry challenges. First is towards ambient ammonia synthesis. Synthesis at room temperature or near room temperature and normal pressure conditions. Okay. Why I'm saying this? Because ammonia is also, other than its role in manufacturing fertilizers, ammonia is now also touted, as you know very well, as a safer hydrogen storage molecule for storing energy, hydrogen, and for carrier of energy. Hydrogen is difficult to transport. Ammonia is easier to transport. It has been done for last 50 years, 70 years. And so you have a hydrogen storage system in ammonia and also as an energy carrier. So and today the world needs a sustainable and clean source of hydrogen. So ammonia is a good substitute or a surrogate for hydrogen. Just remember, 96% of hydrogen today comes, which is used in the ammonia synthesis, from fossil fuels. And ammonia production involves co-production of high levels of carbon dioxide. So it is not a sustainable process. And I will show you something about this. I will not go into all the details, but I will tell you this. Single molecule, please look at it. Ammonia production requires almost 2% of global energy. Ammonia production requires 2% of global energy. And you can see here how much of carbon dioxide is co-produced. 500 million tons of carbon dioxide, which is also 2% of the global carbon dioxide production comes from single molecule. That's why I said this planetary connection of a molecule. One molecule accounts for 2% of global energy and 2%, nearly 2% of global carbon dioxide production. Okay, so what should be one of the goals? And of course, a lot of work is going on in last 5 to 10 years in this area, is towards a room temperature ammonia synthesis. You have all studied the Haber process. Almost 100 years ago, it was invented. You know the conditions. Many of you must have remembered it by heart. 450 to 600 degrees, high pressure, iron catalyst, and so on and so forth. 100 years later, in 2020, a group of very eminent chemists and material scientists say it is possible to make ammonia at 50 degrees at 1 to 2 at 10 atmospheric pressure using this special ruthenium CAFH catalyst. So you can see we are approaching where ammonia can be made at room temperature with very less consumption of energy and so on and so forth. Okay. I will not go into the details of this. The advances in catalysis, some of you who work will recognize that single atom catalysis is poised to make revolutionary changes in catalysis. And I show you here a diagram or a photo from the review in Catalysis Today, which appeared a couple of years ago, which shows what kind of approaches are going to do this. I saw in the title of your workshop, you use electrochemistry for sustainability. Well, this is very handy because electroreduction of nitrogen can be done at 100% efficiency. And electrochemical reduction of nitrogen can give ammonia. Of course, you have to go through lithium nitride. It's not a straightforward process, but that's the direction. And very recently, people have also said that nitrates can be directly electrochemically reduced to ammonia. So this is the way forward. And that's why I see that your workshop is very relevant. How you can do a non-polluting room temperature, sustainable reduction of nitrogen to ammonia. That's the way the future is going to be. I will not spend time. I'm sure you are all very familiar with the colors of hydrogen, great demand for green hydrogen. The only way, or one of the major ways, perhaps sustainable way, you can access green hydrogen is through photoelectrolysis of water. Photoelectrolysis, I will correct, through solar electrolysis of water. You can get hydrogen. And there are many, many approaches here. It's a hot topic of very competitive nature, but this is something you should be exposed. I'm sure you will be exposed during this thing. Okay, health and well-being, I will skip. I'll just take a minute for contemplation because I'm running out of time. This is for the revisiting the teaching learning processes in chemistry. And I will only focus on one. Rebalancing content and context. You are the students in one of our premier institution, IITs. You always revise your course content. Some of our institutions are very good in revising their content, making it up to date and all this. What we don't do is that we don't change significantly the context. There is a mismatch between the content and the context. And I've been pleading with my fellow chemists that please rebalance content and context, because eventually it is the context which will determine the efficacy and utility of the content. Okay, since all are good researchers, you look at the content, but we seldom capture the context. So my request particularly to the faculty and teachers present here is please rebalance content with context. Okay, there are many other things, but I will not go into this. I will also say it is very important for all chemists and learners of chemistry to have cultural competence. And we wrote a guest editorial in Angawande a few years ago. Actually, the key to get the best out of learners is by empower them through cultural competence. This cultural competence, when I talk and scientists talk, has a very different dimension. So don't confuse it with other culture things that you hear. Okay, this is a different kind of competence which is there. I also have a word about research integrity, which is also, in my opinion, is a part of culture. Integrity is part of culture, not of regulations. not of notice boards and circulars. It is part of culture. And therefore, it is important that this culture should be inculcated. Most important thing, I'd like to make a strong pitch for humility. All scientists should be humble. All chemists should be humble. And humility is the guide towards becoming a humble person. And I have a very famous example of Marie Curie. You know, she won Nobel Prize 2 times, as you know, but you probably do not recognize that what Einstein said about her. And it is important to read that. One of the most celebrated scientists for last 1 century, Einstein said Marie Curie was probably the only person who was not corrupted by the fame that she had won. You know, to be not corrupted by fame, you have to be humble. And at the bottom, you see Daniel Sackman, the 2011 winner of the Nobel Prize for his epoch-making discovery of quasi-crystals. He put it very simply. A good scientist is a humble scientist. And when I see the science, the way it is practiced, the scientists, the way they behave, I will also add to this. A good scientist and chemist is one who is objective and follows the method of science. You may be a scientist, but very few scientists follow the method of science. So I will say that to be humble, following humility is important, but to be an objective and fairness are cherished values of science, and scientists should practice that. Well, I have given you examples from overseas. You don't have to go look that far. In our own country, we have a shining example to emulate, and that is the father of chemistry and chemical industry in India, Acharya P.C. Ray. He is one who could integrate ideas with idealism. Please think about it. How do you match ideas with idealism? And he has left us a venerable legacy of humility and patriotism. I would very strongly urge we should all decide to follow, at least in this matter, his footsteps. Okay, I think now you can ask me a question, and I'm answering that question. Why have I taken you through this unusual journey? I'm sure many of you are perhaps regretting that you have attended a chemistry workshop lecture which didn't talk much about chemistry, altu-paltu things he has been talking about. I will try to answer that question. We are what we are due to 4 billion years of evolutionary revolution. You know, we're part of an evolutionary process. And for last 4 billion years, this evolutionary revolution has been taking place. And that's why we are Homo sapiens, with all these prosperity numbers that I shared with you in the beginning. Time now has to come. The time now has come to make a big shift in this, particularly because sustainability challenges now mandate revolution in evolution. We can't evolve the way we were evolving. We must have a revolution now in evolution. Okay? So think about it. I will not elaborate. These are complex issues, but I just want to leave you with some thought. And always be mindful that we as humans must adapt to survive and coexist. Don't change the environment. Change yourself. Adapt to the changes in evolution which are taking place. And always remember that as humans, as Homo sapiens, we are one among the planet's gigantic diversified forms of life. I told you, we only account for 0.01% of the weight of our planet. That's all, predominantly, overwhelmingly something else, and we should be mindful of that. So I will leave you with this message. Chemistry, of course, I have tried to convince you, we live in the molecular world, but it helps and enables us to face planetary challenges. And then I would say, resist the rearranging the deck chairs on the Titanic affliction. Many of you may not know what is Titanic affliction. I'm sure you all know the Titanic movie you have heard about, but there is a Titanic affliction. I'll not dwell upon it. Please go and read what is this titanic affliction. And I'm only saying is that develop some, or at least be resistant to this titanic affliction. And lastly, learn to look beyond one's methodology, process, technique, reaction, catalyst, algorithm, spectroscopy. These are all tools, tiny tools in our hands. But our vision should not be defined by the tools that we use. The vision should be beyond, and that's the purpose of my mentioning this. Now, certainly the last slide, I'm trying to project what will be new additions when you look at the periodic table in the 22nd century. Chemistry must adopt new symbols. And in my view, these should serve as an addendum to the periodic table. And you will see here I have symbols which don't exist in the periodic table, will never exist in the periodic table. But in my view, they are as important symbols of chemistry as any element present in the periodic table. What do they stand for? SU for sustainability, ID for interdisciplinarity, ES for elemental stewardship, and SC for societal connect. There can be no progress in chemistry. The chemistry cannot serve the humanity unless we also concurrently develop societal connect and sensitize people about chemistry. Now you will know why I have spent an hour, close to an hour, talking to you something which to many of you, I am sure, both teachers and students alike, might look somewhat irrelevant. Why is he talking about all this? But as I mentioned at the beginning, I will end with this. Perhaps you will find this topic very relevant in the 22nd century, those of you who will be around there. Okay, thank you for your kind attention. As usual, I exceeded my time by a few minutes, which I always do, but I have earned enough notoriety to live up to that notorious attribute. Thank you.
Profuse thanks to Professor Mehta. I hope you will be able to take one or two questions.
Well, if I can answer, because all questions will be very difficult.
Okay.
It will not be chemistry questions, I'm sure.
Let us see.
Yeah.
You all agree with me that Professor Mehta has taken us to new dimensions. Okay. Those of us who are from Kanpur know the brilliance of teaching of Professor Mehta as well as in other places. And you have just seen a symbol of that. I wish Professor Mehta would have walked around this podium and given you this lecture. We didn't have that privilege, but we had the privilege of listening to him along with the slides. So this is time for me to invite questions. We have made two arrangements. If you can write it down and pass it on to the volunteers, or you can just raise your hand. Please, I would invite the students because this is one in which Professor Mehta wanted to really strike a chord with your heart. Please. Any questions? From the front side, back side, any side? Yeah. It would be really nice if some questions come up because he has really given us a lot of thoughts to think, right? Yeah. Please.
Yeah, Professor Mehta, this is BK Patel from IIT Guwahati. It is always inspired listening to your lecture.
Thank you.
I must say, I take several of your articles. I have prepared 2 lecture series in my BTech classes, and I cover it in the form of circular chemistry actually. So I'm really grateful to the material they have put in your thought process, and I'll take few more material from your today's lecture, and that really inspire our BTech student actually. So thank you so much for giving such a beautiful articles time to time, and we hope you contribute many more articles.
Thank you. Very kind of you.
Yeah. Thank you.
I only want to repeat again, which was in my first slide. Chemistry needs repurposing.
True. Absolutely true.
What Professor Bishnu Patel had said, that's the way. If we all join hands to see that we have to give new direction to chemistry. This is the way to do it. As he mentioned, yeah.
Yeah. Indeed, sir, I have also told you earlier that I keep reading the system thinking that you kept on telling us. So that is a big thinking. And only people like you and others who are in this nature papers, etc., can teach us what is systems thinking. It will take us quite some time to put that thinking into our practice in the classes. I hope we'll be able to do it. Thank you very much.
I just want to briefly respond to this. As far as systems thinking is concerned, engineers have been practicing this for almost 30 years because they have to deal with a lot of moving parts. So they deal with systems thinking. Biologists have adopted systems thinking in the last 20 years. And systems biology has emerged as a separate branch altogether in life sciences. But chemists have been very slow. And that is one of the problems with chemistry, because chemistry, I tried to share with you, has many dimensions and therefore has many moving parts. But chemists are notorious for only looking at one part, not many moving parts. If you only look at one part, when there are many moving parts, you are missing a lot. It will never deliver the kind of things it is capable of delivering. And that's why systems thinking is very important. People should consider all the moving parts. And that's what engineers do when they do systems design.
Right. I'm sure some book from your side will come up on systems chemistry.
On?
Is there any book coming on system chemistry?
Well, we keep on writing. I mean, I do
I follow all the articles which comes up in Angu.
All of us have to keep the pot boiling. I also do research. I also keep on publishing this reaction, that reagent is. But you also reach in life a position where what you do is less important. What you enable others to think and do is far more important. And our writing is our little effort. We are part of an international group. 4 of us. We are now expanding. We have become almost 6 now, who keep on writing on different arenas, because there are many people who want to join us. So, we are expanding because I suppose with more people joining in, our voice will carry more weight.
Absolutely. Yeah. So, ladies and gentlemen, and my dear students, on behalf of each one of you and each one of your heart, let me join in extending our heartfelt thanks to Professor Mehta for giving this time. Okay, he's getting a time from him himself. And I would be requesting you to stand up and give him a big ovation. Thank you, Professor Mehta.
This is not necessary. Please don't make me feel embarrassed. Very kind of you. Very grateful to all of you. God bless you all.
We respect you as our teacher. So nothing less than we can do as a student, but to stand before our teacher. Thank you very much.
Thank you very much. Thank you. Okay, bye. Have a good workshop.
Thank you very much.
Best.
Yeah. या कनेक्ट हो गया सर का कनेक्ट कर दो. हाँ, ये प्रोफेसर पैटल. Okay, right? My dear students, after a very big lecture like Professor Mehta, you feel like you are immersed in a kind of, hallucination kind of a thing. But I have to come out of the hallucination and take my duty to introduce before you another son of the soil. Okay, he is none other than Professor Bhishma Kumar Patel. Professor Bhishma Kumar Patel and I both are from one institute, that is Kanpur. I keep telling about Kanpur and irritate all other IITians, but they must be doing the same thing too for their group. Let me introduce Professor Patel because he's a prolific scientist. Okay, and he has his education because of the students only. I'm reading this. All senior knowledge in Sambalpur University, BSc. Okay, was in Sambalpur he did his masters in 1987, and in both the places he was a gold medalist. And he then joined and in PhD in 1994. I finished in 1987, so you can understand the difference of age between us. After that, he had been to several places and finally joined the IIT Guwahati. And he has been there since the inception of IIT Guwahati. At a time when IIT Guwahati started from a college, and when they have to cross the Brahma, that river, that is the time. Since that time, he was there and had been very dedicated to that department. This is one thing. I have seen in IIT Bhubaneswar, some faculty came and they left for their own green pastures. But Professor Patel has made his green pasture there itself. That is the hallmark of a sincere chemist and a good, humble person. Obviously, a person like Professor Patel would be awarded and recognized by the fellow peers. So he is fellow of the two academies, Indian Academy of Science and fellow of National Academy of Science, and a range of awards. Okay, the most recent one, perhaps if I can read, at the Postal Chemical Research Society Award, Bronze Medal of Chemical Research Society, Eli Lilly Outstanding Award, and your T.S. Bhakuni Award. This is a very important one in organic chemistry. Okay, and his students are all around the globe. That I can definitely tell you because we are in close touch. So he's produced more than nearly 200 publications, along with patents, chapters, huge number of impact factor, things like that. Okay. And today, I recently I've heard Bhishma, I keep hearing him now and then. So I recently heard him as well. Today he's picked up a very interesting topic before you, and this you will definitely enjoy. Those of you who are in any synthesis, not only in organic or organic. Nitrile triggered access of N heterocycles. So this is a special invited lecture, and I don't want to stand between you and me. It's my great pleasure to invite Bhishma to this dance. Thank you, Professor.
Yeah, okay.
With the greatness of the Sujit, I know him for last 27, 28 years actually. He's always a very nice person. And if person is good, always he see goods in other thing only. Okay, so that is the greatness about him. So thank you so much, Sujita, for your kind words of introduction. It is echoing a little bit. Okay, yeah, okay. So after hearing a mesmerizing lecture from Professor Mehta, it is a very, very difficult task. And I must thank Professor Sarvesh for inviting me. And it is a homecoming for me. I am always really grateful to him. And particularly choosing the kind of topics which have sustainability and which Professor Mehta has elaborated in details. But I like to add few more things. Recently, a lot of political issues are there. Okay, you must be following this thing because some of the opposition parties doing why not stop the business with the China. Okay, so now there is a Dhoklam issue is there. Now the Tawang issue is there. Okay, so what is the consequence? As a opposition party, you can always say that you can stop the business with the China, but where we stand this thing, 80% of our chemicals are imported from this thing. All the API drugs are imported from China. The way they stop will not survive more than 1 month. Okay, so we need to do business with the China. If you don't want to do the business with the China, then you have to find our own ways. And government is proactively working in this area. I'll tell you, I'm one of the task force committee members. I must share this my experience. Now the SCRB has constituted 5 nodal centers in India. One is located in the Tirupati, Chennai region, one in the Hyderabad region, one in the Pune, one in the Calcutta, Guwahati region, one in the Dehradun, Himachal region. Unfortunately, you don't find any in the central part of India, not covering all these things. And this job of this nodal center is to make API drug with a competitive price to the China. Because now we are importing a drugs of say 1 kg 120 rupees. We have to manufacture this thing. So we have to need to develop our synthetic strategy so that we can sell it at a competitive price. You don't need to import from the China. Okay. And that is the thing how we have to repurpose the chemistry. Synthetic steps are known. You have to modify the steps. You have to modify the organic chemistry, modify the strategy, develop the reagent, develop the condition, and come up with the alternative so that we can be self-sustained. Okay, and that's what the one of the approaches to the electrochemistry and different kind of photochemistry kinds are there. So I would request the colleagues from this region particularly to come up with this. So I'm in the one of the committee member in the SCRB. So we'll definitely look for the 6th nodal center. Why not 5? Why not they can have 6th one? Like here, all the 3 national institutes are situated. Like IISR Berhampur is there, IIT Bhubaneswar is there, NISR is there right next door. So there can be another nodal center here as well. Okay. So I request the colleague you can discuss this separately. So today I'll be talking about nitrile trigger access to the end heterocyclics. So my group has been working in the heterocyclic chemistry for quite some time. We work on the various aspects of this thing. Not changing, can you just see it? What is wrong? Slide changer, just see. Yeah. So N heterocycles, they are present in the biologically active compounds. They are ubiquitous in the many of the natural products. Core skeleton in the most of the market drug, about 80% of drugs contain the heterocyclic skeleton in some form or other, and they found huge application in the material sciences. So our group has been working in the N heterocyclic synthesis using transition metals, particularly alkane insertion, dioxide annulation, and cascade addition cyclation. Lately, during the corona time, last 3-4 years back, we have just found say how to do the reaction in a sustainable way. So we are aiming to trigger the nitrile functionality in the cascade cyclations to construct heterocyclic moiety. Again, there is something in the connect. Am I from distance not reaching this thing? Or battery is down? Yeah, okay. Something is not getting. Yeah, okay. In the meantime, I'll see. So nitrile is a very important functionality. If you can look at the student perspective, this is a pi coordination site. It has the electrophilic C site, nucleophilic N site, and this nitrile can be hydrolyzed completely to a carboxylic acid, partially to the amide. Okay, you can do a metal catalyzed addition with the boronic acid particularly, and you can convert to this kind of amines. It can convert to the keto. You can completely reduce to the amine and selectively reduce to the aldehyde. So it's a very important functionality so far in the perspective of an organic chemist. So our group has contributed 2 review articles during lockdown time. So one is the dealing on the metal catalysis reaction of organic nitriles and boronic acid to access diverse functionality. So this has appeared this thing. So these are by Amitabh and Hirendranath and Tipu Alam. They have contributed this article. Another recent article in the Chemistry Essence Journal, Renaissance of the Organic Nitrile in the Organic Synthesis. Those who are interested, you can go through these two articles. If there is something, can you change the maybe setup? Yeah, okay. So since I am new to the electrochemistry, so since the theme of that today's topics is the electrochemistry, I have done little bit of one publication in the electrochemistry, so I must start this thing before I'll start the nitrile functionality. So our group has been working lately on the electrochemistry. One of my students, we have got few other interesting results as well, but students did not want to share this thing, so I want to share the published result. What we have done in the electrochemical means we have make a amide bond formation, so which is a metal free and exogenous. And then it is a concomitant formation of CN bond, and this hydrogen and nitrogen coming as the byproduct. So one can collect it and they can make it a useful product rather. Okay, it has a broad substrate scope, and we could accomplish the synthesis of benzafibrate. This is a marketed lipid lowering drug. So we could accomplish the synthesis of this molecule using this one. If you look at the amidic bond containing substance, there are thousands, millions of the molecules, but some of the molecules, important molecules, are the benzafibrate. Okay. And this molecule has the anti-cancer, all possesses the various kind of amidic bond. Okay, the penicillin is the amidic bond. Then you have the chloramphenicol. This antibiotics is the amidic bond. So there are many molecules having amidic bond, and there are a lot of methods are known in the amidic bond. There is nothing great in this thing, but making in a sustainable way is the what is need of the current hours. So you can start there are some of the known method of synthesis of making this kind of thing, starting with the corresponding keto compounds, or you can do a carbon monoxide insertion with the having a different kind of functionality, and you can construct the amidic bond. And there are some other electrochemical, other oxidative approaches also known, where the people are using the azides and then converting the corresponding acyl radicals. On the alternatively, under metal catalytic conditions, you can form also nitrogen. You can undergo coupling reaction kind of thing. So what we did in our present case, that you took the azide where you generate the acyl radical, and on electrochemical process, another process, you develop nitrogen center radical and couple the acyl radical and nitrogen radical, you made the amidic bond by a cross coupling process. So this reaction requires the optimization, of course, that you have to play around the various kind of parameters. So what is the parameters used? This is the supporting electrolyte, tetrabutyl ammonium. This is perhaps one of the drawbacks of the electrochemical method, because you require a specific electrolyte. Okay, but this can be recycled. That is the advantage of this thing. And then it is required a combination of dichloroethane and HFIP. HFIP is the solvent, is very much essential for interacting with the solvent for enhancing the oxidation of this process. Okay, so this is the optimized condition, most optimized condition. I'm not going through the other this one. So using this process, what we did, these are the blue ones are coming from the corresponding azides, and the green ones are coming from the corresponding amines. Most of these things are secondary amines. So you can see it works with the various kind of secondary amines. Secondary amines having the various kind of substituents present at the various position, they give the corresponding amidic product. Okay, so similarly in the N substituted one, various kind of substituent present at the N protection, they also work. 5-member ring, 6-member ring, and 7-member ring, it can go to higher member ring. Aliphatic amines, they work beautifully for this one. Even the benzylic amine, they work nicely. Heterocyclic amines. This is interesting aspect of this thing. If you have the aniline versus benzyl amine, in this case, only benzyl amine is getting selectively coupled and not the aniline part. So one can achieve a selective amidic bond formation in this case. You can see there are many other examples are shown over here. One can go to the peptide system, the peptide like particularly morphol, it is your prolines. You can make the corresponding prolines amide. We tried to also make some of the dipeptides by this process. And this is also another phenylalanine. You can make the N-protected phenylalanine. Various kind of amino acid derivatives are there. But some of the substrate were found to be unsuccessful. As we have seen here, this one aniline is not working. So this aniline doesn't work here. This kind of heterocyclic system does not work here. But we have worked with this system, this tetrazole system, successfully under nitrogen center radicals. But we are surprised to find this nitrogen center radical is not forming in this case, whereas we have got many publications earlier which is going via radical mechanism. We have a clear proof that this is going via radical mechanism, but somehow under this electrochemical condition, this is not forming the nitrogen radical. There may be some other factor which we have not thoroughly investigated why it is not working. We have also worked this tetrazole system can undergo a radical coupling and you can get the N-methylation, which you have also used it for the synthesis of particular kind of drugs molecules. It can go various kind of N-alkylation and you can carry out various kind of N-arylation reaction. And we have also done the remote functionalization using the tetrazole moiety. So we are surprised to find why this nitrogen center are not reacting in this electrochemical condition. So what are the parameters we found at that point of time? That this nitrogen center radical should have a sufficient electron density. So for the tetrazole system, it has electron density of 0.22, activation energy of 32.6, it is the minimum requirement, and they are said to be sufficient stabilization. So these are the three factors needed for the to form a nitrogen center radical. Okay. So then we investigate why these other nitrogen systems are not working that time. Okay. Only this was working, but many of them were not working. But if you look at this system, this is basically this system, benzotriazole system. Triazole is very similar to the tetrazole system. Triazole system, if you look at the spin density, is very close to the 0.22. Activation energy is slightly higher. Okay, so initially it was not working for our particular reaction, but when we increase the temperature by 10 degree to overcome the activation energy, this reaction did work. So our theory was correct, and theory is correct now also, but we don't know why this system is not working in electrochemical condition. Okay. So extending the scope of this reaction, so not only work with the, now it is a variation of the azide part, these are the various kind of hydrogen parts, these are blue components, various kind of substitutions present in the aromatic ring, in the para positions. Okay, you can see these are the various kind of substitutions. Okay, and you can also make the carbazoid, you can make a various kind of carbazoid derivative efficiently using this electrochemical strategy. So then we have to prove the mechanism of this reaction that it is going by indeed a radical path in the electrochemical process. When we did the standard reactions in the presence of radical scavenger like tempo, tempo is a good radical scavenger, we got a very trace amount of the product along with the tempo trap radical. So what does this indicate? That the acyl radical is forming in this process. The acyl radical is forming, that's why we are getting a tempo radical. On the other hand, if you carry out the reactions in this thing, you can also trap the nitrogen center radical. So that means this proves that both the acyl radical and nitrogen center radicals are forming in the under electrochemical path, and then they undergo coupling reaction. So this is not going by the aldehyde intermediate, that proves this one, not going by the acid intermediate, that this is proven by from this control experiment, not going by the amidic intermediate proven the control experiment. Okay, so it is only going by the acyl radical interpath. So also we did the cyclic voltammetric measurements and the linear scanning voltammetric measurements to see both the substrate and oxidizole under this condition, and this is well fitting with their oxidation potential. Okay, so coming back to the mechanism of this reaction, it undergoes a sequence of the oxidative process at the anodes. Okay, it is losing an electron and the protons, another set of electron and the proton it is losing and forming the corresponding and double bond. And when it is losing the third one, it is forming the corresponding nitrogen center radical, and when nitrogen is coming out, it is forming the corresponding acyl radical. Okay, and this solvent is very much crucial for this electrochemical oxidation process because it interacts and this reduces the oxidation potential that we have shown from the previous CV measurements. Okay, it's formed a nitrogen center radical, and both of them gives and couple this one. Okay, so we applied this strategy to make this drugs. Okay, this is a marketed drugs which is used for the lipid lowering or cholesterol lowering drugs. It is a marketed drugs. Okay, so you applied our strategy in the gram scale reaction where you can make in the up to the 70% yields. Okay, and then we just applied this strategy. This is the first coupling stage, and this is the usual nucleophilic substitution reaction of the corresponding phenolate under a basic condition with this kind of bromo derivative, and you can get the benzofibrate in a 81% yield. So this is the electrochemical path, but I'll come back to the nitrile trigger reaction. I'll just remove the conclusion part. So this is why we're focusing on the nitrile trigger reaction. The nitrile functionality was considered to be quite inactive towards organometallic reagents. Nitriles such as acetonitrile, benzonitrile have been employed as a solvent in several organic reactions. They do not react that strongly unless you require a strongly acidic condition. A ligand of choice in certain catalysts, like there are well-marketed catalysts where they are bound with a acetonitrile solvent or benzonitrile kind of solvent. So nitrile trigger reaction offers exciting opportunity to the organic chemistry. So the three nitrile precursors that we have been working in our group are the beta ketonitrile, this is the beta ketonitriles, this is the gamma ketonitrile, and this is dicyanodiene, and all of which can be easily prepared in the laboratory. So where there are several cyano-containing drugs are marketed by and which are approved by the FDA. You can see these are the list of the cyano-containing drugs. There are plenty. I have just collected in the 2 slides, but there are at least 50 numbers of them are there. Okay, so these are also FDA approved drugs where the cyano functionality is present. This is also cyano functionality used in the fungicides. Okay, these are some of the compounds present here. So coming back to the first work of this thing, where what we did here, this dicyano compound we selectively hydrolyze in the presence of copper acetate. So this is the control of hydrolysis doesn't go to the acid stage and the amidic stage. At that amidic stage, it will cyclize to form the corresponding amidic bond here. And this amidic bond this amidic substrate having a CHNH can undergo efficient annulation in the presence of ruthenium parathymine. Okay, all these things can be carried out in a sequential step. So what are the things here? This is a one-step reaction, selective hydrolysis of the one of the cyano group, and we are forming a simultaneous CC bond, CO bond, 2 CN bond, and 2 carbon-carbon double bond form are taking place in a single process. Okay, and this is a photoluminescence, and this molecule exhibit a lot of interesting photochemical behavior, which of course I will not be presenting in this today's talk. Okay, so what is the importance of isoquinoline? If you look at the core skeleton of the compound which you synthesized previously, they are found to have a anti-leciminic behavior found in some of the natural product. They have anti-hepatitis properties, and there are many other. They have some of them have anti-malarial property, antibacterial, and so on. And these are some of the molecules. They have an interesting. They are fluorescent molecule and found application in the material sciences. How this compound have been synthesized in the past? Using the literature. They are using the various kind of starting from the cyano compound, using a dual catalytic system. We are making this compound. And you are having the already pre-existing amide and undergoing a CHNH kind of annulation reaction in the presence of cobalt-2 species, and again similar CHN annulation to form this kind of thing. So these are some of the well-known literature method. But our process, I told you, is the one-part sequential process involving the selective hydrolysis to the amide followed by the annulation stage. And the optimization condition for this reaction was for the second step rather, this is the second step or this is the overall step, okay? Both the step you can do the one part using the ruthenium parathymine, copper acetate, large excess at least 50 mole%, which is of course not very desirable, but that is the best condition that we can arrive at. And polyethylene glycol gives about 72% of the yield. So these are the various kind of substrate scope where you have done the varieties of substitution. This is the parent compound without any substitution. The R1 having a various kind of substitution like paramethyls, paramethoxy, and various kind of chloro, bromo, and nitro groups. It works reasonably good, but yields are not that great. I must admit here, the yields are not great because this is a lot of other side products are also associated with this thing. Similarly, there can be various substitutions present in this ring, and all of them are giving a yield in the range of around 50%. So you have the bicyclic systems. Both the bicyclic system, you are having a electron withdrawing group like chloro and nitro groups, and all of them are responding quite well to this protocol efficiently. Okay, these are some of the heterocyclic moieties. So in the unsymmetrical alkynes, it also works for the alkyne substituents. In the aliphatic alkynes also work, aromatic alkynes also work. Okay, and you can see the substrate variation. But in the unsymmetrical alkyne, you are getting a selectively, this one is a higher percentage and this one is the lower percentage. The product originating from the phenyl attacking of the nitrogen to the phenylic side is the higher, and that is as for the mechanism, and this is getting the lower percentage. See also this higher compound and this is lower compound. And these substrate, electron withdrawing substrate and the terminal alkynes were not successful for this annulation process steps. So coming back to the mechanistic investigation on this reaction, when you carry to find out the source of the carbonyl group, where it is originating, whether this is staying intact or it is originating from something else. So when we did the reaction in the O18 level water, what we found that this carbonyl group was completely replaced and the new oxygen were incorporated. So that means the carbonyl group is originated from the water present in the reaction medium. Okay. Similarly, we did this if there is any reversible C-Ruthana bond formation is taking place or not. So there is no ortho deuterium exchange was observed when you carried out the reaction in the presence of D2A, and we did not find any of this thing. Similarly, when you do a kinetic isotope effect of a level deuterated substrate versus undeutrated substrate, we found by KH by KD2 we found to be the 3.0. So this shows the CH bond cleavage are the rate determining step for this reaction. So based on this, we propose the following mechanism. This compound, this one of the nitrile group is selectively hydrolyzed to form the corresponding amide, undergoing a dehydrative cyclization to form the corresponding amide. Then on this undergo auto-oxidation and under oxidative condition to form the corresponding this species. And this is in the regenerating form. And then this will form a react with the corresponding active Ruthana species generated by the Ruthinum parathymine in the presence of copper acetate. That will form the corresponding Ruthana species. And then undergo CH activation at the ortho-CH activation followed by the alkyne insertion and the reductive elimination to give the corresponding heterocyclic product. Now coming back to the synthesis of this compound, so we started with the now earlier was the gamma ketonitrile, now it is beta ketonitrile. Beta ketonitrile, when you did the carry out the reaction in the presence of this one, the alkynes, in the presence of copper palladium acetate and the phenanthroline, in the presence of paratoluene sulfonic acid, we got a fused ring which consists of the furan and the pyridine ring. So furan and so we constitute the furanopyridine rings. So what you have found here, that formation of furanopyridine rings, you are observing a CH annulation reaction, and you can see the formation of CC, C double bond C, C single bond N, CN. There are so many varieties of bond formation taking place in one pot in a single step process. Okay. So but interesting thing is both the cyano groups are involved. In earlier, one of the cyano group was getting hydrolyzed and other cyano group was remaining intact. Here both the cyano group were remaining intact. And also we have demonstrated some of the useful synthetic application, post-synthetic application of this thing. So where do we find these furopyridine rings? These are found in the fumagastins 1, fumagustin 2, and there's some of the potential drugs molecule having the furopyridine ring. You can see some of the furopyridine ring having the anti-cancer activities, okay, having the CB1R inverse antagonist, okay, and there are many other application of this kind of molecules. So how people have been constructing this kind of molecule, starting with the alkynes, and they suitably place hydroxyl group or phenolic group, it will undergo a cyclization reaction to form this kind of thing. And there are, if you look at some of the other methods, so one of the pyridine ring is inbuilt and you are constructing the second furan ring. That is the thing. Okay, so you can see all are pre-formed pyridine rings. Okay, pre-formed pyridine rings are there, and there's a furan ring is constructing here. And there is another approach, is already furan is constructed, then you are building the pyridine ring over this thing. So furan is constructed, and pyridine ring is built here. Okay, so if you look at all these methods, at least one of the ring is preformed, but there are few miscellaneous strategy. But if you look at the kind of substrate they have used, in very, very difficult to design. Okay, so there where both the rings are simultaneously getting constructed, no doubt about it. But the designing this kind of substrate is a really, really difficult task. Okay, so these are the some of the rings where again here partly pyridine is constructed here, nothing is constructed here, simultaneously construct the furan and the pyridine ring. But in our strategy, we are none of these things were existing, but we are constructed both the pyridine ring and the furan ring simultaneously in one pot process. So these are some of the substrate scope that we have demonstrated, starting from the corresponding beta ketonitrile and the corresponding alkynes, alkynes. Okay, so these are some of the substrate scope having the methyl group, methoxy group, isopropyl, and fluoro, chloro, and so on. It also tolerates to the strongly electron withdrawing group because okay, and you can see hardly there is any influence of the electronic effect. This thing it works equally good for both the substrate having the electronic donating group and the electron withdrawing group. It also works with the corresponding heterocyclic system, like you have demonstrated the thiopyridine rings. But when it started with this kind of ketone, this is cyclic ketones, which was not aromatic. So no doubt we could construct the furopyridine ring, but at the simultaneous, this ring got aromatized, these things. Okay, so simultaneous the aromatization is also taking place during this process. Coming back to the scopes of the alkynes, the green ones are coming from basically derived from the various kind of alkynes. So it works with the range of the alkynes having the substituents, various kind of electron donating, electron withdrawing substituents, present in the para position, present in the meta positions, and the parachloro, metachloros, parabromo, and trifluoro, and so on. This thing. In the unsymmetrical alkyne, what you see, unsymmetrical alkynes, there is a distinct preference for this thing. Here, at least we could isolate this one as the major product. There might be a small percent of other product, right? Here, the methoxy is coming here, methyl is coming here. But here, if you go, if the electronic withdrawing, yeah, they are a little bit different, okay? But if it is a little bit similar, this thing, methyl is not a strongly electron donating and it is not a strongly electron withdrawing. You can see 1:3 ratio of this compound. Similarly, you can see 1:25 ratio of this compound. So if there is electron different, and similarly in this case of aromatic versus aliphatic alkynes, you are getting a 1:2.5 ratio of this compound. Similarly, terminal, this is also successful for the terminal alkynes. The other method are not successful for the terminal alkynes. Here also terminal alkynes works, exposing corresponding amino groups. Okay, so these are some of the terminal alkynes, but some of the strongly electron is doing alkynes like nitro and this kind of heterocyclic or strongly electron, they are not very successful in this case. So now coming back to the control experiments, when you did this reaction, both in the absence of this thing, so in the absence of palladium, it gives the corresponding product. So that means that furan ring formation, the palladium paratoluene sulfuric acid is required for the furan ring formation. But when you carry out the reaction, so either it takes place in the absence or in the presence of palladium. So that is basically the paratoluene sulfuric acid essential for the furan ring formation. But in the second case, that without the palladium, this ring formation does not take place. You can see this side, this product is not forming at all, but in the presence of palladium. So both the palladium and paratoluene sulfuric is essential for the formation of this furan and pyridine ring moiety. Okay, so now what we realize this thing, maybe this is forming initially having a amino and a cyano group. So if this is the intermediate, we did not initially we did not detect the intermediate, then we thought, can we do the same kind of annulation with a cyanoamine, ortho-cyanoamino compound, and we could get the annulation reaction. So this is the first time the NHC annulation kind of things were reported. So this is the mechanism for this reaction, undergoing a ketonization, enolation of this thing. Okay, and then in the presence of paratoluene forms, this furan ring is constructed, and this active catalysis it will get added up. This thing, a ligand is not shown here, so it forms the corresponding palladium species, alkyne insertion, cyclopalladation reaction, and then protonation takes place, and finally aromatization give to the corresponding furopyridine ring. Okay, and having made this compound now, you want to see that how it can be further utilized for the various kind of applications. So when you can carry out a further annulation reaction on this thing, it is already an annulating product. So this is now CH and NH is there. So you could achieve the annulation reaction, giving the product in 80% yield. You can also this CH, you can get a CH activation product with this kind of substrate. Okay, you can carry out the Suzuki coupling if there is some bromo group is present here. You can carry out also Heck kind of couplings, and you can carry out Sonnegasserer coupling and extend the diversity of the molecule. Now extending the cascade synthesis to the fused imidazo pyridine ring. Now what is this thing here? Again, this is the gamma ketonitriles. We use the orthoiodoaniline. So expected this will form the corresponding form the corresponding CIP base. This iodo group is exposed this thing. This is perfect for the kind of Ullmann coupling ion. So they combine both the strategy, and we could construct the fused imidazo pyridine ring in a single pot process. So beauty of this thing reaction, you are able to construct the CC, CN, C double bond N by cascade strategy. Okay. Because these kind of compounds are found to have antimalarial activity, they are known to have the antifungal activity, antiviral activity, and there are many other anti-leukemia and anti-neoplastic activity. So how do the people construct this kind of molecules? If you look at the literature, again they construct using a free-form heterocyclic alkyne moiety. Both these are the two coupling patterns having the amino halo compounds and the two iodopyridine kind of thing. Similarly, using boronic acid and that aminopyridine compound, and then here is also undergoing a CH kind of coupling reaction. And so these are some of the strategy. There is only one strategy known using amino iodide. This is the precursor we are using this thing. So but they are using a cyano compound and a alkyne. So this is very difficult to design this kind of substrate. So they have made this kind of fused heterocyclic following these two coupling patterns. In our present work, what we did, you are using the gamma ketonitriles and this orthoiodoaniline in the presence of copper. It is forming the CIP base, undergoing a intermolecular Ullmann kind of reaction, and you are getting this product in this thing. So we have demonstrated the scope of this reaction, having optimized the condition. The optimized condition was found to be the use of 50% copper acetate, and bipyridine ligands and paratoluene sulfonic acid, and giving the 76% yield of the product. Okay, so these are the various kind of substrate scope. You can have the various kind of substituent present in the any of this ring. R1 ring is these are the substrate variation. R2 ring, these are the substrate variation, and similarly this is this corresponding naphthalenic systems. substrate having the electron donating, two electron donating group, and so these cyano groups are exposed, which you can carry out the, and this bromo group you can carry out the many post-synthetic applications of the substrate. Okay, so these are the substrate scope with respect to the orthoiodoaniline. This green one is derived from the orthoiodoanilines. Okay, and these are various kind of substituents present this thing, and yields are reasonably good, but when you go to this kind of substrate having the strongly electron withdrawing group, the yields drops drastically. So we have proposed a two cyclic path, one for the Ullmann kind of coupling, one for the formation of this one. So the first step is the basically C base formation between this keto group and this amino groups. Then you form the corresponding C base, and this copper catalyst which forms activates the nitrile group, undergo intramolecular attack of this thing, then form the corresponding imine species. So this can directly participate in the Ullmann kind of coupling, but we have just shown it in a two-step process. So this is the basically typical Ullmann kind of coupling here, undergoing oxidative addition, and then it undergoing the protonation and the reductive elimination, giving this kind of product. So the third part of our work is the, again, we trigger this nitrile trigger reaction using the boronic acid. This is a photochemical condition because photochemical is more sustainable because here the catalyst loading is less. And this is the first time we have used the palladium as the photocatalyst in our group. Of course, the people have been using in this one, using white LED. So these methods, if you start with the gamma keto nitrile, you get the corresponding periodial derivative. If you start with the beta keto nitrile, you get the corresponding this 5-member nitrogen heterocyclic containing cyano functionality. So this method is photosensitizer free. A condition is reasonably mild, and the selective attack of one of the cyano group and other cyano group is not affected, and the formation of carbon-carbon single bond, carbon-nitrogen single bond, double bond, and C-triple bonds takes place in this process. Okay. And we have demonstrated a good number of examples for both the pyridine formation and the imidazole formation. So if you look at the some of the photochemical process using the palladium catalyst that people have carried out this kind of coupling, this is the kind of coupling of the iodo versus the boronic acid. Then they have carried out some of the palladium mediated reaction using the blue lights. And so these are some of the palladium catalyst coupling reaction known in the literature. And this kind of skeletons and some of the other is looking at the reactivity of boronic acid, which we have covered in the two of our recent review. We can go through these review articles that boronic acid add to the nitrile group and give a variety of the product depending how they are suitably placed. So you can construct various kind of heterocycles. Like here, if this substrate can give this kind of heterocyclics, this substrate in the this can give this kind of heterocyclics, and all starting with the boronic acid as one of the coupling partners. Okay. So in this photochemical approach, I said we get the corresponding pyridyl derivative and this corresponding 5-member nitrogen heterocycles. So these are the again substrate scope demonstrated for this one. That this is the simple substrate and without any substituents, substituents present in the R1 ring. These are the various kind of substituents in the R2 rings, and the yields are modest in most of the cases. These are some of the more substrate scope for the pyridine synthesis, and then we extend this to the variation in the boronic acid coupling part. So you can carry out a lot of various kind of boronic acid are all compatible under this condition. But however, the boronic acid possessing an aldehyde group or the aliphatic boronic acid or heterocyclic boronic acid, they are found not to be reactive under this kind of conditions. Okay, this is the formation of the 5-member ring using the beta ketone nitriles, not the gamma ketone nitriles. So we could get these products in a reasonably good yield. So these are some of the substrate scope. So mechanism of this reactions starts from the formation of the corresponding active palladium species. Okay, it is from the activated palladium species. Then this will add up to this palladium, and this will undergoing this kind of reaction, palladation reaction. Okay, and then it will undergo protonolysis and undergoing then intramolecular cyclization reaction with the inside. Either you can write in the form of amine or imine, and that's how we can construct the corresponding pyridine skeleton. So this our other reaction is the, if you can also trigger this reaction under photochemical in the presence of a thiol. So thiol can form the corresponding thioneal radical in the presence of eosin Y. In the under a basic condition of potassium carbonate and DMSO, it in the presence of two green LED, 210-watt green LED light. Okay, so you can construct the metal-free condition for the synthesis of this kind of thiofunctionalized pyrroles. You can construct the CN, CC, and CS bond simultaneously, And we have demonstrated with a good number of examples, and this is a scalable process, and all this has been well supported by the CV measurements, and this method is basically oxidant free. So if you see some of these nitrogen containing compounds are found in the anti-hyperthermic molecules, which is marketed Dr. Evostatins. Okay, they have a potential inhibitor of leukotrienes. Okay, and sornitinib is also anti-tumor drugs. Okay, so this kind of skeleton can be constructed by using this strategy. So initially we assessed that initially to carry out this work, we assessed this thing that they have a compatible oxidation potential. So if you look at the benzene thiol, this is a oxidation potential plus 2.5, and if you look at the beta ketonidyl, oxidation potential plus 0.95. So they are ideal donor acceptor complexes, so they can react this thing under the photochemical condition. With that optimization, this is the optimization condition for this reaction. So if you use this reaction in the presence of eosine, which require about 3 mole% under a nitrogen atmosphere, you can construct this one. Okay, eosine is this exactly matching with the wavelength of the blue light. This blue light, the green light, so the green light is exactly matching with the very close to the eosine wavelength, absorption of eosine wavelength. So having optimize this photochemical condition, this thiol can trigger this reaction at one of the cyano group, and you can construct the various thiofunctionalized spirals. So these are some of the substrate scope, with having a various kind of soft change present here. So this reaction condition, to carry out the reaction in the dark without light, this gives a very low percent of the yield. That means the light is very, very essential for this reaction. Without photocatalysis, this reaction gives a very low percent of yield. So both the light and the photocatalysis are very much essential for this reaction. But if you carry out the reaction in the absence of base, this reaction does not take place. That means base, light, and catalyst, these are the three things. Again, we have proved that if you carry out the reaction in the presence of radical scavenger, then you can trap the corresponding thionyl radical. That means the S dot radical is forming in the reaction medium. And when you carry out with another radical scavenger like this kind of thing, also you can trap this thionyl radical species. That means the thionyl radical is forming in the medium, and many of these species has been confirmed by HRMS analysis of this compound. So this continuous supply of light is very much essential. If you stop the supply of the light, that hoping that once the reaction initiated will continue, this is not correct. So this reaction, the continuous supply of light is required. So without that, when the reaction doesn't proceed, this thing. And that's also we have verified this thing, that when you quench this reaction get quenched in the presence of eosine Y, in the presence of benzene thiol, that means this radical species is forming, and this also we have confirmed by Stern-Volmor plot. Okay, so the mechanism of this reaction involves the eosine Y form the excited species, and that form the corresponding radical anion. And then either you can think about that this radical thionyl radical is forming by the oxidation of the thiol first. This thiol is getting oxidated to radical plus, or it can originate from the corresponding S minus species. But this is not to be the path. That's what we found from our CV measurement as well. Because when you carry out the CV measurement in the basic condition, it is not matching. Okay, so this is forming by this path is forming the S radical, attacking on one of the nitrile group, forming a nitrogen center radical, undergoing another single electron oxidation, and forming the corresponding amine. Okay, so either it can attack the it can result in the corresponding amine. This amine will attack intermolecular the carbonyl group, and then you can, with the elimination of the water, it will give the corresponding species. So, and this is the perfectly matching with the corresponding oxidation potential measured in the appropriate basic medium. Okay. So we extend this scope to the gamma ketonidyl. This earlier we have done the beta ketonidyl, but when you do the gamma ketonidyl, you could construct the 5-member thiosubstituted pyridine rings. So this is the metal-free condition. Again, similar kind of bond formation is taking place. And the beauty of this reaction is you can carry out the reaction in the presence of sunlight. Okay, and the reaction is very shorter compared to the previous reaction. The problem challenges with this reaction is when you carry out this reaction under basic condition, normally you get the corresponding chalcone. This compound will decompose into chalcone. That's why you have to carry out the reaction under control condition. Most of the reaction, the gamma ketonite require a tungsten metal. Most of the reaction averts the use of the bases and require a very high temperature. But if you carry out the reaction under photochemical condition, this reaction is quite smooth. So these are the various kind of substrate scope with the starting from the gamma ketonidyl. You can mix various kind of cyano-thiosubstituted pyridine. So these are the substrate scope. But what is the beauty of this reaction? We can also don't require a particular setup. So what my student did, he just put in the roof. Okay, he just put in the roof almost similar reaction time. So that you don't require a specific wavelength of the light, but the broad wavelength of light available in the sunlight is sufficient enough, and you are almost getting a comparable yield. But if you want to design a large scale reaction, one can design the reactor. We are using the same round bottom flux, but one can use a large RB or a flat one surface, so that reaction can be scaled up in a better way using the sunlight. So control experiment, what we found, that when you carry out the reaction in the dark, you are getting only 10% of the yield even after 24 hours, and without eosine, we are getting less percent of the yield. Okay. So this is require a basic medium, and the radical stress experiment confirm the reaction goes by the radical intermediate. Sujita is standing this thing, so I'll just cut short this thing. Okay. So these are the solvent effects. If you look at the solvent, how it affects the human being, okay, it changes the reactivity of the human being. So we also did the solvent chemistry quite some time back, and so we have got, so I'll just skip off this thing because we did a lot of solvent chemistry earlier in our work. So I just tell you one of the quickly in the 5 minutes time. So we also carried out the solvent mediated selectivity. So when you carry out the same reaction, same coupling partner, same catalyst, just change the solvent. So you are getting a complete selectivity. In this case, using the TFA as the solvent, using the manganese catalyst, you are getting a ortho-related product. Using the TFA catalyst, you are getting the activation, the reactivity is taking better. This CH bond. In this case, it's taking this CH bond, and you can find from this publication. But what we found interestingly, this substrate, the third nitrile substrate, when boronic acid in the presence of palladium catalyst, TFE solvent is giving the ethanol solvent is giving the predyl derivative, but in the TFE solvent is giving the cyano derivative with a exocyclic cis alkene containing substitute. So we are getting a jet selective product exclusively. So one solvent is giving this product, another solvent is giving this product. So this is the exclusive solvent selectivity, and this is quite general, work with a large number of substrate. And if you look at this thing, this is for this one, the predyl derivative is working fine. Okay, these are all predyl derivatives, and this is the alkyne substrate. You can get exclusively the cis product, not the trans product. Okay, so although your starting metal is as trans product, you are getting the cis product here. Okay, exclusively. So we did these are some substrate code. I'm just skipping this one. I did some control experiment. Okay, and we found that if you look at the energy difference between the cis and trans, they are just differing by 1 kilocalorie per mole. So what is the exact driving force? We are not yet clear this thing. Okay, so we have again this revised manuscript submitted, but we are yet to get the final acceptance of this thing. We have given our argument that there are few literature reports are known this thing where people are getting the exclusive cis product. Okay, so coming back to the last slide of this thing. So having made this compound, we also carried out some of the post-synthetic modification of this compound. You can get a highly fluorescent molecule using the preformed compound. You can do a manipulation of the nitrile group to corresponding amide. You can do a boronic acid addition to the corresponding keto group. So these are the mechanism. Probably I will not touch upon detail this thing. There is some solvent interacting in a peculiar way here and giving a completely different selectivity. One case you are getting a predyl derivative. In the ethanol case, you are getting this kind of other product. So I'll just skip this thing by. This is the abstract of my work, and I'd like to thank all my students who has contributed to this work, and I thank the chair and the organizing committee member.
Friends, I'm sure all of you are enlightened by this lecture by Professor Patel. He showed various complicated substrates designed by simple arrangement of designed mechanistic steps. This is where chemistry comes into picture. When you can understand mechanism of various bond forming in using metal, then light, and also electro, and you can achieve a lot. Particularly like the way he has extensively exhausted the list to see what are the substrates which doesn't work. Many of us don't present that data, that for these substrates the reaction doesn't work. That is a true spirit of a good human being, and we are already learned today that we have to be a good human being. So very honestly, he has said for this substrate that the substrate doesn't work. And he's also critically looked into the mechanism. Being a person who is interested in mechanism, I like that part also. I would like to invite only 2 questions because we are very close to the lunch break. Only 2 questions I can invite. Please, Alokesh, go ahead.
So a great lecture, really enjoyable. So in case of alpha tetralone, I could see that in one of the slide, I think
Aromatase.
34 slide,
Hmm.
where you had alpha tetralone substituted, and then product you got actually over oxidized, right?
The oxidation, yeah, there is a reaction condition, yeah.
So have you done that reaction under oxygen atmosphere or?
34,
And then you
yeah.
have used the similar type of substrate later on,
yeah,
with thiol.
yeah, it did not
with
oxidize.
light.
Yeah, it did not oxidize. Yeah, yeah.
Yeah, it's
So
very
that
interesting.
because this is due to the presence of the 30. This one probably, if you remember, just a second. Yeah, this one. Yeah. So if you look at the condition for this reaction, yeah, this condition for this palladium is there. Okay, this is in the presence of oxygen atmosphere. This is in the oxygen, but the second case it is in nitrogen atmosphere. Second case, the thiol case, that is nitrogen atmosphere, because thiol tend to get oxidized. So we did not do the reaction in the oxygen atmosphere. We did the nitrogen atmosphere.
So you in all these cases you have done under oxygen.
Yeah, normal air atmosphere.
Okay, great. Thanks.
Yeah.
Interesting one.
Any other question, please?
Yeah, the last one someone is asking.
Yeah, please go ahead. Please be precise and ask clearly.
Yeah, Professor Patel, indeed a very informative talk. So my first question is regarding that electrocatalytic method. Is it done on a divided cell or undivided cell?
I am just not very expert in the electrochemical method, to be honest, so I'll not be able to do this thing. So it is divided cell actually.
Okay.
Yeah.
And from your CV, it's look like they have different potential to
different
get
potential,
oxidized.
yes. And
So-
different potential in the different solvent also. We have done in the DC, you have done in the DC, TF, and there is another solvent is there, tetrafluoroethanol solvent is there, another solvent is there. So this changes, shifts this thing.
Okay.
So helps in the oxidation.
So that means the synthesis was done at a particular potential so that both can be oxidized.
Exactly. Yeah.
Okay.
It's the intermediate
Okay.
potential.
Okay. And another thing is you showed a Sternformer plot
Yes.
regarding a eosine.
Huh.
So at initial concentration, it looks a little bit of flat line and then the quenching starts.
Yes.
So is it due to like some initial interaction is required?
Exactly. The hydrogen bonding interaction is required only. That's so that particularly hydrogen bonded solvent is very much essential. Without that solvent doesn't work. Okay. That's what I have shown in the mechanism, that the strongly hydrogen bonding with the others, this hydrazide nitrogens is required.
Okay, sir. Thank you.
Yeah.
Thank you.
I'm sure there will be questions, but Professor Patel will be with us today as well as tomorrow. So it will be our pleasure to appreciate his distinction in presenting this particular work. I would request the volunteers to give me a token of our memento so that I can felicitate Professor Patel in our usual way. This is only to show that we are very thankful to you. Okay.
It's my pleasure.
And this is our,
Thank you.
Okay, now without any other thing, we'd like to break for lunch. But before that, I would like to remind you that very exciting talks are coming up. So you have to hurry up and then be here exactly at 1:55 p.m. Any other announcement by the volunteers? Please come.
Hello. Please, everyone be seated just for a couple of minutes. So, I now request the Associate Head of the Department of Chemistry, Dr. Snehasis Chaudhary, to felicitate Professor Sujit Roy for chairing this session. Now we can move on for the lunch. Please use your left exit for the lunch for the smooth function of the workshop. Thank you. I request everyone to please reassemble at 2 p.m. precisely for the next session. Thank you. I request all the participants to kindly occupy the seats so we can proceed further with the workshop. I once again warmly welcome all of you. I hope we are all re-energized after that scrumptious lunch. Let us resume session 2 of day 1. This session will be chaired by our honorable guest, Professor P.C. Ravi Kumar from IIT Bhubaneswar. I humbly request sir to commence the proceeding of this session.
First of all, I would like to thank Dr. Tadrish for giving me the opportunity to chair this session. We have two eminent speakers in this session, Dr. Alakesh Bisai and Dr. ATB2. And first the talk is by Professor Bisai. So Professor Bisai don't need a big introduction, but still, since it's a formality, I'll briefly introduce him. Professor Bisai completed his PhD from IIT Kanpur with Professor Vinod Singh, and subsequently he moved to University of Berkeley, University of California, Berkeley, with Professor Richmond Sarpong, wherein he worked on the project total synthesis of lycopodium alkaloids. And in the year 2009, he moved to IIT Bhopal as assistant professor, where he continued and rose to the rank of professor in 2018. And later in 2019, he decided to shift his base from IIT Bhopal to IIT Kolkata. Currently, he's a professor at IIT Kolkata. And Professor Bisai has got numerous awards, but I will mention specifically few of them, a prominent one. Professor Bisai got a CRSI Young Scientist Award and CRSI Bronze Medal, SCRB Star Award, and recently he got CDRI Award for Excellence in Drug Research. Professor Bisai is also a member of various committees, and also he's Dean of Faculty Affairs at IIT Bhopal and many other committees. So right now I will request Professor Bisai to come on stage and request him to complete his talk within 40 to 45 minutes. Thank you. Professor Bisai.
Pointer इधर है. All right, so good afternoon, everyone. Good afternoon, everyone, and I thank the chairman for his kind introduction. So at the outset, I would like to thank the organizer, particularly Professor Tabrez and his colleagues, all the organizing team, for wonderful hospitality and for the kind invitation. Today morning, we already had a phenomenal lecture by Professor Mehta. And then followed by, we had another lecture by Professor Patel. So it's a great start, I could say. So today's lecture, so I'll be talking about nature-inspired total synthesis of architecturally intriguing natural product. Of course, those are having some interesting biological activities. So the inspiration for our group, so particularly after listening first talk by Professor Mehta, is sort of very tough where to start actually, because the sort of slide he said and the kind of sustainability and futuristic things he talked, so many times it will not fit of many, our research. But however, I would like to connect with his talk in terms of circular chemistry. Okay, so in that regard, our inspiration and motivation is for the drug discovery. And if you look at the criteria for better drug, particularly follows ADME principle, this is well-known things, but for the benefit of student, I would just like to read out some of the things which is already shown and also try to appreciate that circular chemistry itself is a nature-inspired strategy. Okay, let's look at why this ADME principle. So this particularly tells us why chemistry is very important, and particularly why actually heteroatoms are very, very welcome for the drug discovery. Look at this distribution. Again, everywhere you will see that homo-lumo consideration, that interaction is very, very required. In fact, chemistry itself is inspired from nature. Okay, so therefore, we tell that if you want to be good biologist or good chemical biologist, one has to understand basic principle of chemistry. Now, the problem comes in the drug discovery over here. The reason being, if you look at nature, the way nature makes molecule, she will not only make, she will also break it. Therefore, nature follows the principle of microscopic reversibility. Okay, this is very, very important phenomena or strategy that nature makes, utilize. So not only synthesize them, but also break into pieces. And again, if it is required, again you combine them, right? So the principle of microscopic reversibility, again, it is nothing but a nature-inspired thing. In fact, today Professor Mehta was saying that we have to repurpose of research, repurpose also the teaching, the way we do teaching, because probably we have to think about how nature is operating things. In that way, we could actually probably address many issues, what are the difficulties associated in the chemical synthesis. So I just take this example that if you to get fatty acid biosynthesis, okay, and its degradation, and the kind of mechanism nature follows, because these are very different than what we do in the laboratory. Think about the oxidation event in the nature by NAD+. and the way we do oxidation in the laboratory using PCC or any other oxidizing agent, the mechanism itself is different. Okay. So we need to know the nature. Of course, this is also very important things. So as a whole, if you look at in the drug discovery, the three-dimensional architecture, therefore chirality is a very important thing because nature itself is chiral. And you can see that natural product and its derivative will have better success in the drug discovery. Why? As I already said, nature follows the principle of microscopic reversibility. Since these are natural products, since nature know how to make them, probably nature also know how to break them, right? So therefore, a good drug, by definition, has to metabolize. You get some, derivative or small molecule that should again take part one of the biological processes already occurring in the biological system. Okay, that itself tells circular chemistry is already involved. Therefore, we think that circular chemistry is not a new idea. It is actually a nature-inspired strategy. Okay, so we think that natural product will have better opportunity for drug discovery. And in fact, you can see some of the example I have taken. Today, you have seen folic acid methotrexate molecule in Professor Patel lecture. He has very nicely made this carboxamide bond using their strategy. Now, if you look at folic acid, which is a natural product, so vitamin B9, okay, used as a drug molecule. Now, if you look at the biosynthesis, it starts from GTP. Now, GTP is the responsible for the synthesis of pyridine ring, which is a heterocyclic motif. Okay. Then you see this para-aminobenzoic acid. The starting point is shikimic acid pathway, and then of course this glutamic acid. And the point I'm trying to make here is that the natural product can actually inspire to make new drug candidate. If you look at methotrexate, okay, which is nothing but N-methylation of folic acid at this junction, as well as an aminolysis at this position, right? That leads to an anti-cancer drug. So I have taken another example, which is actually a drug, which is already a commercial drug, originated from CDRI, RT-THAR, particularly beta form drug. And if you look at the natural product, artemisinin, and you know the 2015 Nobel Prize to Professor Yu. So this particular motif is nothing but again nature-inspired molecule. So what is that? There is a lactone. Now lactone is reduced at this position. Now it can give you alpha and beta. And they have seen that alpha and beta, both mixture, is found to be a good drug molecule, and in 1997, it was actually marketed. So in this regard, we have developed many strategies for the synthesis of biologically active natural product. And while doing that, we devise a strategy which goes through, which gives us unified approach. So while targeting a complex molecule, we go through a route where we also come across through a number of natural product. So in this regard, I would like to show you this methargine or ergometrin, which are actually again commercially available drug molecule. We have synthesized from some sort of chemical strategy. Later on, we have also developed on strategy from tryptophan. So this is another drug molecule, physostigmine. So this is used for the treatment of Alzheimer's. Now this molecule is also, you can see that 1 mg per ml. So this is the salicylate salt of this physostigmine is actually commercial drug molecule. Now recently drug repurposing is becoming the major focus for many pharma industry because the cytotoxicity of those compounds are already reported. Therefore, a drug repurposing would enable people to make better drug for other diseases. So we have synthesized this molecule. I'm not going through this synthesis. Very recently, we have made another natural product, that is galanthamine. And galanthamine, again, this is a well-known drug for Alzheimer's treatment. And this is, we have already completed, but recent focus is towards the synthesis of this kind of natural product. This has been isolated very recently in 2021. This particular natural product is showing arthropoda Basically, in this case, what is happening, you have a biaryl system. Now, since you have already chirality enriched over there, so this leads to a pair of arthropoda and those both diastereomers have been isolated in 2021, and we are very close to the synthesis of this. Also, there are other alkaloids. We particularly target alkaloids or other oxygenated molecule because these are found to be better drug. So these are the other research area which I'm not going to talk today. Just wanted to show you some of the structure like lysergic acid or their derivative, as well as their rearranged skeleton like cycloclavin or like dimeric hexahydropyrroloindolin alkaloid or their rearranged structure. Also, there are some structure where diketopiperazine is appended onto these dimeric hexahydropyrroloindolin alkaloids. So in today's talk, I would like to give you little overview of what we have done in this area. If you look at geomycin and oridamycin, they are nothing but a pair of diastereomer. Now, if you look at the literature, what they said that dimeric form of these monomers found to have better biological activities. So there are natural products like digeomycin C, where you can have a CN bond formation at the para position of this nitrogen. There are a lot of various oxidized version of this molecule, like at the pseudobenzylic position. If you look at here, you have alcohol, you can have ketone. These all are natural products isolated from various species from nature. So when we do devise a retrosynthetic analysis, we look at the structural resemblance between the diterpenoids, which are already reported in the literature. So what do we think that if you have this kind of scaffold, by replacing this aromatic ring with just carbazole would actually give us a strategy for not only for indolosesquiterpene alkaloid, but also this kind of diterpene molecule. So more interestingly, this is particularly only one example in the literature reported where a NN bond dimerization, NN bond formation leading to a pair of diastereomers, which is very interesting because these kind of molecules are very, very interesting in a sense that the question of their stability, because it can easily make NN diradical, and therefore they can lead to a lot of side reaction associated with dimerization. So if you look at digeomycin C, this is the only one molecule. However, if you look at digeomycin A and B, these are two different molecules. These are nothing but arthropodiastereomers. This is very interesting. NN bond formation leading to arthropodiastereomers. So if you look at the literature, it started by Phil Barron in 2014, and then Mike Crisse has shown a report on oridamycin. Richmond Sarpong in 2019 showed unified approach to both these classes of alkaloids. These are diastereomers. They start with a carbon. And from our country, Dethe from IIT Kanpur also has shown a synthesis from misaroylen ketone. And in 2022, we have reported our strategy. Now, when we look the first report by Phil Barron, Barron showed that if you take this geomycin A under electrochemical oxidation, one can actually form NN bond. Now, interestingly, what they said that if you oxidize it, they could only isolate digeomycin B in 28% yield, and there was no trace of digeomycin A. Okay, this is where actually we ask a question: if it is a NN bond formation, why not the other arthropodiastereomer? This is where we started asking a question, and also in this condition, they could see that aromatic bromination could give them 17% yield of this bromoiodine compound. Therefore, it clearly indicates the choice of electrolyte for electrocatalysis is very, very important because this is the source for actually this bromination, and of course they recover some of the starting material. So we ask a question, why not diazomycin A? If it is a N radical dimerizing to another nitrogen. So this is where we started our project, and we thought a functionalized skeleton shown over here where there is a double bond, we can actually, this double bond can give us synthetic handle for the synthesis of all these alkaloid what I have already shown, and these can be synthesized from a sort of CH activation. So if you look at this molecule, there are a lot of delta position, delta 1, delta 2, delta 3, delta 4. So we thought of, functionalizing one of this CsP3H hydrogen to get this kind of functionalized code. So we started our synthesis from here. So we thought of doing some sort of, chelation with this iodosobenzene diacetate. Therefore, thought of doing this because this based on the well-known literature by Phil Barron for their synthesis of methyl atisinoate. However, what we have seen that in this case, these always give byproduct, like we got elimination product, we got a double bond. In many cases, we have got ketone as well as over-oxidized product like alpha-beta unsaturated ketone. We have also tested other condition and using light, but we again found that this reaction is rather disappointing. This always gives some sort of byproduct. Those are essentially because of the oxidation in the presence of hypervalent iodine. Then what we did, we just took this enone and treated with NBS in presence of H+, and we were pleased to find that we can actually get this secondary bromide in 86% yield. So to look at the reaction mechanism, what we did the same reaction in absence of NBS, and what we can see that we can isolate this particular compound and which has been characterized. And that when we have taken and treated with NBS, this gives us secondary bromide. So this particularly give us the sort of a mechanistic consideration, and what we believe is that this enone is pulling the electron, therefore generating a carbocation over here at this position. And now once you get once you generate a carbocation, it can do 1-2 migration of methyl group, therefore you get a stable carbocation that can give us the olefin which has been isolated. Now in the presence of NBS, we believe that this NBS reacting and the convex phase of this ring leading to this kind of bromonium ion. Now again, 1-2 migration of methyl group leading to the formation of this kind of secondary bromide. Now with this in hand, in 5-6 steps, we have completed the synthesis of all these natural products. So basically you do an E2 elimination followed by allylic oxidation, followed by again hydrogenation or synthetic manipulation. Now, when it comes to diazomycins A and B, what we thought, can we have this kind of 2-aryl aniline? Now, can we do in one pot CN bond formation as well as NN? So we thought of having an envision of having CN, NN, and CN. These 3 new bond formation at one go. So that is sort of very ambitious project. So we also thought of having synthesis of this molecule based on the biosynthetic hypothesis, starting from geomycin A, what has been reported by Phil Barron under electrocatalysis, but we thought of doing this under chemical condition. So basically this N-center radical can dimerize to give diazomycins AB. Also, this N-center radical can react over there. Also, this hypothesis also tell us there would be future natural product which has not been yet isolated, but will be isolated. That is what we strongly believe, because if you look at this C-center radical, this should also dimerize to give us CC dimer, as well as it should be there are a lot of CC and CN dimer leading from this kind of radical species. So what we thought? We thought of having this kind of motif so that we can have, we can test our hypothesis. Again, the synthesis start from this kind of structural scaffold, which is diterpene. So in the forward direction, what we have done is that we closely followed the Pauline cyclization reported by Professor Kore, E.J. Kore. And what we did that this kind of epoxy alcohol was cyclized in presence of BF3 thread to give us the synthesis of epitryptobenzene L. And from there, we could actually make this carboxylic acid, and which has been done in large scale. And from there, we have just did electrophilic bromination followed by knockout of this isopropyl and stitching on nitro group in the aromatic system. And we have seen that interestingly, this secondary alcohol also can actually react under this nitration condition leading to nitrite. And that was confirmed through this crystal structure unequivocally. And then hydrogenation of this species finally give us this kind of species. Now, with this in hand, as per our hypothesis, we have tested various reactions. Various conditions using high valent metal, but till date, we are not successful yet. However, we believe that we should able to get some condition to affect this kind of 3-bond formation at one go. So with that failure, we thought of utilizing Buchwald process, where Buchwald has told that 10% of palladium acetate in presence of 1 equivalent of copper acetate, and under aerial oxidation, they could get this kind of carbazole, and they could synthesize this kind of molecule, a number of molecule, in up to 97% of yield. However, when we started our synthesis using this with the NHSE, this amine protected and secondary alcohol intact, we could see that this condition could give us mixture of product. Actually, so when student did the reaction and then sort of, was, not very happy, said that too many spot. Then I told that, can you just characterize all this? And what has been found that it gave this required bond formation. However, in addition to that, it also gives oxidation product like ketone as well as oxidation product like enone. And also we have recovered 19% yield of starting material. By changing this condition, by changing this toluene to DMSO, and without any transition metal oxidant, just aerial oxidation, we could see that this reaction could give us 83% yield of these two products, which is very encouraging to us, because this is actually doing a cascade oxidation. And what we believe is that this is doing this C-end bond formation, and this is particularly giving this ketone, and that ketone is actually again further getting oxidized to enone under when we have run this reaction in 18 hours. So what we could see that after the C-end bond formation, palladium acetate can do the oxidation of secondary alcohol to ketone. Now this ketone can undergo some sort of Sagusa-Ito type oxidation, leading to this enone formation. So with this in hand, what we did, we thought of just protecting this secondary alcohol as it was creating problem because of associated oxidation. So what we did, we just again under optimized condition, without using copper, we could get this intermediate, and from there we have made the monomer. Now monomer in hand, then we have tested our second hypothesis, which is actually a biomimetic one. What we could see that after several trials, we could see that it was required to protect this secondary alcohol in the form of TMS. However, in the same pot, we could do aerial oxidation with copper 1 and followed by deacylylation using potassium carbonate in methanol, leading to a pair of diastereomer, thereby establishing the nature's way of making these molecules through oxidative NN bond formation. So you could see that we could get diamycin A-methyl ester and diamycin B-methyl ester. So this is the first time we could get this structure. Now, keeping this sample over the period of 1 month, what we could see that diamycin A is sort of unstable, and that is slowly converting to diamycin B. And what under electrochemical condition, Baron reported that diamycin A could not be observed. This is probably converting to the better stable atropodiastereomer, diamycin B. Now I'm coming to the second part of my talk. So in this case, what we thought, can we devise a strategy for some sort of tetraterpene, which is thione J. So if you look at this molecule, there are around 12 stereogenic center, and there are a lot of stereogenic center and many all carbon quaternary stereo center in addition to this kind of cyclobutane ring. So if you look at this molecule, there is all carbon quad center, here is all carbon quad center, there is another one, here is another one, here, there, and here. So if you look at, there are 7 contiguous stereogenic center from this side, and 5 contiguous stereogenic center from this side. So this is very interesting thing because we thought of again following a biomimetic approach. So if you look at the thionoadacs B, C, D, they are nothing but again tetraterpene associated with a Diels-Alder adduct. If you look at this particular junction, you can see that cyclohexene over there, and thionoadact D is actually coming from the carbonyl in reaction of thionoadact B. So in 2014, Ang Lee group has shown their total synthesis of thionoadact D. So when it comes to 4+2 cycloaddition, this is very close to my heart. Actually, what Professor Mehta shown in way back 1980s, reagentless chemistry. So if you talk about sustainable chemistry, according to us, nothing could be better sustainable than the pericyclic reaction. Again, pericyclic discovery itself is a nature-inspired discovery. Nature is making this molecule long, but in 1950, when Diels and Alder discovered this reaction, we came to know what is called 4+2 cycloaddition. By the way, those all discoveries are nature-inspired. So in this discovery, if you look at what Professor Mehta showed, a 4+2 followed by a 2+2, followed by under heating a retro 2+2 can give them the triquinone. Without reagent, one can go there. And if you look at hirsutin, those are sesquiterpene, and there are many more. This triquinone can be elaborated to number of natural products that they have shown later on in their full paper, synthesis of coriolin and many other. This is another slide, the synthesis of longithoron. And this is probably the best example, and this is the only one example reported in the literature. If you look at longithoron, this itself tells us how an intermolecular as well as intramolecular Diels-Alder can give the synthesis of longithoron A. Both are normal demand Diels-Alder reaction. It's a fantastic, discovery by Matthew Sayre way back in 2002. So what we thought, can we, based on the hypothesis, biosynthetic hypothesis, can we do a Diels-Alder coming from this kind of, abioabiton skeleton with transoxic acid, and then do some sort of 2+2 cycloaddition reaction. So a 4+2 followed by 2+2 should answer the synthesis of this. Again, we thought of synthesizing both these partners from a common precursor that I have already showed you in my first part, that is nothing but diterpene. Okay, there are a number of natural products nature makes. Those are actually diterpenoids. So we thought of utilizing this unit to get both these partner, and that can be combined to get the natural product, tetraterpene, thionoadact J. So in this regard, again, Core's polyene drew our attention. Core has shown a number of polyene cyclization, and these are very interesting things. There are studies, Professor Shantanu Mukherjee is there, which is who did postdoc with E.J. Core, and I used to also listen a lot of interesting story from him, that how Core has envisioned all these, and then how actually they could actually get the success in this area. So what we have seen that 1.1 equivalent of SbCl5 and this particular binol can give rise to this kind of tricyclic motif in 91% of yield. And very nicely, they have decorated their substrate in such a way that this should give the only 666 cyclization. And with that, they could actually get 91% of enantiomer selectivity. Now, the next job was to do the oxidation through aromatic electrophilic substitution using thalloyl perbenzoate type of motif. So oxidation followed by ozonolysis and this thioesterification give this compound. Now with this in hand, we just did a reaction like Rosennemann type reaction. If you have acid chloride to aldehyde, this reaction and followed by 2 level of Utig and saponification give us transoxic acid. On the other hand, with this compound, we have functionalized it to get more functionalized skeleton like this. So there we have followed a procedure reported by Brian Stolz, and what he has shown that a phenol of this kind can be oxidized to this kind of over-oxidized aromatic ring. So with these two in hand, we then make this kind of benzylic ketone, then we made this alpha diazoketone. Now under heating, it can do a ring contraction under Wolf rearrangement, leading to the contraction of this ring, leading to a 5-member ring required for ABO-Abiton skeleton, then reduction, oxidation, followed by another level of oxidation, and hydrolysis, saponification give us this particular secondary alcohol in one of the diastereomer, which was further, make quinol, but this is where we have followed electrochemical oxidation to get a quinone. Now with quinone in hand, we have just heated these two compound. Of course, you require europium 4. So this gives us 3:2 regioisomeric ratios of these two compound, which were not separable under column chromatography. Therefore, it was oxidized. Now this gives us two regioisomers, which are clearly separable in column chromatography. Now, in fact, when we took this mixture and we irradiate with light, we have found that this 2 + 2 can be performed. Very simple way. I mean, these steps, although, the separation of this compound, this particular steps gives a lot of pain to the student, but however, when it came, it actually came in very nice way. We could see that a 2 + 2 would give us 93% yield of this final natural product, which was also characterized through the usual X-ray crystallography. So right now we are concentrating on, another interesting observation, we have seen that if there is this OH protected, earlier case it was OME, but if it is enol, we have seen that this Diels-Alder give only one of the single regioisomer. Although we do not know the reason of such selectivity, we are just trying to explore this reaction, why exactly we are getting one of the single regioisomer, but we are very happy that this itself is the starting material for thionyl H. And now for thionyl D, what we believe is that a natural product ABO-Abiton having this and this should able to do give us a 4 + 2 followed by a carbonyl in reaction. Hopefully, under the same pot, we should able to do this cascade, and hopefully I will be able to speak in next visit. So to conclude, natural products and this analog having 3-dimensional architecture are very, very welcome. In the area of drug discovery, I have taken few examples. Strategies that can give us unified approach. At one go, you can come across many natural products are welcome. And development of nature-inspired methodology. Therefore, knowing their biosynthesis is very, very important. And asymmetric catalysis, of course, is very crucial, because in one of the steps, you have to do asymmetric catalysis, and from there, you have to follow a diastereoselective reaction. So with this, I would like to again thank the organizer for the kind invitation. I'm thankful to my institute, IISER Kolkata. This work started at IISER Bhopal 4 years back, and which would complete actually last year. Pandemic took away 2 years. That's same for everyone. I'm thankful to all of my students who have actually contributed in this. I am just conveying their research. Also, some of the students' pictures are shown here. I'm very thankful for your kind attention. We'll be happy to address if you have any question. Santanu has one question, I think. No, you know. Yeah, Professor Mal.
Okay.
Yes, yeah.
Even after the synthesis, how stable this compound is? And
Yeah,
once
so
you make it, for example, the right side one, that is the dexamycin B, because he was saying that it can be easily convertible to other one.
yes.
So what is the kind of temperature or everything? So it's a room temperature, or if you store in the low temperature, and then how stable the compound B is?
Yeah, so that's a very nice question. When it comes to the ectopodiastereomer, see, normally if you take example of binol, these are having CC, very stable bond. But in this particular case, it is NN. Definitely this is weaker than CC bond. So therefore, this question is very valid. Thank you for asking this question. So basically, if you look at, so we have to do, although I admit that we have to do DFT calculation to understand the barrier to rotation required for this molecule. So one of these isomer, particularly digamycin B, which is also made by Phil Baron, which is more stable than this one. Now, the sterics is coming because of this decalin system. Now, this stereogenic center is actually responsible for, digamycin B to be more stable than digamycin A. So what we have seen that keeping 24 or 25 days, digamycin B NMR is same. However, this particular compound,
It's an atropisomerization, right?
Yeah, it's a atropisomer. So yeah, look at here and this stereogenic center.
Like biphenyl atropisomers.
Like biphenyl, yeah. So in this particular case, we have seen that over the period, this started decomposition. And what is that decomposition? Slowly, this is converting to this. So if, after 24 days, we have seen that this structure is, it was 90:10, some sort of ratio. But I'm sure we have to do some more studies under heating or under thermal condition and just to find out that how long it took from here to there.
Even try some visible light,
Not only that, we are also looking for opportunities for such compound. Can we generate this N-center radical? Now, can I get the other isomer coming from CC dimer or CN dimer? So this, right now we are working on it, but thank you for this question. Yeah, we should do some sort of theoretical studies to understand the various.
Okay, thanks for this.
Yeah, Santanu, please.
Following Professor Mal's question, I think you don't need to do the DFT for checking the NN barrier. If you have this mixture, if you can separate them, and I'm assuming that you have.
Yeah, we can separate. These are separated.
So in that case, you can actually follow the temperature versus DR curve, and then from there you can actually determine the NN barrier. You don't need to do a DFT. I think there is a very nice method developed by Dennis Curran. He did it for atropisomers, which are basically enantiomers, but these are diastereomers. So I think it will be even easier actually.
Please share that.
You can check by.
Thank you very much.
Check by NMR.
Please share that reference.
Yeah. Yeah, you can get the ratio of these two, and it'll be much
from
easier.
NMR even we can actually separate them.
Yeah.
So from NMR, of course, it will be easier to get the.
Easier actually. You can do a temperature dependent. Temperature dependent actually. Yeah, you can do that. Yeah. Just another thing, just out of curiosity. You said atropodiastereomer. Is this a term commonly used? I've never heard about it. I mean, these are diastereomers. We completely understand.
These are atropisomer, but some of the isolation paper, they said actually two terms. Like if you say atropisomer, that itself represents the same thing. But they call it as atropodiastereomer.
Yeah, so that
so
is
I just took.
Clear.
I mean,
no, that's fine.
This term.
Okay. Thank you.
But
So, any more questions?
Okay.
Yeah, Tirupati. Yeah. So so this compound we can get 1.5 gram. Yeah. So and then therefore we can get more than 100 milligram. We can actually synthesize this very easily. I mean, of course, if you do repeated time, we can get more. Yeah, sir. Huh? Oh no. I mean, yeah, of course, student has done. Yeah,
So
thank you.
continuing the same thing.
Yeah.
So many of the drugs molecule that you synthesize in the earlier slides.
Yeah.
When you make it a large scale, in a kilogram scale, and how is the price compared with your methods with the market one? Where do we stand?
Thank you. Thank you very much. So right now we have not done in kilogram scale. Okay, we have established to get up to 1 gram or 2 gram. Okay, so we have to do fine tuning to get this actually. Basically, we are following some biosynthetic strategy to get them
But one can
from
do a
tryptophan.
calculation that the cost of this thing and method, solvent cost and other things, you can do it.
Probably a patent, and there are a lot of opportunity to do patent and all this, but you need student of different set of that kind of mental set and
Comment that. I think more than that, most of the time we do not calculate the cost of solvent. I think that will edge out everything else.
Oh, definitely.
That is even
Definitely.
I think solvent is going to be much more expensive as well.
Yeah, so you can think this is a much of academic interest right now. Yeah, Tabrez, please.
Setting up the carbocyclic core and then you are constructing the heterocycle ring.
Yeah.
So what about the other way around? Is it already reported? So that's why you're doing this way? can we start with carbazole and then set up the carbocycle?
Yeah, so carbazole anchor with such strategy is already reported by Phil Barron, but the problem associated with that is that they have utilized unprotected, and then yields were not that great, and then based on recover starting material plus costly palladium catalyst, we thought of having a separate flexible approach, which would address both at one go, diterpenoid as well as indolososquiterpenoid. So our target is it at one go, both things, because there are a number of natural products in diterpenoid also. Yeah. So with the one methodology, we can actually address them.
Any more questions from students? Okay. So if no questions, still we have time. So I will ask one question.
Oh yeah,
so in your 44 slide or somewhere, so
actually nobody give us 45-minute lecture time. Normally people give up to 30 minutes. So I think I went fast. Yeah.
Okay,
Tell
actually,
me. 45, huh?
You, yeah, this previous one.
Yeah, previous one.
Previous one. The last step. The previous one. Yeah. So actually can directly oxidize para-dimethoxy to ketone, the diketone.
Yeah. So that's a good
I
question.
wonder why you have gone for two-step process.
Yeah, this is not required actually. So as he pointed out, so can directly give us this, but while this process, what we have seen that, it gives a mixture of sport actually. The can, and once you have this kind of species, when you have this, particularly carbonyl, and this particular position, you have hydrogen that is actually situated at the vinylogous alpha position of carbonyl. So this particular reaction is very tricky.
Yeah, expected. Yeah.
So
tricky.
So you have to oxidize and immediately you have to charge and you have to reduce with this to get a stable form of this.
Even if you just leave it in air overnight, you can get that ketone without electrochemical. Did you try that?
Yeah.
That is very robust. It very quickly, hydroquinone gets quickly to paraquinone, even with potassium carbonate base.
That's a nice suggestion. So what we do here is that one equivalent of BCl3 actually can give us one of this OH. Yeah. Right? Now that we are actually doing electrochemical oxidation to get parabenzonucleone. So one equivalent of BCl3 followed by the treatment of electrochemical oxidation. So yeah.
Yeah, it's tricky.
This step is tricky. You correctly pointed out. Yeah. So yeah. So there are many things showed very simple way, but please, as I said, 4 years before we have started. So there are a lot of optimization involved that I have not presented. Okay.
Yeah, as you rightly said, I thought since we have time, it's time to mention it. Many steps for the benefit of the students. Many steps look so straightforward, but actually it is after a number of trials. Yeah. So there are very few people in the country who's doing total synthesis, and Alakesh is one of them. And I'm really proud and privileged to introduce such an eminent speaker here. So thank you so much. It was such a nice lecture, and I'm happy.
I would like to request Professor P.C. Ravikumar to felicitate Professor Bisai for such insightful lecture.
So our next speaker is Professor Biju from ISC Bangalore. Professor Biju is also another very eminent speaker, and he doesn't need much introduction, but still I have to do my job. So I will briefly introduce him. Professor Biju did his MSc from Sacred College, Thevera in Kerala. He did his PhD from NIIST under the guidance of another famous scientist, Dr. Vijay Nair. And he did his first postdoc in National Taiwan University with Professor Tain Yan Lu. And then he moved to Germany as an Alexander von Humboldt Fellow with Professor Frank Glorious. And in the year 2011, he came back to India. He joined as an independent researcher scientist in CSIR NCL Pune. And in June 2017, he moved to ISC Bangalore as associate professor. And since then, he's continuing in ISC Bangalore. And his research is focused on transition metal-free carbon-carbon and carbon heteroatom bond forming reactions using arine chemistry and N-heterocyclic carbene chemistry. I now request Professor Biju to give his talk in 40 to 45 minutes. Biju, please.
Okay, so good afternoon to all of you. And at the outset, I would like to thank Tabriz for the very kind invitation. Yeah, thank you, Ravi, for the kind introduction, first of all. Yeah, Tabriz for the very kind invitation to be a part of this wonderful event. So this is my first visit to IIT Bhubaneswar, so fantastic campus. So in the next 45 minutes, I will be talking to you about one phase of our research on catalysis, especially on N-heterocyclic carbene catalysis, where I will try my best to convince you how carbenes can be used for unconventional access to target molecules. So we know that catalysis is one of the sustainable process for generating or forming carbon-carbon and carbon heteroatom bonds. And if one uses an enantiomerically pure catalyst, one can have enantioselective synthesis of target molecules. And among the various catalytic modes, starting from the enzyme catalysis, the transition metal catalysis, and the third and important, or the area which is developing, which is the small organic molecules based catalysis, which is now well known as N-heterocyclic or organocatalysis in general. So in the vast realm of organocatalysis, there is a subclass where one uses N-heterocyclic carbenes as catalyst for forging carbon-carbon and carbon heteroatom bonds in an unconventional way. So I hope I will be able to tell you how it is unconventional in the following slides. So carbenes, we know that carbenes are, in general, it's a electronically sextet species, very reactive and short-lived species because of the high reactivity. And whenever we think about carbenes, in general, we know that carbenes are electronically sextet. It needs 2 more electrons to complete the octet. Or in other words, carbenes are electrophilic in nature. The typical carbenes which are electrophilic are dichlorocarbene or dicarboethoxycarbenes. On the other hand, there are types of carbenes where the carbene-carbon is flanked by heteroatoms, such as oxygen, sulfur, or nitrogen, where the mesomeric effect of the heteroatom pushes the electron density towards the carbene-carbon, thus making the carbene-carbon nucleophilic instead of the inherent electrophilic nature. Such carbenes are known as nucleophilic carbenes. A typical example is dimethoxycarbene. When this carbene-carbon, which is flanked by heteroatoms, forms the part of a ring, we call it as N-heterocyclic carbenes, which can be either imidazole-derived, thiazole-derived, or even triazole-derived species. And these carbenes can be generated in solution from the corresponding azolium salts, the imidazolium, thiazolium, or even the triazolium salt by adding a mild base. So the mild base can abstract this relatively acidic CH proton, generating the carbenes in solution. So in most of the carbene catalyzed reactions or the carbene catalyzed organocatalytic reactions, this catalytically active species is generated in solution from the corresponding azolium salts in the presence of a mild base. So when we look at the chemistry of N-heterocyclic carbenes, carbenes are known for typically doing catalysis or by forming carbon-carbon bonds in an unconventional way. How? If you consider the addition of a nucleophilic carbene to an aldehyde, which is inherently electrophilic in nature, which will convert a flat aldehyde molecule to a tetrahedral intermediate, which can undergo a proton transfer, bringing it back to a flat species. Or in other words, if you take an aldehyde which is inherently electrophilic in nature, after addition of a carbene to the aldehyde, what we basically did was a polarity reversal of this aldehyde from inherent electrophilic nature to a nucleophilic nature. Because this enaminol, which is otherwise known as the Breslow intermediate, it is a hidden enamine, making this carbonyl carbon now nucleophilic, or in other words, it is as equivalent to an acyl anion. So carbenes are typically known for this polarity reversal of an aldehyde from inherent electrophilic nature to a nucleophilic character. And once this acyl anion is generated, this acyl anion can add to a different molecule to form a alpha hydroxy ketone, a benzoin, or it could add to electron poor carbon-carbon double bond to form 1,4-difunctionalized ketones in a name reaction called Stetter reaction. So this is the foremost mode of reactivity of carbenes in organocatalysis. The ability of this catalytically active species to reverse the polarity of aldehyde from the inherent electrophilic nature to the nucleophilic character. And this Breslow intermediates, the enominols, which I showed, which was just a proposal in 1958 by Breslow. So in 2013, the structure of all these Breslow type intermediates were fully characterized, even with single crystal X-ray analysis by Professor Berkesel and co-workers from University of Cologne. And if you see the chemistry of Stetter reaction, where the aldehyde can add to Michael acceptors. So the carbene adds to the aldehyde, generating the nucleophilic Breslow intermediate. Now it is nucleophilic enough to add to the electron poor carbon-carbon double bond, generating this enolate equivalent, which undergoes proton transfer and elimination of carbene to form the 1,4-difunctional compound. So when we started working in this area, the Stetter reaction, everything was known, but the addition of aldehydes to moderately electron-poor vinyl sulfones and vinyl phosphonates were not well studied. So in 2012, we demonstrated the carbene-catalyzed addition of aldehyde to a moderately electron-poor vinyl sulfone, generating gamma keto sulfones in moderate to good yield. So generating the umpolung species from aldehyde using this thiazole-derived carbene and addition across this carbon-carbon double bond to form vinyl sulfones in moderate to good yield. We extended this concept to vinyl phosphonates, where a variety of aromatic aldehydes can be cross-coupled with this electron-poor system to form gamma keto phosphonates in moderate to good yield. So in addition to Stetter reaction, where the aldehyde can add to electron-poor carbon-carbon double bonds, this chemistry can also be combined with a variety of cascade processes. For instance, this Stetter reaction can be combined with an aldol reaction for the construction of tetralone derivative, a diastereoselective synthesis of tetralones, demonstrated by Song-A and co-workers. So what happens here is the carbene adds to one of the aldehyde moiety, generating the tetrahedral intermediate now, and a proton transfer to form the nucleophilic Breslow intermediate. And this Breslow intermediate now adds to the electron-poor carbon-carbon double bond, and the generated enolate then adds to the second aldehyde moiety to form this carbinol derivative in high diastereoselectivity. So we envisioned having this knowledge of the Stetter aldol cascade, can we utilize this chemistry for the construction of axially chiral molecule? Specifically, the CN axially chiral molecules can be envisioned by using a Stetter aldol cascade process. So what we envisioned was, so to take a dialdehyde and take a maleimide derivative, so a tertiary butyl substituted maleimide derivative, and if the Stetter aldol pathway is feasible, this could lead to the formation of a carbinol. Now one can think about two chiral centers here, point chiral centers, and a CN axis. To make things little easier, what we did was, if the carbinol is oxidized in situ, the 2 point chiral centers will be gone because now the system will be symmetric and leads to only a CN axis. And essentially, this leads to a simple desymmetrization of this type of malamides using carbene catalysis by the combination of a Schetter reaction and an aldol reaction. So with this idea in mind, Salman Barik, an integrated PhD student, started working in this cascade process, the Schetter-aldol cascade, and finally using phthalaldehyde and this 2-tertiary aryl malimide derivative, the carbene generated from the amino-indinol derived N-heterocyclic carbene species, and in situ, this was coupled with an oxidation event using PDC to form these succinimide derivatives in good yield and high enantiomer selectivity. So this reaction was working with variously substituted malimide derivatives as well as symmetrically substituted dialdehyde derivatives. In all the cases, the yields are okay and the enantiomer selectivity values are reasonably fine in most of the cases. So this reaction proceeds via the generation of free carbene, and the free carbene adds to one of the aldehyde moiety to generate the tetrahedral intermediate. Now the proton transfer leads to the formation of the nucleophilic Brislow intermediate, and the Brislow intermediate can add to one of this electron-poor double bond of the malimide derivative, generating an amide enolate equivalent, which can undergo a proton transfer to form a more substituted, a tetra-substituted enolate, amide enolate equivalent specifically, and this will undergo an intramolecular aldol reaction in the presence of a carbene to generate this carbinol, which can subsequently oxidize to form the desired CN axially chiral molecule. So we also considered the possibility of the elimination of free carbene first before the aldol event to generate this ketone system, and to this ketone, the intramolecular aldol reaction can again lead to the carbinol derivative, which can be further oxidized to the desired product. So to get more insight into which pathway is operating in our case, we seek the help of my colleague, Garima Jindal. And with the detailed DFT calculation, Garima was able to find that the pathway 2 leading to the aldol reaction in the absence of carbene was stabilized by almost 5.4 kcal per mole, which indicates that the carbene eliminates first before the intramolecular aldol reaction. And once the carbinol is generated, it undergoes oxidation to form the desired axially chiral succinimide derivative. So if you look at the symmetrical malimide derivative, as I said, it is a symmetrical molecule. And this molecule has two atropotopic phases, the CA and CB. The nucleophilic addition to one of the phase can lead to the pair of enantiomers. And in our case, we believe that the addition of this nucleophilic Brislow intermediate happens at this particular carbon, which leads to the formation of this desired product after the intramolecular aldol reaction, which is in agreement with the single crystal X-ray analysis, what we observed for one of the compounds. And this also rules out the possibility of the nucleophilic addition of Brislow intermediate to the CA carbon, which could otherwise lead to the minor enantiomer of the reaction. So we also tried to get some insight into the stability of the CN axis, or how much the CN axis can survive with respect to temperature. So we found that up to almost 90 degrees Celsius, the CN axis is restricted in rotation, which is clear from the EE retaining the EE value of almost 90% up to 90 degree, but further increasing the reaction the temperature of the system will allow a drop in E, which gives a hint that the CN axis is free to rotate after 90 degree, and almost at 150 degrees Celsius, this will be resonate. So the CN axis is stable up to 90 degree without any considerable change in the E of the system. So moreover, we calculated the CN rotational barrier. The rotational barrier for this tertiary butyl substituted succinimide derivative was calculated to be 32.4 kcal per mole following the procedure of Denis Picuran. This was in agreement with the theoretical calculation by Garima. So the calculated CN rotational barrier is almost 34 kcal per mole, which is in agreement with the experimental value by noting the EE value with respect to the change in temperature. So I should confess that this reaction proceeds with high efficiency only when the two tertiary butyl substituted malimides were employed for the reaction. But we also try to get some insight, what is the role of the tertiary butyl group? So we synthesize the malimide derivative with a methyl as well as the isopropyl substitution. In those cases, the reaction works well, leading to the product formation in moderate yield, but as you can see, the product is racemic. That means the CN bond is free to rotate with methyl and isopropyl substituted system, which also gave us a hint that in those cases, the rotation, the energy for the rotation will be relatively low, which was calculated by DFT by Garima to be 22.4 and almost 24 for methyl and isopropyl systems respectively. This gave us a hint that with methyl and isopropyl system, the low rotational barrier is the key for no EE in the process. So in short, what we demonstrated was the desymmetrization of this malimide derivative using a combination of a Stetter reaction and an aldol reaction, where one can think about construction of a wide variety of N-aryl succinimide with a CN axis, with the reaction proceeding under moderate to good yield and high in-ensure selectivity. So as I said, this tertiary butyl substituted malimides are symmetrical, and we have demonstrated the desymmetrization using this Stetter aldol pathway. So if you think about this malimide derivative, it is symmetric, a chiral and a prochiral substrate, which is clear from the HPLC pattern having a single peak in HPLC. The moment you introduce a substituent, either at the olefin or by a reduction of this carbonyl to the hydroxy functionality, the symmetry of this molecule is lost, or the molecule will be not symmetric or even the chiral, and normally it is racemic in the absence of any chiral source, which is demonstrated by the 50-50 separation in HPLC. So we thought, can we utilize this chemistry, the non-symmetric malimide derivative, for non-carbene catalyzed reaction? So specifically what we thought that if we introduce an amino moiety at the olefin, that now this will be an enamine moiety which can be utilized as a nucleophilic species in carbene catalyzed reaction. So specifically what we envisioned was the addition of this enamine moiety to catalytically generated alpha-beta unsaturated acetylsodium, which is one of the important modes of reactivity of carbenes in organocatalysis. And this mode of reactivity, or this species, can be generated from an alpha-beta unsaturated aldehyde and a carbene generating the nucleophilic slow intermediate and a stoichiometric oxidation to form this alpha-beta unsaturated acetylsodium species. So the idea was to couple this enamine moiety with this alpha-beta unsaturated acetylsodium, a 3+3 annulation, with one of the enantiomer of this malimide species, thus leading to a kinetic resolution strategy. Because now the moment we introduce an amino functionality, the molecule is not symmetric, so we can have two enantiomers in that mixture. So with this knowledge of this alpha-beta unsaturated acetylsodium, over the years, we have utilized this single intermediate for the construction of various N-heterocycles, pyrosols, carbocyclic systems, and even spirocyclic system in moderate to good yield and high selectivity. So with this result, what we thought was the 3+3 annulation of this malimide derivative, the amino malimide with a 2-bromoenol, and as anticipated, Sauman got two products. One is the resolved malimide derivative, which did not react under the carbene catalyzed reaction, and the other opposite enantiomer, which underwent a 3+3 annulation to form this dihydropyridinone derivative in high enantiomer selectivity values, thus leading to a kinetic resolution strategy. So this reaction was found to be quite general with respect to wide variety of bromoenols and malimides. In all the cases, the dihydropyridinones as well as the resolved malimides were formed in reasonable yield and enantiomer selectivity values. So the reaction proceeds via the addition of free carbene to this 2-bromoenol, generating the nucleophilic Breslow intermediate And a debromination generates this alpha beta unsaturated acylosolium, which is the key intermediate. And now to this alpha beta unsaturated acylosolium, the enamine can add from this particular beta carbon to this beta addition, a vinylogous addition generates a will install a new carbon-carbon bond, but in this process, the reaction proceeds only with one of the enantiomer of the malimide. So we believe that this particular enantiomer of malimide, where the two tertiary butyl moiety is projecting above, will react where the enamine adds from the bottom face of this molecule because the top face is shielded by the amino internol core, which leads to the 3+3 annulation, whereas the opposite enantiomer where the tertiary butyl group is projecting below the plane, which does not react with the catalytically generated alpha beta unsaturated acylosolium, which explains how the resolution takes place or the kinetic resolution happens in this 3+3 annulation reaction. So with the result on CN axis, so the atroposelective synthesis of CN axially chiral molecule, we envision can we extend this chemistry to the atroposelective synthesis of NN axis. Just now, Alakesh has explained the importance of NN axis in natural products, and this atroposelective synthesis of NN axially chiral molecules will be even more challenging because of multiple reasons, because of the weak NN bond, the possibility of deplanarization, relatively low rotational barrier, and not many things are known with NN axis. So this will be even very challenging, the atroposelective synthesis of NN axially chiral molecule. So with this, with the screening of several NN bond-containing molecule, my student Balana came up with a quinosolinone substrate, a tri-substituted quinosolinone. As you can see, one of this nitrogen is part of the quinosolinone moiety, which gives some rigidity to the system. And there is a free NH. One can think about the functionalization of this NH using carbene catalysis to install a theta-substituted quinosolinone type system. And if successful, this could lead to an axial chirality. So as anticipated, using chiral carbene, a combination of this quinosolinone and NH amidation using this alpha beta unsaturated acyl aldehyde and carbene catalysis, we could do this amidation reaction and get the product in up to 94% yield and 98% enantiomer selectivity. The scope of this reaction was also very broad. We could extend this to a wide variety of quinosolinone derivative, even the indole derivatives. I'm not going into the details of the scope. So in all the cases, this axially chiral NN bond containing quinosolinones are formed in moderate to good yield and excellent enantiomer selectivity. Here the reaction, again, the reaction proceeds via the generation of free carbene. The carbene adds to the aldehyde, generating the tetrahedral intermediate, and then Brislow intermediate by a proton transfer and the alpha beta unsaturated acylosolium, the sequence of steps what we have seen in the previous case. Now in this, once this alpha beta unsaturated acylosolium is generated, the nucleophilic quinosolinone derivative can add to the alpha catalytically generated acylosolium intermediate from the bottom face of the molecule so that the top face is shielded in all the cases. So the bottom face addition is more feasible, which leads to the formation of this axially chiral NN bond containing molecules and axially chiral quinosolinone with an NN axis in moderate to good yield. So far I told you the ability of carbenes to reverse the polarity of aldehydes, where the carbene addition to the aldehyde generates the tetrahedral intermediate and then the Brislow intermediate. And if you look at the literature of carbene catalysis, in majority of the reaction, the carbene addition happens to the aldehyde, and beyond aldehyde is not well explored. However, there are few reports on the polarity reversal of Michael acceptors in addition to the aldehyde, what I have explained. So if you look at this alpha beta unsaturated ester having a bromide at the beta position tethered, so we know that this beta position is inherently electrophilic in nature, but using carbene catalysis, one can make this beta carbon nucleophilic and then displace this bromide to form this exocyclic cyclopentene derivative. This was demonstrated by Fu and co-workers. And the intermolecular version of this type of reaction was demonstrated independently by Matsuoka and Glorious group, where this CC bond formation effectively take place from via a tail-to-tail dimerization, and these reactions are proceeding via the deoxy analog of Brislow intermediate. So what we envisioned was, can we use this strategy, the polarity reversal of Michael acceptors originally demonstrated by Fu and co-workers, to the polarity reversal of a simple enone, which is known as chalcone. So a stoichiometric reaction of this chalcone with a carbene generated from this IMS hydrochloride using potassium terbutoxide resulted in the formation of this 1,2 diketones in almost 60% yield. So this reaction proceeds via the initial addition of this carbene generated from this imidazolium species to the chalcone, generating a tetrahedral intermediate, and now a proton transfer to a deoxy-Brislow intermediate. But the Brislow intermediate did not stay as such. Under basic condition using potassium terbutoxide, the enolate generation was very facile, and with the dissolved oxygen present in THF, the oxygenation or the oxidation happens at the alpha position to form a 1,2 diketone. So when we did this reaction in simply open air, the yield was slightly enhanced. So the deoxy-Brislow intermediate cannot be isolated. It spontaneously undergoes oxidation to form the dioxo compound or diketone species, which gave us a hint that the generated deoxy-Brislow intermediate is not staying as such. It is getting oxidized, or in other words, a irreversible quenching of carbenes under the reaction conditions, which gave us a hint that there is no possibility of catalysis. So with this unsuccessful effort to do catalysis using chalcone, we tried other Michael acceptors and finally came to this 1,3 diketone, the cyclic analog, the cyclopentene dione species, where the addition of carbene generated from this imidazolium salt generated the deoxy-Brislow intermediate without any oxidation at the alpha position. So the reaction proceeds via the addition of carbene to this Michael acceptor moiety to generate the tetrahedral intermediate, and then a proton transfer to form the deoxy-Brislow intermediate, which can be isolated, which can be fully characterized. We have even the crystal structure. So this Brislow intermediate generated from this diketone survives. There is no oxidation happening. That means there is a possibility of catalysis in this species, in this system. So with this interesting result, we tried a cross-coupling reaction of various isotin derivatives and 1,3 dicarbonyl systems, the Michael acceptor system, forming this oxindole derivative with very good substrate compatibility, and the products were formed in moderate to good yield. So this reaction proceeds via the addition of this thiazolium salt in a one-form fashion, generating the tetrahedral intermediate, and a proton transfer generating the deoxy-Brislow intermediate. Now the deoxy-Brislow intermediate can add to the electrophilic carbonyl of isotin, generating this alkoxide species, which undergoes the elimination of free carbene to form the oxindole derivative. At this point, we also considered the possibility of a simple Baylis-Hillman type addition. So instead of the proton transfer generating the nucleophilic deoxy-Brislow intermediate, the tetrahedral intermediate can just add to this carbonyl of isotin, generating an alkoxide intermediate, which can undergo a proton transfer and elimination of carbene to form the same product via the Baylis-Hillman pathway. However, our initial mechanistic experiment and the isolation of the free deoxy-Brislow intermediate and the reactivity using the generated deoxy-Brislow intermediate to get this oxindole derivative gave some hint that in our reaction condition, it is not the Baylis-Hillman pathway, but the deoxy-Brislow intermediate generation is more facile under the reaction condition. So initially, I told you how carbenes can be used for the polarity reversal of aldehydes, and later how one can use this for the polarity reversal of Michael acceptors. And what next? So just like aldehydes and Michael acceptors, we know that imines are also a class of very good electrophiles. And the polarity reversal from the inherent electrophilic nature of aldimines to the nucleophilic nature using carbene catalysis was not at all known when we started working in this area. So what we envisioned was to use a carbene catalysis for polarity reversal of this aldimine species. So as you can imagine, this imine carbon is inherently electrophilic. So by using carbene, if we can reverse the polarity of this imine to nucleophilic nature, it can add to the Michael acceptor moiety, forging a carbon-carbon bond to construct 2,3 disubstituted indole derivative. And if successful, this reaction should proceed via the ASA analog of Breslau intermediate. So remember, in the case of aldehyde, it is a simple Breslau intermediate. In the previous case, the Michael acceptor, it is the deoxy Breslau intermediate. And now with aldimine, we envision these reactions could proceed via the ASA analog of the Breslau intermediate. So with this idea in mind, Atanu Patra tried the optimization of reaction conditions of this aldimine, which is connected to a Michael acceptor moiety, using this N-phenyl triazole derived carbene, and we got this 2,3 disubstituted indole derivative, N unprotected indole derivative in moderate to good yield with excellent substrate compatibility. So the reaction proceeds via the generation of free carbene from the Asolium species, and the free carbene adds to this imine moiety to form the tetrahedral intermediate, and then a proton transfer leading to the generation of this deoxy Breslau intermediate, which is now nucleophilic at the imine carbon position. At this stage, we also considered the possibility of a direct carbene addition to the Michael acceptor moiety instead of the imine, which could lead to the formation of the deoxy Breslau intermediate. And this deoxy Breslau intermediate, again, it is an enamine, which could add to the imine moiety to form the same product. But our initial mechanistic experiments combined with the preliminary DFT calculations carried by my colleague from NCL, Kumar Vanka, we have enough hint that this reaction proceeds via the ASA analog of the Breslau intermediate. Once this ASA Breslau intermediate is generated, it could add to the Michael acceptor moiety, generating this enolate equivalent, and then it undergoes elimination of free carbene to form the 2,3 disubstituted indole derivative. So with this result on the synthesis, direct synthesis of 2,3 disubstituted indoles, we considered, can we extend this imine umpolung strategy beyond indole synthesis? So the idea was to synthesize a 6-membered ring starting from, again, an imine substrate, which is connected to the alpha trifluoromethyl styrene moiety. So under a modified reaction condition, Atanu was able to get this disubstituted quinoline derivative. More importantly, the 4 difluoromethylated quinoline derivatives in moderate to good yield. So the reaction proceeds via the polarity reversal of this imine moiety and this deoxy Breslau intermediate, the ASA Breslau intermediate, the ASA Breslau intermediate generated could add to this moderately poor electron carbon-carbon double bond with a fluoride elimination to form the difluoromethylated quinoline derivative. So from the very beginning, we have also considered, in addition to the imine umpolung, always we consider the possibility of the Michael acceptor umpolung. So to confirm that the imine umpolung is happening in our case, we again came up with a substrate, a bis imine substrate, formed from the condensation of the phenylene diamine with the salicylaldehyde derivative. And this case, what we are envisioning is the carbene add to one of the imine moiety generating the deoxy ASA Breslau intermediate, and then the second imine moiety will be the acceptor or the electrophile. And in this process, we could generate the dihydroquinoxylene derivative in up to 98% yield and 98% enantiomer selectivity. I should confess that this reaction works only with the salicylaldehyde derived bisimines. So simple benzaldehyde derived bisimines are reactive, but the selectivity was only in the moderate range. But with this salicylaldehyde derived species, the isolation was much easier, and the reactivity and the selectivity was also very impressive. So towards the end, I was able to tell you, or I hope I was able to tell you, the way carbenes can be used for the polarity reversal of aldimines via the generation of the nucleophilic ASA Breslau intermediate and the follow-up chemistry for the construction of wide variety of indoles, quinolines, and quinoxylene derivatives. So in the last 35 to 40 minutes, I hope I was able to give you a take-home message on the chemistry of N-heterocyclic carbenes, the application of NHCs in polarity reversal of aldehydes, Michael acceptors, and imines, and specifically for the aldehyde umpolung for the construction of CN as well as NN axially chiral molecules and axially chiral molecules with high enantiomer selectivity. So this is my most important slide. So I should thank all my extremely talented and hardworking students. So today I highlighted the work of Sauman Barik, an integrated PhD student, and he developed the CN axially chiral molecules. So the Pruva Balana, he demonstrated the NN axis axial chirality, and also some of the works of Rohan, Shilpa, and also Sayan I highlighted in the various aspects of NHC catalysis. So these are all impossible without the support from various funding agencies, starting from the startup grant from NCL Pune, the support from CSIR, the startup grant from IIT Bangalore, and most of our work is now being supported by CRB. So I should thank CRB for the continued support for various programs in our lab. And also, once again, thank you, Tebris, for inviting me for this wonderful event. And thanks a lot for your kind patience. And I will be really happy to take questions. Thank you very much.
Questions from audience?
Yes, Adi.
Hello, sir. It's very interesting talk on NHCs and organic catalysis. So my question is about the electronics of the carbenes. For which kind of carbenes are suitable for stabilization of Breslow intermediates? More electrophilic or more nucleophilic?
So generally for the Breslow intermediates, so this is based on our experience. So the simple Breslow type intermediate, the generation of the Breslow intermediate is facile with imidazole as well as thiazole and even with triazole. But generally for an acyl anion reactivity, the efficiency in terms of carbene will be for thiazole derived species. Okay, so thiazoliums are generally used for acyl anion reactivity. But if you want to have beta reactivity from alpha beta unsaturated aldehyde, where the reactivity of a carbonyl position should be shifted towards the beta position, so then we use imidazolium salt with a sterically demanding groups of nitrogen, so that the nucleophilicity from the carbonyl position will be shifted to the beta position due to sterics. So one can tune the reactivity, all this reactivity using this carbene precursor, but to answer you, the thiazole derived carbenes are best for acyl anion reactivity.
Actually, that was my second question.
Yeah.
You have used the triazoles and thiazoles as well as imidazolium salts, right, for carbene source.
Yeah.
So how do you choose which salts are suitable for particular reactions? So I can see a lot of all these salts you have used.
Yeah.
And you have generated the carbene in situ, right, by using mild basis, for example.
So as of now, to my knowledge, there is no report which predicts which carbene is suitable for which reactivity. But we only have a feel about which type of carbene can be utilized for a given reaction. Just like, as I said, an acyl anion reaction, we use generally thiazole derived carbene. So if we want to try an acyl anion reaction, a Stetter reaction, we start with thiazole. We find some reactivity, but then we have to screen all the imidazolium and triazolium carbenes to get the optimized reaction conditions. So to my knowledge, there is no shortcut. We have to screen all the reaction conditions.
Last one.
Yeah.
You know, there is one set of carbenes. Those are cyclic alkyl amino carbenes. The SCAC carbenes.
Yeah.
Are you doing anything?
The Adungo type. Sorry, not the Bertrand type.
Yeah, Bertrand type. Yeah. 5 angiones.
So the Bertrand type carbenes are nucleophilic enough, but so far it is not known for catalysis. This is a good ligand for metal catalyst, but organocatalysis using Bertrand type systems are not well known. Yeah. They are relatively, the nucleophilicity compared to an imidazole is, so the CAC carbenes are relatively less nucleophilic. Yeah. Yeah.
Yeah, next, Shantanu wants.
Hello, sir. Sir.
Yeah, Shantanu, you can tell.
Oh.
I'll start with you. Just one question. I don't know if they can go to slide 11. Can you press 11 and enter?
I can probably move.
It will take a long time. Anyway, so I think in the third-butyl substituted maleimide, I think the nucleophilic addition, the enhancer selectivity that you were talking about, I think it does not come from the phase selectivity. It comes from the site selectivity.
Which number slide?
11. Right.
Yeah.
So if you where you are seeing that the two atropotopic phases, because the top phase is already blocked by the tertiary butyl group. If you have an N-phenyl maleimide, in that case you have to worry about both the phase selectivity and the site selectivity. And it is actually the diagonally opposite phases give the same enantiomer.
Yeah.
In this case, the top phase is completely blocked. So therefore the phase selectivity you can take out of the equation.
Yeah, but top phase is blocked, but the bottom phase is still accessible,
So
right?
that's what I'm telling. So now the enhancer selectivity is basically dictated by whether addition will happen at CA or CB. Okay, so that's basically site selectivity now. Now it is no longer phase selective.
But for CA, this the Breslow intermediate cannot add because this amino internal core is
So it is controlling it.
Yeah.
Your Breslow intermediate, which is bound to the chiral carbene, that is now controlling the site selectivity.
Yes.
Not the phase selectivity anymore.
Okay.
Okay, because between A and B now.
I understand.
Otherwise, like here and here, that gives one enantiomer, and the other two gives other enantiomer.
Absolutely.
So now that you have broken one symmetry element, the phase selectivity is no longer of consideration.
Yeah, I understand what you're saying.
Yeah. Thanks.
Hello, sir. I have a question. Yeah.
Oh, yeah. Please.
Yeah, it's nice hearing your talk. Regarding reversal of the polarity of ketone, aldehyde, or imine. So, if you consider the overall reaction, which step do you think would be the rate determining step, you can say, or which is the control the overall rate of reaction?
So we have not tried the kinetics of this reaction per se, but we have a feel that in some of these reactions, say like the Stetter-Aldol cascade, so the generation of the Breslow intermediate, so from the tetrahedral intermediate to the Breslow intermediate, this is known by Rovis and Kovacek. So the key proton transfer event is a slow step in that reaction. But specifically in our case, we did not do a detailed study.
Okay, sir. Thank you.
Dr. Barna?
Yes. Sir, my question, can you show me the third slide? Slide number 3.
Third, okay.
Yeah. Next.
Yeah.
Next. This one. So my question is, when the Breslow intermediate we are talking about, so is there any specific solvent, polar, aprotic, protic, like in which solvent the intermediate is more stable?
So this we cannot tell for sure, but I can tell you for the Berkesel's isolation, these reactions are mainly done in ether solvents, either in tetrahydrofuran or dioxane as a solvent.
Like in dry condition?
Sorry?
In dry condition or like normal?
Yeah, so in the carbene, the Breslow intermediate generation was done in THF and in some cases dioxane as solvent.
Okay. And
yeah, generally people do carbene catalysis in ether solvents. So that's better for the solubility of the substrate as well as the generation of carbenes in solution.
Okay. And we are talking about the like polarity reverse, like of the aldehyde or like carbonyl compound.
Yeah.
So there's various reactions of carbonyl compounds, like the Claisen can
not
be
carbonyls, aldehydes.
Like
specifically.
Specifically
yeah.
aldehydes.
You cannot do this for ketone.
Yeah.
The proton transfer will not happen, right?
So for different aldehyde related reactions, we also can try this out, like this catalysis.
Yes.
Okay.
That is known with, so once a an optimal condition is reached with a given aldehyde, people usually screen various aldehydes, like such as aliphatic aldehydes, heterocyclic aldehydes, aromatic aldehydes. So yeah, most of the aldehydes will work.
Thank you, sir. Thank you so much.
Please pass the mic to Dr. Barla this side. Excuse me.
Yes.
It was a nice talk, lot of application. So I just have a curiosity based. You have studied temperature versus chirality, right?
Mm-hmm.
So you are heating the sample and bringing it room temperature and measuring HPLC or kind of.
So you what we do is we did several parallel experiments. Okay. So just take the given constant or given concentration of this compound in toluene, and the first reaction mixture we check the selectivity after 10 minutes, 20 minutes. So with respect to temperature, with respect to, at a given temperature, with respect to time, we monitor the change in selectivity. And we found that up to 90 degrees Celsius, the CN axis is stable, that E is unchanged.
When you cross the time.
When we go beyond 90, we see that the E is dropping. That means the CN axis or CN bond can rotate. And at around 150 is almost racemic. That means it is free to rotate.
Yeah.
Thank you.
Dr.
Yeah, Viplav.
Hi.
It's here.
Excellent. Yeah, excellent talk. Okay. So actually, I have a curiosity for a long time. These deoxy-based intermediates. So if you look into those, so those are structurally very closely similar to phosphorus elite or the sulfur elite, right? You have a C minus and a imidazolium plus. Consider that, right?
Yeah.
Yeah. So why not having, let's say, cyclopropanation reaction or epoxidation
with the Brislow?
With the deoxy Brislows. These are like same as that of phosphorus elite or the sulfur elite.
So the deoxy Brislow, what to my knowledge, the reactivity of the deoxy Brislow is far less compared to the simple Brislow. Okay, so but specifically the cyclopropanation, what you are telling, it is still unknown to my knowledge. But which type of Michael acceptor you are thinking about? Is typical acrylate or? Yeah, chalcone, we already found that the deoxy Brislow will rapidly oxidize. So we even tried with a mild base like potassium carbonate, but we could not get any hint of the deoxy Brislow. It is oxidizing. But the 1,3-diketone, what we have tried, there the Brislow intermediate is isolable, the deoxy. We have not tried it. Yeah, that's a good. But I think it is still unknown. Yeah. Yeah, Peru.
It's just a curious question.
Yeah.
Epoxide with your carbene.
Carbene addition to epoxides are known. Yeah. The adducts are known, the epoxide adducts of carbenes. Just the stoichiometric addition of carbenes to epoxide.
Don't generate the acetaldehyde enolate.
No, to my knowledge. Acetal.
It's like enolate. It's 2 carbon fragment. It's for to open up, you have O minus. Again, the other hydrogen can transfer. Right? Or maybe aziridine. Either one.
Yeah, but there's 1 or 2 reports on the carbene adducts of epoxide, but there is nothing known with the catalysis. So what you essentially need is at the end the carbene will come out and it is a catalysis. So just like cyclopropanation reaction, what you. But I think it is still unknown. So yeah, maybe because this carbene will irreversibly bind to the epoxide, so then that adduct will be relatively stable. So we may not get any catalytic reactivity. That could be one reason, but we have not tried it.
Thank you.
Yeah.
Maybe
I think one question would be, since the talk was done quickly, so we are having enough time for questions.
Okay, yeah.
Good afternoon, sir. Thank you for this nice talk. So I wanted to ask that when we are reacting some intermolecular reaction where when we are choosing two substrate, so based on previous literatures, both of them has been reacted with some other compound, but when we are taking the two compounds together, sometimes they don't react as we wanted. So how to get a previous idea that these two compounds will react or not?
Yeah, so what we generally do is we look into the literature and see the closest precedence to the reaction what we are trying. Okay, and then we pick that particular, say, pick the same carbene catalyzed reaction condition. So in our CN axial chirality, so we started with a literature report. So there is a JOC paper, and we started with that particular reaction. And then we got some result, and then we tried the reaction again with our maleimide system, with the new system. And then followed by the change of carbene precursor from an achiral one, which is reported. And in our case, it is our interest is a chiral carbene. So we always start from the closely related report from the literature to see whether there is a first hint of reactivity, and all start from there.
Thank you, sir.
Okay. So I have one question.
Yeah.
So I saw in one of the catalysis you have used that hydroxy carbene. Hydroxy is there.
Thiazole, that is vitamin B, commercially available carbene, the thiazole derived
So
carbene.
it is just for the solubility purpose, or what is the role of that?
Commercial availability.
Commercial.
Hydroxyethyl, right?
Yeah.
Commercially available.
Another case where you use that azo with that in 23rd slide or somewhere. So there was one methyl group also. If you don't have that methyl group, what will happen? I mean, that heterocycle. The heterocycle as a precursor which you took.
Methyl. What is that slide?
Around 20. After this.
Yeah.
Next one, the heterocycle one. This here. So you have that methyl.
Yeah.
So what happens?
So this group at this position is important to restrict the C's N and rotation. We can vary this methyl with the aromatic systems and with ethyl also. We did not try much, but we tried with free and CH, but then the selectivity was only moderate. Yeah.
Okay.
The group at this position is important.
Okay. So let's thank Professor Biju for this excellent talk. And
thank you.
Let's honor him with a moment.
I would like to request the session chair, Professor P.C. Ravi Kumar, to felicitate Professor Biju for this insightful lecture. I now request Dr. Vijay Krishna Kari to felicitate Professor P.C. Ravi Kumar for chairing this session. I believe we have gathered great insights from the lectures of Professor Bisai and Professor Biju. I wish to extend my gratitude to them and to you for your zealous participation. We will now break for a blue ocean tea break, which I'm sure will keep us zestful for the session ahead. I invite you to kindly take your tea and reassemble in the hall by 3:55 p.m. sharp. Thank you for your active participation in the session.
Just try.
Yes, yes, yes.
Hello, if anyone lost their phone, please collect it from the backstage. Someone had kept their phone near the water cooler. If anyone lost their phone, please collect it from the backstage.
ring further induces electrophilicity in the system, probably that accelerates reaction. But these last three examples are the ones having beta disubstituted systems. But this provided, at least we could provide a solution to something that was long standing, at least at that point of time. Now coming to, obviously you may be wondering, what is this HFIP doing? You've done so many reactions, so many solvents, but what is that all of a sudden you got HFIP working for you? So for this, we took help from my colleague, Dr. Balnarayan, who was a computational chemist. So what Dr. Balnarayan did, he came up with a model substrate. Of course, he took the substrate, he took the model catalyst. You can see that this is a truncated version of the original catalyst. Of course, this is to save time, computational time. Otherwise, you should not think that pH2 works. It won't work in reality. I mean, in experimental system. And he modeled the reaction conditions and came up with an interesting proposition, which of course we haven't thought at that point of time, that the HFIP has a dual role, not just activating or coordinating the catalyst, it also activating the electrophilic aldehydic component here, and thereby it is bringing together in a synergistic fashion both reactant, catalyst, and HFIP, forming a nice consolidated network. That eventually gave access to the desired product that we have seen. Of course, these further details can be accessed from this particular paper if some of you are interested, but just wanted to showcase what this HFIP was doing. Eventually, what we have done, we extended the scope of this work to dienones also. Just as you saw last slide, it is enone aldehydes. We have also extended. Of course, it's a trivial extension of the earlier work that we have done. See, the dienone aldehydes and ketones also worked, and we got the respective products in good yields and similar enhanced selectivities that we saw in the earlier case. But what is important in this particular instance is when we referred to this particular paper in RSA Advances review work, what was demonstrated till then, till about 2016, is a consolidated, this review consolidated the developments in the Bailey-Silman chemistry that indicated there was no reaction observed as long as the dienones were or dienylic substrates of this kind, or this kind were employed. Only this kind of substrate worked in those instances, but you can see in our case that variety of substituted dienones also work, bearing different electronic and sterically diverse substituents. That highlights the importance of this particular work. But this also led to another question or another hypothesis. What is the source of that hypothesis? If you see carefully, what happens here is that this catalyst, this bifunctional catalyst involving a Lewis base and Lewis acidic site, okay, activates the substrate in this fashion that it undergoes 1,6 addition that leads to the generation of this dienolate. And the product formed because it attacked, the enolate attacked from the alpha position. That's why you got that product, okay? But we never observed a product coming from the gamma position. That dienolate addition leading from the gamma position was something we never observed. That would have given us access to this. Of course, this can be understood. This is a kinetically driven product formation. That is what this particular product, or these are the kind of products. But our intention was, can we switch the selectivity? Can we introduce divergence in this system? That is, when you don't have substitution at this position, this is the product you get. For example, if I introduce a substitution and block the alpha position, if you block the alpha position, Bailey-Silman chemistry should not work because it forms a new bond at the alpha position. It leads to pentavalent carbon, so it won't be feasible. So that's why we thought that if you introduce a substituent at this position, it should not encourage anymore the alpha attack. It should now possibly drive the reaction to the gamma attack, leading to the product that we anticipated, as I showed in the last slide. Possibly that we should be able to get this. Accordingly, we made the substrate, and when we actually performed the reaction with the alpha blocked dienone, we got this product. Still, we got that product originating from the alpha attack. But you see interestingly that this now represents a reductive aldol reaction. This is a different reaction now. So we started from a Bailey-Silman reaction. We just modified the substrate to accomplish a gamma addition, but it led to still alpha addition, leading to what is so-called a reductive aldol product. Of course, we found some significant features associated with this particular transformation that are written here, that substituted dienes were never employed in a reductive aldol process. And this also creates two stereogenic centers, as you see, contiguous stereogenic centers, one of them being a quaternary, all-carbon quaternary center. Of course, it showed significant scope as of the reactants are concerned. A variety of arenes, heteroarenes across the dienone moiety, different substituents across R1, R2, R3 can be, tolerated. That's what we realized. And even with the heteroarene backbones, you see, such as pyridine or benzothiophene kind of moieties were also well tolerated under reaction conditions. Of course, in this instance, our efforts to develop a chiral version were not successful, but nevertheless, we went ahead with this particular version, and we then moved on. Mechanism is especially important. Okay, as I talked to you, reductive aldol reaction. Reductive aldol reaction, that indicates to you when the substrate has reduced, something must have been oxidized. Okay, we now wanted to see what got oxidized versus how it got oxidized, and by the way, where from it is getting reduced. These are the questions, obviously, right? For that, first of all, I need to convince you whether it undergoes 1,4 addition or 1,6 addition. I showed you in my hypothesis that phosphine undergoes 1,6 addition. This is a proof, sort of a proof that we realized when we made selectively this Z double bond, that is 6:1 selective Z double bond here, and subjected in the product, we got that homogenized, and we got E product, possibly indicating that, of course, a thermal isomerization can never be ruled out, but still, at least under the reaction conditions, this is what, because this was done at room temperature, so most likely indicating that the phosphine addition undergoing 1,6 addition and eventual aldol, Michael aldol reaction, that is what giving the product. Okay, next. What is the source of the hydrogen that was responsible for this reduction of the substrate? For that, we have performed a reaction in D2O. We identified that these two positions, which were marked in blue, were enriched with deuterium, as the numbers are indicated there. Okay, that is one observation, important observation we made. When we have performed the reaction with oxygen-labeled water, O18 water, that we identified that the phosphine got that oxygen. That means now it tells you somewhat that phosphine is the one that got oxidized, and that's eventually introduced reduction in the product. Okay, how this happened eventually? We believe that phosphine now undergoes 1,6 addition followed by intermolecular aldol, giving you this particular deuterionic species. Now water takes this anion, takes this proton, and the resulting hydroxide eliminates phosphine and generates that allylic anion, right? And that allylic anion is now what was responsible for extracting proton from water or D2O that you have. In fact, that's the reason that you have got deuterium at these two positions, just as these two. That eventually explains how the product form. Of course, this can happen in two pathways, either direct protonation followed by 1,3 proton shift or direct protonation. This was how we could be able to convince the mechanism. We also extended the synthetic utility of the products that we got. As you see here, what we have done, we took these products and treated with osmium tetroxide and oxone. We got these butyrolactone derivatives. This, of course, this method, these reaction conditions were adopted from this Borhen's paper. Okay, we also extended the scope of this substrates, that is the products, I mean to say, the adducts, reductive aldol adducts. We just when treated with boron trifluoroethyrate, we got the endocyclization occurring, and we got these products. This was confirmed. This is part of showcasing the further synthetic utility of these products, that is reductive aldol products. Okay, what you have seen is the reductive aldol reaction. We started with alpha blocked dienone aldehydes, giving access to reductive aldol products. Okay, while we were pursuing some other reactions, especially involving alpha blocked enones and dienones, we realized something more interesting. That is what is here. When we have actually performed this alpha blocked enone having gamma protons available. You see carefully the difference. Gamma protons available here under phosphine conditions gave another interesting product. This is, of course, not even reductive aldol product. Okay, if you see carefully, overall transformation is actually vinylogous aldol reaction. Okay, this is a vinylogous aldol reaction. That means you are generating aldol initiating from this position. That is what is called this vinylogous aldol product. Okay, how this happens and what is the significance associated with it. Okay, as soon as you see the structure, you can obviously take the significance of these products in this particular form, that this creates one alpha-carbon quaternary center, of course, obviously two contiguous centers, of course, whatever we can talk of. But what is more important is the mechanism. What we believe happened in this particular case is that whenever there was gamma protons available, phosphine undergoes Michael addition, just as the Bailey-Silvan type reaction that happens, and subsequent aldol reaction, that is alpha aldol reaction, that is alpha aldol, I mean to say reaction occurring from this position, giving access to this zirconic species. Now because this cannot now undergo elimination, the phosphine cannot undergo elimination as such, and this alcohol also cannot undergo elimination. And now this alkoxide undergoes proton shift from this position, as you see here, from this position. This is more acidic now, right? Because it's connected to a phosphonium center, and that leads to obviously the stabilizing force is the formation of the ylide. This ylide subsequently reacts with moisture present in the reaction medium, and this anionic species takes proton, and that resulting hydroxide takes proton from here. That facilitates the elimination of phosphine, and that is what we got the vinylogous aldol product. Okay, of course, the gamma aldol product again was not observed in this case, which we of course wanted to a certain extent, because that can give access to heptane fused systems, but we didn't get that. We didn't observe it at any point of time. This is the scope. You can see interesting scaffolds can be accessed, especially that creating two contiguous centers with a quaternary carbon incorporated, more importantly establishing reductive aldol process, or in this case it is vinylogous aldol process under catalytic conditions. You see the reaction conditions, so simple. Just you take this substrate, add catalytic amount of phosphine such as tributyl phosphine, and you get the products such as this, and different. Even you can see that beta disubstituted systems also were considered. One reviewer asked, every time you have gamma protons available, so probably it is taking proton. Of course, phosphine as such were not known to be Bronsted bases, but to prove that case, we took a substrate with diphenyl substrate, and even that worked in a different fashion. Of course, that leads to a different product. Of course, that doesn't give you this product. Eventually, we could prove that it's not going through the dienolate through the deuterium incorporation experiments as well. Here, we have shown some interesting synthetic elaborations. If you see carefully how you can extend the scope of this work, let me tell you, some of these we didn't plan at all. Some of them, in fact, not some of them, most of them were serendipitous. We just tried to get to showcase the synthetic utility. We got into something else. For example, here you see we got the vinylogous aldol product. We added vinyl grignard, and we got this particular product. Of course, not isolated. These quite unstable compounds. This, when treated with potassium hydride, it underwent a oxycope rearrangement, leading to ring expansion up to 9-membered rings. So this was found to be quite general. Of course, one can have questions of the relative stereochemistry that I've shown here. They can be conveniently explained by these models that I've shown. Even the oxycope rearrangement leading to the relative stereochemistry that I've shown here also can be explained by this. Maybe if I have time, I'll get back to that. Or if you're clear, that's good. Nevertheless, this is the scope of this particular work. It is a 9-membered, arene heteroarene fused systems are quite rare in the literature. This is something that can be easily accessed through this particular work. Just as we have performed this reaction under basic conditions, I also asked the student, just see what happens to these compounds under acidic conditions, because you have alcohol here, possibly if at all that alcohol eliminates, generates benzylic cation, that may induce some rearrangements. That was the idea. Okay, that interestingly something else happened. You see here, what Uttam did in this case is he took this substrate and added vinyl magnesium bromide, got this alcohol. When treated, of course, this was not isolated, of course, straight away when treated with the catalytic amount of PTSA, we got this particular product. Don't think that there is a benzene ring. This bond is not there actually. So there's a triene we got. Okay, how that triene forms, as you see here, the proton, we believe that the PTSA activates this alcohol, that is the tertiary alcohol, especially that it's being benzylic and allylic in nature. That undergoes now fragmentation leading to the triene moiety. We subsequently could further cyclize this triene to biaryls also, but that won't be so appealing because to access biaryls, there are easier methods than going through this particular longer route. This was found to be reasonably general. We added vinyl grignard, we added phenyllithium, you got the respective product. We added phenyl magnesium, we got the respective product. Okay, in the similar fashion that you see here. But when we added methyl grignard and subjected that to PTSA conditions, we got simple elimination. It didn't undergo the fragmentation that you saw in the other three cases. That is, of course, again, another surprise we got. Okay. What you've seen so far, of course, I'm not summarizing yet. A Bailey-Silvan reaction leading to this particular kind of substrates. And on the other hand, I haven't talked about this work, but in line with enone aldehydes reacting, we one day thought what can happen with inones as reactants under phosphine catalyzed conditions. We actually, interestingly, we saw a gamma CH functionalization happening under simple conditions. You see that we obtained variety of cyclopentenone fused arenes and heteroarenes. With this proposition, we questioned one day, just as the inone is able to activate the gamma position, that means the initially formed anion or elinoate that can form possibly can also react with aldehyde, can lead to potentially some useful products. But what is important, if you see carefully the substrate, this cannot form any bond unlike Bailey-Silvan reaction because there's already a triple bond here, right? So if it is a double bond, there is a possibility of formation of this kind of products. But once you have a triple bond, products such as this cannot form because phosphine has no means of elimination. So we don't know, I mean, what potentially can happen, but it was out of the interest of that particular student, Atanu, for example. They actually took this substrate and subjected this phosphine. Interestingly, this is what happened. This is again, we haven't expected at all. At no point we expected. Even when we got the product, we were unable to believe whether we got right product or by chance some aerobic oxidations or something else happening leading to these particular products. But if you see carefully, this effectively the reaction that involves intramolecular hydroacylation. Right. So how it is the inone underwent acylation on one and hydrogen added at the other end. So effectively, our overall this is what is a hydroacylation process. This was something achieved under metal-free conditions. Usually, hydroacylation of alkynes typically you can refer to literature achieved under metal conditions. Okay, this is something an exception. That's what you see here. Of course, one can definitely argue that this doesn't require this many steps to prepare. Yes, we agree, but this is a concept that we established again. Okay, this mechanism can be explained in the following fashion. This can be explained in two ways. One, considering the proton shift, also considering the hydrate shift as the first step. You see, for example, phosphine. Now I'm showing you the mechanism involving initial proton shift. Phosphine attacks in a Michael fashion or 1,4 addition it undergoes, and followed by aldol addition gives this vitrionic species, right? Now this undergoes 1,2 proton shift leading to this anionic system that eventually isomerizes to this ylide. Another proton transfer, that is this proton undergoing transfer here, and subsequently it undergoes elimination in this fashion shown, gives access to this. That's what the proton induced or proton involving proton transfer mechanism. This can, in fact, our original proposition was a hydrate transfer mechanism, but reviewers somehow were not in favor of it because this reaction works even in water. Reaction works in water. So they started questioning when reaction is working in water, how you can propose hydrate transfer. So came up with this proton transfer mechanism, but this is another possibility. Of course, we don't have any evidence whether it is proton transfer, hydrate transfer. We didn't conduct any computational work or whatsoever. But you see the difference here is that this involves hydrate shift followed by proton transfer and eventual phosphine elimination. Yeah, this was also extended to forming 7-membered cycles, as you see here. And even this is another piece of extension that we achieved using this particular protocol. Just in the earlier case that you have seen, sorry. Yeah, here you see that it is inone aldehydes. When we use Enone ketones, we see a different product. We actually expected this product, but this is what formed 8-member ring formation. The mechanism is explained here. Maybe already the chair is standing, waiting for me to conclude. Maybe I'll be a little quick now. But otherwise, can you give me 5 more? How much time I have? Can you please tell me? It is 45 minutes talk. Okay. I'll be a little quicker. Or I'll skip some of the slides. Sorry for, I think I'm still a little bit more to go. Yeah, otherwise, let me present to you another concept that we have got into. This is what you have seen, that enone aldehydes giving the Belli-Silman product. We questioned one day because double bonds and cyclopropanes are considered chemically, to a certain extent, electronically equivalent. So we thought, what about replacing the double bond with the cyclopropane? What will happen under phosphine conditions? Okay, so to that, we need to prepare the desired starting compound, obviously, right? This is the desired starting compound to evaluate the hypothesis, right? To that, what Uttam has done here, Uttam, the first author here, so what he has done, he took a shortcut. He didn't inform me. Of course, starting compound synthesis is something no need to consult your supervisor. You can design your own way of accessing the starting compound. What he has done to get it so quick, he has taken this enone aldehyde. He thought that treating this with Korsakoffsky reagent, you will get this product. That was his idea. But what happened? This is what formed. Okay, so you can see how complicated structure that it generated. Okay, completely unexpected, and that's what happened. And you can see that what happens here. I'll just explain the mechanism. The ylid, that is Korsakoffsky ylid, the anion adds here to the aldehyde, forms this zwitterionic species. This undergoes 1,3 proton shift, forming this stable intermediate that undergoes a Michael addition followed by intramolecular displacement of DMSO to give access to these particular compounds. Okay, this is quite general. You can see works with arenes and heteroarene backbones, and we also extended the synthetic utility of it, subjecting this to lithium liquidomer conditions. We accessed breaking this cyclopropane, accessed transfused, 1,2 trans endonones. Eventually, what you have seen last slide is the enone ketones, enone aldehydes. Enone ketones give you different products again, you see. This is enone ketones. Now the ylid doesn't undergo 1,2 addition unlike aldehydes. Now it undergoes Michael addition, and then aldol gives this one, 1,3 proton shift gives, and eventually DMS elimination, the spirocyclopropane structures. Okay, this also was found to be quite general, you can see. And this also, maybe I'll skip the extension of this work, but we subsequently demonstrated the scope of this work in desymmetrization. So you saw in the last 2 slides, enone aldehydes we took, what we got a different product, enone ketones gave a different product. Now enone enones give again another different product. You can see a mechanism I'm skipping, but you can see the diversity that you can achieve through this protocol. Very interesting because Korsakoffsky reagent is something that is typically used for cyclopropionation or epoxidation of olefins or carbonates, but none of them happen in this case, but leads to these complex scaffolds. By the way, I forgot to deal with this, that what happens, by the way, if you take cyclopropyl ketones and phosphine reactions. Maybe I'll skip this, what Danishevsky has told way back, that cyclopropyl ketones won't react just like that. It needs dual activation, unlike olefins that react in a different fashion. Because we are now considering olefins and cyclopropanes equivalent. Olefins can react if in a Michael fashion, but not the cyclopropanes that you have, but it requires minimum 2 activating groups such as this. Danishevsky in 1975 has used Lewis bases to access such compounds. By the way, with the closest report we can find matching our hypothesis was this in 1987. The cyclopropyl ketone was treated with phosphine at 120 degrees, giving access to this particular substrate. What is more important is this particular intermediate that attracted our attention. So can we, rather than killing this enolate with HBr leading to this one, can we utilize this in a 3+2 cycloaddition manner so that gives access to interesting scaffolds such as what I've shown here? So this was the hypothesis. Phosphine reacts in this fashion. It can react the way that I was shown here and potentially give access to such compounds. But that is another way that this kind of compounds can be achieved. When we actually, let me actually take to the real story. This is what we made eventually by protecting it now. Earlier we didn't protect, Uttam didn't protect it and you got a different result. Now we protected the aldehyde aldehyde, and we actually made this substrate. When treated with phosphine in DMSO, we got this product, not this expected one. This is another surprise. But more surprise is upcoming. That is, this reaction works even without phosphine. Okay, that you take this one, heat it in DMSO, you get this product. In fact, that's what you can see. It showcased extensive range of generality, and of course I'll skip this. But when you substitute with a substituent at this position, that is alpha position, you get different products again. These are something resembling to you the vinylogous products or reductive aldol products. Okay, and this is the other types of products we got with cyclopropyl ketones leading to such stuff. This is about mechanism. If you allow me 2 more minutes, I'll just talk about the mechanism. That you can see we have performed reaction with O18 labeled water. We see no oxygen incorporation because you see the product, there is extra oxygen or OH here. This oxygen was not coming from water. This oxygen was not coming from this aldehydic oxygen also. We have labeled this, and we don't see oxygen 18 in the product. But when we treated only with DMSO, we see the product most likely indicating that the oxygen is coming from DMSO. And in fact, through other experiments, we realized that the oxygen is actually coming from DMSO, and this is the proposed mechanism. DMSO is actually facilitating the ring opening of the cyclopropane, eventual proton transfers, giving access to this kind of substrate as shown here. Maybe I'll skip the mechanism part. If you are interested, maybe I'll talk about it a little later. But otherwise, this is to summarize. What I've shown was to demonstrate the utility of phosphines in various transformations. Some of them are listed here. I also showcased how we entered the sulfur-related chemistry accidentally, and you have seen that the variety of scaffolds can be accessed through this particular chemistry. Actually, I should let you also know, actually these compounds were of interest to someone pharmaceutical company. They actually pay us 100 euros per compound, per molecule of such structures, because the compounds are known in nature. So we actually sold some of these samples to them. But these are the ones actually I should thank. I'm standing here on their behalf. The ones that are highlighted in red are the real contributors. Started with Vishnu, then taken over by Uttam and Atanu. Lona, who is here, is actually now writing thesis. But otherwise, they are the ones actually contributed to this chemistry. This is my current group. Let me thank the funding agencies for the support, especially IISER Mohali, of course, SARB. Thank you very much for your kind attention. I'm really sorry for taking more time. Sorry for that.
Thank you, Sam Ramasastri. Yeah. So we'll have some quick questions from audience.
Fantastic. I mean, phosphines are amazing. So you are showing another dimension of that. Regarding your reductive aldol reaction, can you completely rule out the possibility of 1,4, because the mechanism, whatever.
No, we can't rule out.
Yeah,
because we got some evidence in favor of, I told at that point, we got some evidence in favor of 1,6, but we can't rule out 1,4.
Yeah, because that allyl anion that you generate, that can happen from.
Yes, even proton shifts can happen and leading to the same intermediate.
Right. I mean,
yes.
You can expect, I mean, there are two conflicting ways, like 1,6, you are talking about a reduced electrophilicity. On the other hand, if you think about the corresponding intermediate, from 1,6 that will be more stable compared to the 1,4. So, I mean, it can go either way.
Right.
So
I agree.
Hard to figure out,
yes. Okay. Yeah. Because only one evidence we got that I showed when we purposefully made a cis olefin, Z olefin. Right. That is only evidence we have.
Actually, even then, that case also I had a question, like your reactions are like 35 hours or something. Let's say if you stop it in between, if you recover the starting material, does it remain still E or
yes.
It isomerizes?
Yes, yes.
It isomerizes?
No, it doesn't isomerize. It doesn't isomerize. But what happens during isolation, we see it may be isomerizing.
Yeah, because it is known that if you take a Z enone, for example, if you treat with phosphine catalytic amount.
Very well, even light can do that.
Yeah. No, I mean with phosphine, phosphine particularly, light you do that for a different mechanism, but addition elimination gives you E, that is known.
Right.
So,
but in this case, until reaction was over, we're sure that Z was Z. But after that, you need to isolate. You need to obviously, during column chromatography, distillation, purification, you need to subject to various processes. It would have isomerized during that. Wouldn't rule out. that we responded to. In fact, same question was asked by reviewer, we responded in that fashion. This is the minimum evidence that we can get. After that, what happens is not in our hands.
Right.
Yeah.
Thanks.
Yeah, thank you.
Any more questions from the audience? Yes. There is one.
Sir, presentation was very good.
Thank you.
Sir, at the place of phosphorus and nitrogen, tertiary phosphorus and nitrogen, can we use DAPCO?
Of course, of course. But many of the reactions don't work with the nitrogen-based Lewis basis. DAPCO, not many reactions. Many of them, whatever I've shown, don't work with DAPCO kind of reagents.
Why, sir? It will also show one.
Yeah, because phosphines are more nucleophilic. That is the only understanding that we have. Phosphine more nucleophilic compared to amines such as DAPCO that you're talking of.
Yeah, Biplapi had a question, right?
Hi, Anand. Excellent talk.
Thank you.
So in first few slides, so when you are forming this exocyclic double bond,
right.
So for unsymmetrical system, I've seen that aryl is actually pointing trans to ketone. Aryl methyl, phenyl methyl, so aryl is actually pointing trans.
Okay. Pointing trans to hydroxy group?
Trans to the keto group, carbonyl. So, no, aryl was trans to that.
Trans to ketone, of course, because of the interaction of that position will be occupied with the phosphine of the interaction with the oxygen.
So this stereocenter is generated during the elimination of the phosphine.
Right, exactly. Because till then, phosphine and this oxygen.
Draw and see. Okay.
Yeah, till then the phosphine and oxygen will be in complexing form. In fact, several intermediate have shown that interaction. So that position, that cis position is occupied by the phosphine. During elimination, obviously your aryl ring is opposite to whatever the olefin that we are generating.
Yeah, rest of the, I think there is no other query. And I wish I could give some more time, but
maybe last question.
Yeah, last question I can take it. Yeah, please, go ahead.
Sorry.
Thank you, sir. Nice talk. Sir, I have one doubt, like in slide number 8 or 9, you talk about the Lewis acid and Lewis base, and you use a thiourea type catalyst. So is that the catalyst is only for the activation of the center or any proton like hydrate transfer?
No, it is, we believe it is hydrogen bond mediated activation, not proton transfer.
Like it is a donor acceptor type.
Exactly. Yes, that's why I call that a Lewis acid, not Bronsted acid. Yeah. Sorry for
thank you. So
yeah.
for
Thank
a lot of insight, mechanistic, really interesting
Thank
talk. Felicitate with your memento by the organizing committee member. Yeah.
Thank you very much. Sorry to take more time.
Next speaker of the last speaker of the day, Dr. Prasenjit Mal, and he is also a versatile organic chemist. He did his PhD from IIT Kanpur in 1999. Then he went to he worked in a group of Michael Smeaton, and then he joined in the same group as a Humboldt Fellow from 2006 to 2008. Then he was a Marie Curie Fellow, and since 2009 onwards, he is associated with the NICER initially as assistant professor and now in the associate professor. And he worked in various aspects of the organic chemistry. You can see here they put a fly, it's actually having a 6 leg, but it is even it can be even more than a spider, at least 8 legs. Okay, so he works in the various aspects of the organic chemistry like catalysis, supramolecular chemistry, photophysical chemistry, crystallography, and he will be presenting his talk today on the supramolecular catalysis in organic synthesis. Prasenjit, I invite you for the talk.
Just checking whether it was working or not. All right. Yes, all right. Okay. So since morning you have been experiencing a lot of organic electrocatalysis and sustainable synthesis, but this term probably little bit unfamiliar with most of the audience. So this supramolecular catalysis is not an well-defined term. The people like me, whichever way it likes, they give some kind of definitions. Okay. So, but there are people who talks about that the chemical reactions controlled by weak interactions or supramolecular interactions can also be defined as supramolecular catalysis. So we are just going to talk about supramolecular approach, what we think, because by birth I'm a supramolecular chemist. Of course, that means I did my postdoc PhDs in supramolecular chemistry. So if you just look at these are two playing cards, if you place them on a table, of course it doesn't mean anything. But if you place them in a proper orientation, that means you can get a structure. You've taken another card, you replace one of the arm, so you get another architecture, and ultimately what you can do that it is possible to build up a certain supramolecular architecture. Now, so in molecular level, so we basically use various weak interactions, and all of your, this is my fault. Okay, hopefully it's not my fault. Anyway, so that various weak interactions that, if you have seen the slide, if you recall, that means you can see that various weak interactions like, like these are ion dipole interactions, are this kind of various weak interactions we use to make molecule and molecular architectures. So another kind of interactions, or I don't know how you term it, that kind of mechanically interlocked molecule, but here there is no bonds exist, but hopefully I do not have slides for today to talk about some kind of mechanically interlocked molecule. But in supramolecular chemistry, the 2016 Nobel Prize has been given to the Stoddard or J.P. Savage or Ben Peringa. But in this, the term, as I talk in the very the beginning, the supramolecular catalysis, this is also one of the aspects. For example, just take a very simple molecule, this one, that if you just want to do a kind of 2+2 cycloaddition, this reactions, there can be various molecule. But if you just take a kind of molecular flask, and this is prepared by Makoto Fujita, and therefore it is also possible by confining them in a molecular flask, it is possible to synthesize a kind of particular architecture or molecule. So like the way this is one of the work given by Kenneth Raymond, that this is a kind of a supramolecular cage molecule. In this cage molecule, the most important part here that they could do an acid hydrolysis, that means this kind of acid hydrolysis of this diethyl alkyl orthoformate in an alkaline medium. Because outside the cage, it is alkaline, and if you treat with acids, it is possible that such kind of very nice concept. Another way, of course, I'm not going in details, but here are cavity directed cell synthesis, just now I talked about. There are possible that, stabilizing very reactive intermediates, cyclobutadiene, and also this is one of the work, when I did when I was a postdoc, that stabilizing what phosphorus inside the cavity of a cage. Okay. Now, but in this work, since you already have talked that this is a kind of organic synthesis, let's talk about some organic synthesis. In this particular talk, I'm going to talk about carbon-nitrogen bond formation reactions or carbon-sulfur bond formation reactions, and I'll be talking about weak interactions, how we can control. Okay. So if we just look at this particular thing, that mainly here we are just one of the term I have used, organic CN bond synthesis, because I'm going to use hypervalent iodine reagent, and using the term organic, that means I'll try to avoid using any metal catalysis. And this is the kind of a general characteristics of an iodine reagent. If you look at this is a kind of, okay, in terms of very simple chemical knowledge or chemical term, that is a highly acidic. And if you have a kind of lone pair, what we call it's a Lewis base or highly basic, so that kind of acid base chemistry I'm going to talk about. Here it is a well-known term, just now I have talked that ammonia is basic, and also that iodine, okay, when you mix them, they are known as contact explosive. That means they generate an enormous amount of heat, and this is the chemical reactions. They produce an intermediate, that is your Ni3, and this is nothing but called your touch bomb. That means if we just kind of touch it, and that we do during the school level, different kind of various exhibitions, that placing the ammonia iodine mixture, and then when you walk through, there will be some kind of pataka, something like that. Okay, now here also that same chemistry, if you just try to look at, this is a iodine 3 species, and this is an amine. This is basic, and this is an acidic, and they are kind of contact explosive, generate a lot of heat. In the solid state, if you mix them together, they just charge, nothing else. Of course, we did in a very small scale. So we mix in a small scale, and that's how you observe. Now, here I'm going to talk about that we wanted to control these reactions, and I'm just talking about that means solid state and solid state reactions. If you were talking about contact explosive, that means mixing them, and ball milling, it's nothing but a grinding chemistry where you are just putting the maximum stress in a highly pressurized, in a kind of closed environment. And what we saw that if you can control the reactions, we just added some kind of explosion controller. Explosion controller is nothing but an acid salt. This acid salt will try to take over the amine basicity. And this particular amine basicity, what it will try to do, that it will try to lead a kind of explosion-free cross dehydrogenative coupling reaction, that means the amide synthesis. That means the amines basicity can be controlled by addition of an kind of an external additive, which is nothing but an acid. Using this chemistry, of course, we have we have also estimated the heat using a very simple calculation, that is also your isothermal titration calorimetry, and we could show that okay, relative comparison is not there, but what here it is there, that at least you can reduce the 50% of the heat. You can see that into no additive, and just because since it's the isothermal titration calorimetry could be done in the kind of liquid, okay, so we just did in a very different way, and of course we have compared that. Okay, and we have compared that basically that what exactly is happening with the different pKa value, which is matching with the amines basicity, and that's the started of amine iodine or chemistry. Now, in order to understand that if you just take an aniline, this is an iodine 5 reagent, this is nothing but called IBX, and this IBX, of course, it causes an explosion. But if you just take a benzamide, because you can see that nitrogen lone pair is no longer available, but therefore it is no reaction. But when you have a very simple way that to understand that both the functionalities are there in presence of IBX, of course, people will say this is a simple oxidation chemistry, but okay, I do agree, but what we also think that okay, probably that a reactive part and unreactive part, it is possible to successful to make some kind of molecule. Now, in this particular work, that again the same way, this phenyl, that iodobenzene and MCBBA, they generate an iodine 3 reagent. This particular again, it will be kind of that you can see that no reactions could be possible, or again the something mixing, it will cause some kind of charring. But you can see that when you have both the part in this particular molecule, there is a benzylic hydrogens, these are acidic in nature. So the intramolecularly, so the amine and this iodine 3 reagent, intramolecularly they could couple, and this is the reaction controller is basically the acidic hydrogen which is present within the molecule, and it is possible to synthesize a similar kind of a benzimidazole type of derivative. The same way, just now we have shown that in this particular process that this CN coupling could be possible, and of course the same way that particular reactions we have generated the polyvalent iodine reagent in situ using TBI THP, and now we have also shown the similar way the reactions can be controlled. Now this particular one, that means overall that iodine 3 or iodine 5, that exothermicity, the reaction be controlled by using a reactions controller, which is mainly we have taken a various kind of acid salt. Now in this again we have tried to understand that if when you try to do an intramolecular CsP2H amination reaction, that what are the factors we take into account? If you, in earlier cases, we are trying to use a different acid to control the amine basicity, but here we have intramolecularly introduced different kind of acids. That means acid means this is now kind of pi star antibonding orbital of this carbonyl carbon. This is the kind of sulfonyl group, and these are nothing but N to pi star CO, that particular interactions. It is possible to reduce the high reactivity of this amine, and also we will talk about this chemistry now. So, and also we have tried to understand a different solvent effect, that what we have seen, that when we are trying to have this kind of cationic intermediate and this trifluoroethanol or hexafluoroisopropanol, these are excellent solvents to stabilize this particular iodinium, that intermediate, and still we are trying to understand that what exactly that solvent plays a role, because they have a kind of very nice probably caging kind of environment to stabilize this kind of cationic environment. And now what we are trying to understand, so these and these, whether we can call them, it is a kind of an intermediate, this particular one, or it is an equivalent to some kind of nitrogen plus, that what Biju was talking about, the carbene, or so then it's a highly kind of active or reactive species, nitriniamine. It is a similar like to carbene, and also it is possible, if you look at the resonating structure, there are cases it is also possible that if the positive charge present at the kind of this particular carbon center, we call them as a kind of carbenium ion. Using this, okay, so before that I just want to talk about that while working with different iodine reagents, we have also looked at that similar kind of cyclization. It could be possible by choosing a proper solvent and iodine 3 that we have shown, but also a different way that N-hydrosuccinimide also could be possible, and also in the solid state different kind of cyclization, intramolecular cyclization could be possible. This is the kind of an extension of the work where we have used some sort of the use of the I plus region. Now again, coming back to the nitrinium ion, this again I've just told you that this is the nitrinium ion and this is carbenium ion. We have written couple of review article on this, that how the nitrinium ion can be reactive, but we have used this kind of concept of nitrinium ion in order to have some kind of other chemistry. So this is the chemistry. What we can see, that these are the two molecules. This is the kind of, in order to make a kind of carbazole, you can see this is you are taking an aniline and you are taking a benzene or toluene. It is possible just kind of dehydrogenated metal free simple coupling within a 1 hour at solvents like hexafluoroisopropanol or trifluoroethanol, that you can fuse two of the aromatic ring, and this is a kind of annihilation process. Since I'm doing some sort of organic chemistry, and of course at least 1 or 2 slides should have some kind of mechanistic slides. So what you can see, that this is the kind of generation of this nitrinium ion or equivalent. This nitrinium ion can be interconvertible to carbenium ion, and what happens, that this is in presence of a electron donor, that aromatic ring, it is possible. The first is the CC1 formation, and then followed by again one step, again the nitrinium ion, and basically the aromatic. The first was the intermolecular aromatic nucleophilic substitution, and followed by intramolecular. That means in one step it is possible that one can synthesize the carbazole derivatives. Now the same strategy we have used, that when you have that you cannot fuse them together, but if you have kind of a system like mesitylene, so in that case what happens, that we have seen there is a kind of migrations of the alkyl group could take place. And also if you just look at briefly again, that first again the same way that this particular intermediate is formed, and once this is particular is formed, you can see in order to cyclase, but there is a kind of the alkyl group migrations, and because of this alkyl group migrations, what we have synthesized the fused aromatic ring, that is the kind of carbazole derivative, where the kind of an alkyl group migrations could take place. Now this particular strategy, now we have taken that try to understand that how different alkyl group migrations could lead to help us to synthesize the carbazole. So if you just take a kind of this particular group where it can produce a cation, which is a tertiary, okay, this particular carbocation, which is a stable, okay, that does not lead to a migrations. So what we have seen here, that the alkyl group has completely gone, and we could able to synthesize, that means a carbonyl derivative where this one of the alkyl group was removed. Now, other way around, so when this particular one not so stable, we have also seen that by taking the similar strategy, that means the generator of the nitrosamine, this is nitrosamine equivalent. In that case, what we have seen here, that this particular group, when this methyl or ethyl group, that this particular hydrogen, as if it could be like a functional of a CH bond, which is at the distal position. Just looking at the very simple strategy again, that in that case, not generating a stable carbocation as the system. Now here also again, it's a kind of repetitions of the same work, that trying to understand the different conditions, that whether we can have just keeping the substitutions in the free, that whether it is possible that we can control the CC bond formation reactions in different places, or CN bond formation reaction which are controlled by the presence of this particular what kind of groups were present. Of course, I'm not going in details, but in also we could show that if there is a system here, that so far the nitrosamine is flexible, but in that case it is also possible to generate an intramolecular, this is something, there's a mistake probably here. So in that case, this should be plus only because of the camera at the end. So in this, what it is important here, that it is generating a kind of aromatic endocyclic nitrosamine, which also could be generated in presence of another iodine 3 reagent, that is your PIFA. Okay, so in that case, we could generate some sort of the phenanthridine molecule by simply taking this and the cyclization of that. Now we just try to talk about some simple hard soft acid base principle, and we, of course, this is also one of the approach we use in our day-to-day organic chemistry, at least to understand qualitatively how the reactions works. And mainly what we say, that when something we don't understand, we also use this, or maybe it's a hard interaction or soft interaction. So both way it is correct. Okay, so which way we try to understand here? But that means you generate a nitrosamine, and this is we consider as a soft electrophile. The soft electrophile in the sense, and this is a hard electrophile, because you are losing the aromatic ring current. So we believe that this is one is more reactive. That how do we prove it? So soft nucleophile means that electron is delocalized in between the two aromatic ring. So the nucleophilicity of a particular ring will not be that high. But where if you consider it's a hard electrophile, in that case, why it is possible that there because of this kind of restricted rotation, the communication between these two aromatic ring is not there. So that one of the group will be behaving like a hard nucleophile. So take this molecule just using iodine 3 and take an appropriate nucleophile. It is possible that we can have a kind of NH relation, or you can have a kind of CH relation. That means you can selectively form a CC bond versus CN bond by choosing an appropriate electrophile. And just now I showed, when we try to understand that why exactly it is happening, I don't know whether it's exactly, but we try to explain this reactions with the hard-sort acid base principle. Okay, now also this particular work, that same way, the generating of a kind of nitrosamine and try to do the cyclization. But what we have tried to understand in this particular slide, you can see that these are the two molecules, these are nothing but tautomers. And it is also well known to us that two tautomers can be controlled in two different solvents. So we have chosen two different solvents like difluoroacetic acid or hexafluoroisopropanol, and we could see that the relative populations of these particular two molecules are different in different solvent, and in presence of PIFA, it is also possible that we can have a kind of two different molecules can be selectively synthesized, and we have given a kind of term that regiodivergent. Of course, this is the one molecule, so that can exist in two tautomeric form, and you can make a kind of divergent synthesis by choosing an appropriate solvent. This is a very nothing else. Now coming to some, okay, since we have given enough time, so I'm going to talk about some carbon sulfur bond formation reactions using this particular strategy. So like, we have understood the weak interactions, like all of you know what is cation pi interactions, but like the way this also sulfur center, that means the SH also can form a very nice hydrogen bond with this aromatic ring. So if we just try to understand the steric versus electronic control, that you mix them together, if we just want to we know that what is the Markovnikov selectivity versus anti-Markovnikov selectivity, it is a completely an electronic control. But if you have a kind of a steric factor here, that means introducing a methyl group, so selectively what it is possible that it is getting switched. Whether the anti-Markovnikov selectivity would have more or whatever, that where you can have a kind of, because of this methyl group, there will be around the more of Markovnikov selectivity. So we also try to understand that how we can control the anti-Markovnikov, this TEC, it is nothing but one of the click. This is also well-known acceptable terminology in sulfur chemistry, that is your thiol in click. So if you mix them together, of course, that is the mixing together, what you can see that this is a kind of what we initially thought that this probably there are kind of lot of weak interactions are involved. I'll come to the mechanism again. And it is wrong way. Okay, this is a kind of anti-Markovnikov formation. But if you do the reactions in presence of silver metal, of course, we did the reactions with benzene because the silver salt was not soluble. Other is just mixing them together. It's a room temperature. Room temperature, of course, 35 to 40. It's my room temperature. That is my lab room temperature. Okay, so that's why we mention it. So Bhubaneswar is always blessed with a lot of light and heat, of course. So that's how it is. But okay, so when we did the same reactions in presence of some other butyl lithium, we also could demonstrate some sort of aerial dioxin activations or the same two of the substrate, by controlling the simple reactivity, whether you can selectively getting anti-Markovnikov TAC or different silver salt Markovnikov, or we can have a kind of a different aerial dioxin activation. But the latter we have to kind of revisited the mechanism recently. And what we have mentioned here, that sulfur center is an amphiteric in nature, because sulfur is a lone pair as well as d orbital. So it can be a very good donor of electron, or it can be a very good acceptor of electron. So if you try to understand here, that means the sulfur probably it is acting as a acceptor here, because pi bond, which is a more electron rich. So that is by natural selections, it will lead to an anti-Markovnikov one. But by any chance that if you try to add some kind of silver salt, so this pi bond will try to coordinate with the silver cation, that is the cation pi interaction. So this particular double bond will be electron deficient. As a result, the sulfur center will be nucleophilic. So therefore, by simple understanding this, it is also possible the normal polarity versus Umpulung polarity can be switched by choosing an appropriate interaction. Here, another work what we have shown here, if you just look at the amide bond reactivity, amide bond, its proton, it's okay, basically amide reactivity, that amide proton available for hydrogen bonding, generally it's not because of this. In this particular case, if you have an alkyne attached to this carbonyl center, so this carbonyl is no longer a good receiver of this electron from this nitrogen. So therefore, this amide proton can be controlled, can be used for a controlled hydrogen bonding. So the same thiolene click reactions on the neat condition, it is possible by control this hydrogen bonding and jet selective anti-Markovnikov product we could get. But in order to understand that, if you take a kind of that, I think I have a mechanism here. Yes. Okay. So this is the kind of the particular reactivity. But in that case, when you have ortho amino group, which will preferably form a stronger hydrogen bond, in that case, it is also possible by simple choosing and hydrogen bonding interactions. Here also it is possible that we could switch from anti-Markovnikov to jet selective Markovnikov. So another weak interactions, probably it is also relatively unknown to many of the organic chemists, but it is in organic chemistry, it is well known. So there is a kind of sulfur and oxygen in the close proximity, proper geometry. It is also possible that oxygen lone pair can be donated to the sulfur center. And this is a kind of sulfur oxygen interaction. And what we have seen here, instead of going in details, that certain terminal alkynes, so during this kind of thiol addition in presence of a base, that is your lithium tertiary butoxide, so it is also possible. And this is the kind of, in this particular one, it is a kind of acting as a radical initiator. So the radical generation, and there are, of course, there are kind of, we have the kind of supporting evidences from literature that control the reactions, the jet selectivity was controlled by the sulfur oxygen interactions. Okay. Now, in this case, so far we are successful that, simple hydrogen bonding or anti-Markovnikov jet selective. Here also during sulfur oxygen interactions, it is also possible to have kind of anti-Markovnikov selective. But recently we have also developed by simple understanding lithium tertiary butoxide, ethanol, benzyl mercaptan, we can have a kind of different understanding. It is also possible to have a kind of a stereo-specific synthesis. That means 100% Z and anti-Markovnikov selectivity. There is no such kind of any other. So, for example, that if you just look at the mechanism, we try to understand the memory of stereoselectivity. And we have given this term. I really don't know that still the paper is not accepted. People are really asking a lot of questions, but at least I can explain this. So this is the kind of benzyl mercaptan. So it's a terminal alkane because this addition, it's obvious from these directions because this carbon ion will be stabilized. And after that, once this is formed, that what we get Z is to E, that is around 96:4. So this is the well-known mechanism that in presence of base that there will be kind of addition, elimination, addition. That is the mechanism. So this again there will be elimination. So this particular intermediate is formed. Now this intermediate, if again going to the same starting material, then of course then you will not be able to push it to 100%. Rather, again when it's just you are trying to waiting for a longer time or trying to using a better solvent that hydrogen bonding which can form a very nice hydrogen bonding, we have some proof. So we have seen that slowly it is also possible to push the reactions to 100%, and that is a kind of stereo specific synthesis. And these are some of the kind of solvent effect we have shown that which can be comparable with the better hydrogen bonding donating or hydrogen bonding accepting. But here you can see the trifluoroethanol, which is not high. We try to understand the mechanism. Probably it will form a kind of a solvent cage, which can basically we'll try to understand. Okay, we have proposed something that by understanding that what are the factors can control the stereo-specific synthesis. Now, of course, that iodine 3 work that we have been working for this for a long time. So we have also shown the different iodine reagent can be used. I'm not going in details this, but I'll skip it. Okay, so only thing it is possible, there another just very small one slide that where you can show that it is also possible that halogen bond in details, I'm going in details, but the only thing what we can show here, okay, that we can do a kind of a simple cyclization reaction using a carbon tetrabromide, which is nothing but a halogen bonding catalysis. So if you just look at this particular molecule, this one carbon bromine bond, this bromine has a sigma star antibonding orbital because okay, this sigma star antibonding orbital can interact with the oxygen lone pair. And I know Santanu is not happy with this my term, but I'm telling you, so that this particular lone pair will try to interact with this, So in this case, that whole group is a kind of like CBr3 that will be electron withdrawing. Therefore, the overall this part is an electronegative. So this bond will be that bromine, will have a kind of a better sigma star that antibonding orbital which is the acceptor. So therefore, there will be a good donation. And as a result, like the way Professor Ramesh Sastry had shown some kind of activations of double bond, similar way that this was kind of halogen bond donor, halogen bond, not donor, sorry, acceptor. So it is also possible to activate some of the kind of this particular cyclization reaction. Okay, now another 5 to 10 minutes, I have 10 minutes time. I have a stopwatch, so no problem at all. I'm just counting the time. So, so that is the, like most of the people are doing, nowadays the trend Nobel Prize has been given already. So I don't worry about that, So doing some kind of visible light photocatalysis just for the carry out my day-to-day life, So commonly used photocatalysis are these ones. That some of the kind of, these are metal free, these are kind of different dyes, or you can see there are kind of various metal based catalysis. And this is so these are kind of the basic requirement that strong visible absorption, long excited state lifetime, and the stable under photocatalytic catalytic conditions. And this is the review article we wrote about. We did some kind of chemistry. This is an invited article in Archive. So now commonly used light sources that whether all of you can identify easily what are these. So we are mainly focusing on this particular the visible light, that is the LED lamps, and you can see here these are the kind of LED lamps, which is the that absorption around 400 to 700 nanometer. So in this case, okay, that again, one of the most important part, if you want to do a visible light photocatalysis, we try to understand that oxidative reduction cycle, that which one will give the electron, which will accept electron, and that can be easily understandable by doing some kind of cyclic voltammetric experiments. Okay, so and again, so this is one of the well-known photocatalysts because the first work has been published by this particular reagent, which was in 1989 and published by Journal of the Chemical Society, Chemcom. Oh no, so Perkin transaction. The first paper came, and the person who discovered this, I don't know whether he's alive or not. He did not get the Nobel Prize. Okay, but anyway, the important part is that it's a kind of strong visible absorption, efficient generation of this kind of excited state, long excited state lifetime, and stability under photochromatic conduction. So these are, some of the requirements. There are experts are sitting here. Okay, so since that this was the kind of our first example to begin with, they're trying to have a kind of again iodine 3 reagent. Just think what this is a kind of big group was there. We tried to do that whether reactions work or not, and we could show that this particular reactions it is also possible simple doing a kind of thioacetylation reaction. And mechanistically, we have understood that this particular group breaks and generate a kind of this particular radical. This radical generate a kind of thiol radical, which will try to add this and so and so. Okay, that is the way, the stepwise. If you try to follow this, so that is the kind of thioacetylation reaction. In this also, we have shown here that another example that we just mix them together in presence of this N-hydrosuccinimide, that you can in situ generate something like your unsymmetrical, basically thiols. Okay, today I just skip that one. So that particular, again, it is also possible using visible light, you can get back here, that is kind of reversible reaction. Now, where the kind of, this is the kind of sulfur iodine interactions, which stabilizes here the unsymmetrical disulfides. Now, again, coming to that another commercially available reagent, this is the kind of mesetyl actinium perchlorate, and this is also this salt as somehow it is we have started using this particular metal-free catalysis, and we could show that this is taking a kind of this alcohol, and it is also possible that one-step synthesis of kind of thioacetal in presence of 3-watt blue LED 24 hours, benzyl alcohol to basically the thiol that protected thioethers. Okay, thioacetal. Okay. Now, so again, just some of the kind of substrate scope, and again what we have shown here that not only that this is a kind of very well-known reactions, and that if you have this kind of substrate and in presence of a first these radical generations, and it is also possible the nitrogen chlorine bond can be selectively broken using this visible light catalysis, and followed by, if you just look at the mechanism, that first step. Okay, I'm not going in details. So, but only thing what we want to say that using this photocatalysis, it is also possible that aryl alkanate we can have a kind of a simple that cyclization reaction. The more important part was that we could selectively, that means this nitrogen chlorine bond could be broken from N-chlorosuccinimide using simple this visible light photocatalysis, that is nothing but your mesetyl actinium that perchlorate. Okay, now just one small information to the students that how we establish the mechanism. Okay, that we try to understand the fluorescence quenching, or this is basically the star monomer plot we use. Then also we try to understand whether radical pathway or not. So therefore we try to do some kind of reactions. What are the oxidation reductions potential, and how we can basically the light, whether the reaction is proceeding not. And this is a kind of course, we are not, if you are expert, but only thing what we want to say, this is one of the reagents called your, that DMPO. This is also commercially available. When we try to use some sort of, the radicals, so they give you kind of an generation of the radical with the DMPO adduct, and that shows a kind of APR activity. So that also proved that also radical proceeds via, that radical pathway. So here with the works recently we have shown that that this heterocycles, if you want to do a kind of oxygenation here. So we have taken some kind of ipso substitution. I'm not going in detail, but also it is also possible that photochemically it is also possible to do some kind of oxygen insertion, that is aerial oxygen. That oxygen comes from oxygen balloon, and in presence of this catalysis, that is the same acridinium catalysis, it is also possible to do some kind of quinoxalin 2,3 dione synthesis, but using a visible light photocatalysis. Again, just one more information that there are also some of the kind of control experiment we do. Then in presence of tempo, which is a radical scavenger, BHT radical scavenger, CuCl2 electron scavenger, or it's a superoxide radical anion scavenger, singlet oxygen. Also, these are the kind of informations we generally put in the kind of in the mechanistic study, that these are the kind of important requirements that we do. Okay, now again, recently it has been again this one, that if you just we have been using carbon tetrabromide, we have shown the kind of some catalytic activity, but here also it is also we have shown here that this particular one, that carbon tetrabromide or CbRCl3, it is possible that that the terminal alkyne, that that we can have a kind of that alpha beta unsaturated the ketones, that is your gem dihalo. So again, the mechanistically, that whether some kind of bromine radical generation and then additions. Okay, these are the kind of stepwise. I'm not going in details again, but only thing it is possible that using a kind of the CBr bond of carbon tetrabromide can be broken very easily, and we can synthesize various gem dihaloinones, whether it's a carbon tetrabromide or carbon tetrachloride. Now the last, also, we have also here that same reactions we have shown earlier that can be cyclized. But first we have shown that this particular reaction is also possible, that you can do CN bond coupling reactions using UV light, but this particular reactions in presence of visible light also it could be possible, and we have been investigating now. The couple of just 2 minutes already here. So here you can see that nowadays perovskite materials, now people are kind of excited about the perovskite materials because these are a kind of huge application, solar cell, LED, all these things. But perovskite is nothing but a kind of inorganic material which structure ABX3, So that in this one, so we have started synthesizing some of the perovskites by simple strategy, making this. This is the synthesis part using the halo precursor, cesium lead bromide. And of course, this is the kind of synthesis was done by Dr. Subhadeep Ghosh from our department colleague, and since I have given him the gift of dibromohydrin, and he gave me my name there in that paper. So, so I was very much happy. Just simple, this was reported with an SS energy letter, and by simply reporting a synthesis with a dibromohydrin, that means it might be easier. So in the meanwhile, my postdoc joined in my group who did a PhD at IMMT with a material background. चल देखते हैं क्या होते हैं. So शुरू हम लोग कर दिया. Okay. So then what happens then? Okay, by this by changing that another brominating agent, same synthesis, we could get an orthorhombic perovskite, and we are able to do the same reactions CBr4, that same alkyne, that it can have an application. And yesterday morning, this paper is accepted in chemistry materials. Okay. So happy now. I'm focusing on perovskites in coming future because, and this particular reactions was done in sunlight. Hopefully, this is a kind of a sustainable synthesis. All right. So this is the kind of overall my end. I've talked about some kind of visible light photocatalysis reactions, and also I have talked about some hyperboron iodine reagent where without metal free, that some of the kind of synthesis of various heterocycles controlling reactions, we could show that how it could be possible. And also we have talked about some kind of supramolecular catalysis where various carbon sulfur bond formation reactions. And this is a finally acknowledgement slide. The postdoc current who did develop this for perovskites, he's making the perovskites. I'm still learning it because I don't know anything, honestly speaking. So every day I call him and I'm going for discussion, learning from him, and hopefully his term will be over very soon, but hopefully I'll learn before that. And the visible light photocatalysis was developed by Milan Pramanik, and then continued. And this CBr4 activation work is done by Tarun. who is currently here. And okay, and I got whom to acknowledge. Sabko acknowledge kar diya. Chalo. And thank you all. Okay, I'm happy that I'll be taking a couple of questions. If you have.
Sanjay is happy. We all are happy also, and so we'll invite some questions from the audience. Yes, Rabi.
Yeah. Yes.
The last product which you showed, it's vinylogous bromide, acid bromide, and acid chlorides. So
this
yes,
one,
those things, right?
Oh.
So was it stable to column, and you could
This one?
get, yeah.
Yeah, this is stable.
Okay.
We'll discuss during the tea in some point tomorrow. All right. Yeah, Ravi, please. I think this is stable. We have isolated, characterized, and these are pretty stable. And also, and we could do the reactions using blue LED and also in sunlight, because catwalk between this chemistry and biology in the first floor. So we sometimes that's why the Bhubaneswar were blessed with heat and light, and that sunlight is good enough to do the reactions. Yeah, next.
Any more questions, audience?
Yes, Madhu.
Here you are mentioning about that. I think why not halogen bonding? Okay. So when you are doing some activation, I forgot the slide name.
No, slide name.
Yes, 42 something ketone activation.
Yeah. Okay.
Severe
Yeah, here it
proteases.
is.
Yeah, I am asking like why not halogen bonding? Because that is
This is the halogen bonding I'm talking about. This is the one.
okay. This is halogen.
XB. XB is the term used for the halogen bonding.
Okay. Thanks. Then it is linear.
No, it should not be linear, because if you just look at, that, okay.
Be like, yeah, linear.
Oh, no, okay. There's a mistake. Okay.
Because the electron density there. Thank you.
Okay.
Anyone? Any more questions?
Yeah, Biplab.
Yes. There's so much information.
Yeah, no problem.
So much more. I have a question. So regarding this hard cation and the soft cation.
Yes.
So nitrogen plus, I will say it is hard. Every day.
Yeah, I know, because in that case, okay, instead of going, so when the aromatic ring, okay, nitrogen cation is always hard. We are trying to understand, but if you are kind of destroying the aromaticity, the molecule become more reactive. So it is the cation is more reactive, that is the hard one. That's what we try to understand.
Still nitrogen plus is hard. Still nitrogen plus is hard, wherever it is.
No. So you're breaking the kind of aromaticity now. So basically we try to.
But that cation, that positive charge is delocalized.
I know. So we're trying to understand.
Like one way of speaking, hard and soft is like the charge density.
See,
of a
hard and
particular
soft.
region of.
So relative hard and soft, we try to. This is a qualitative term. There is no quantification. So out of these two molecules, which
terms of, if one talk about quantitative in terms of Sallen-Goldman, so then you have to talk about that charge density in a particular volume of orbit.
No, yeah.
Nitrogen being a smaller,
So what happens? So in this case, the nitrogen is the out of the aromatic ring. It's that molecule that in the particular intermediate is not staying as a cation alone, because it's associated with this other, that what you have shown, that that iodinium substrate. So therefore, but when this particular coming to this ring, that has become more reactive. Not only breaking the aromatic ring, but other associated that anions or particular iodinium intermediate, which is not there to stabilize that particular one. So therefore, the relative reactivity out of these two systems, when one is more reactive, that means the harder. If it is the less reactive, that is the softer. So that's what we understand. For example, simple ethyl bromide, if you treat with the potassium cyanide, you will get the ethyl cyanide. And when you treat with the silver bromide, you will get the isonitrile. So in that case, what it does, that silver is try to help the bromine coordination, as that particular carbon center become more, electrophilic.
It's more carbocation.
That means it's a harder center. So we understand that which one is more reactive, that is the harder.
That reduce chemistry can easily be explained by.
No, that is true, and also we have the proof that so when the same reactions, if you try to do that in presence of No, it's gone somewhere. So what is that? So you took the bimecyl versus biphenyl. Anyway, just take a mesitylene group. That in that case, what we could observe here. So in this case, you can see here that if the nucleophilicity of a particular center, that electron, the biphenyl ring electron is distributed. So therefore, it is a kind of a softer nucleophile compared to this one, that because of the restricted rotation, this mesityle have a kind of harder nucleophile. Rather, if you just look at more carefully, as if this is the nucleophile and this group is a kind of an electron donor. So that as if one group is electron donor and another group is reactive. So this is the kind of harder nucleophile. So in that case, so when you just what is the reaction condition? You take this, use iodine 3 and use some kind of a nucleophile, that is your biphenyl or bimecyl, and in the biphenyl system you get the kind of CN bond formation, and bimecyl you get the kind of CHR. So that's how we are trying to understand. So that's the term. Before that I told that. So when you don't understand anything, we tell something like, you know, hard soft acid base. So probably that is the answer. If I try to understand, so I am happy with this term. Chalega. Yeah, students.
There is no more question. Let us thank Prasanjit for just.
Yes, one more question is there. So
Get a chance.
yes, okay.
Sir, nice presentation, sir. My doubt is, how did you check the yield for while you are doing light on-off experiment?
What?
How did you check yield for light on-off experiment?
On-off experiment.
ये पूरा मेरा group members है. So they do it. Okay. I'm just coming to. So you just any particular reaction, that is the how you check a reactions, monitoring the reactions, the TLC. Okay. So you keep it off, take a Ellicott and then try to even the small workup or something like that. You take a NMR, that is also possible.
By NMR, crude NMR.
Yeah, you can do it. Or isolate something, some portions and do a proton NMR or check the kind of percentage yield. Or, you know, then it is also possible that if you are trying to do the reactions in an NMR tube with a deuterated solvent, if the solvent is available with us, you know, that also directly we have a kind of J-Young NMR tube where you can identical J-Young NMR tube, you can check it in the available in the many of the companies. So there you can do the reactions under high pressure, high temperature, even also under argon atmosphere in an NMR tube. So that particular reactions tube you use it. So directly just go and do the reactions in presence of an internal standard. The internal standard means the first portion which is unreactive to the union of the substrate, which does not have any overlap with your compound or product or starting material spectrum. So that particular one, with the time to time you monitor it, you will get this the clean idea that how the reaction is proceeding. So both way it is correct. So if you can afford to do a large scale reactions, you take the Ellicott, because if you want to save the money with the NMR solvents, so that is the crude oil it is possible, and NMR tube experiment also it is possible. Choice is yours, which one is available with your hand.
Okay, thank you, sir.
Yeah, all right. Yeah, the bridge. No, actually, see, initially we started from Jatni Market to Bapuji Nagar, but you know, honestly speaking, I'm not joking. So we failed, and then one of my friend was starting his company, but he has shifted to other business now. So I requested him because he did PhD and postdocs in hi-fi lab and with the photophysics, but he has left the business, his job, and so I requested him to make it, and he did supply some good one. But recently, our student Ashish Mathur is sitting there. We got from some setup from NIT Roorkela. I think that is also working. And we have the setup, the Luzchem photoreactor. That is also possible that you can change the kind of tubes that we can buy from different wavelengths. That is also we are using. You have some other, you know, mercury lamp. There you can use that we are not using because the lamp is not working. So you can use the filter. You can use it. So we have kind of different, but you know, honestly speaking, don't buy from Chatni Market. Try to get from, you know. No, that is concern because we try to measure it from this, you know, luminance or lux, how much lux it has been used. So that is also try to compare, measure of so distant optimization. But the better quality ones nowadays it's available in the market in a good company they're supplying. So try to have it. No, initially we did Jugaad. I went to Bapuji Nagar running door to door.
Okay, thank you, Prasenjit, and I thank both the speaker for the excellent talk and the audience for the stimulating discussion. Yeah. Any committee member?
I would now request Dr. Shrikant Patra to felicitate Professor P.K. Patel for chairing this session.
So on behalf of the organizing committee, my pleasure to present a small memento as a token of appreciation to Professor B.K. Patel for chairing this session very nicely.
Thank you, sir, for the lecture. We have heard profound and impactful lectures from our honorable guests, Professor Raman Sastry and Professor Mal. It is our immense fortune to have them amongst us. Thank you so much, sir. As we come to the conclusion of day one of the workshop, I would once again like to express my gratitude to all the participants for their keen participation and to everyone who has directly or indirectly contributed to the success of day one of this workshop. You can follow us on Instagram for some beautiful pictures from the workshop. The Instagram handle is OECSS'_2022, which itself reads the title of the workshop. As the workshop is going as per the schedule, we have almost a 2-hour break before the commencement of gala dinner. You are welcome to take a glance at our lush green campus situated at the foot of Barunai Hill. You all are requested to join us with family for the gala dinner at 7:30 p.m., which will be graced by our Honorable Director, Professor Sripad Kalmarkar as well. Let us end the first day of the workshop with a Blue Ocean tea. We'll be looking forward to meeting you all tomorrow for the second day of the 2-day workshop on Organo and Electrocatalysis for Sustainable Synthesis, OECSS 2022 at precisely 8:45 a.m. here in the community center. Thank you and a very good evening to all of you. It's a humble request. Please join us for the dinner. Thank you.